I think there are still seats at the front. So welcome to the 4th annual summit of the Center for Responsible Machine Learning. And this is also our second in-person event. In the last 2 years, we've been doing this virtually. So this year, we're very happy to finally meet everybody in person. So we have a wonderful program throughout the day. I'll tell you more in just a second. But I'd like to welcome Professor Theresa Pollock, who is the Distinguished Professor of Material and also Interim Dean of College of Engineering. So Theresa will tell you a little bit about her address. So let's welcome.
Okay, thank you very much, William, and welcome to the summit. It's wonderful to see so many of you here in person. Since 2019, the center has created a unique platform for discussion of topics relevant to AI and ML. And it's been able to host a lot of pioneers in the field and bring attention to the campus and our accomplishments in this area. And so we're pleased today to be having an internal meeting where everyone can have a chance to talk to each other. I would like to point out that AI/ML was a topic that came to the top in our strategic planning exercise that the faculty ran last year. And so we think this is a good opportunity to be discussing foundational aspects, applications, and things that could be going on campus in the future. And so if you look at the program, I think this symposium is characteristic of what we're good at. We have speakers from CS, psych and brain science, math, mechanical engineering, electrical and computer engineering, statistics, physics, linguistics, and technology management. So that today and tomorrow, just today, that we can use this summit to have dialogues, think about funding opportunities, think about what the future looks like in this area here at UCSB. So everyone enjoy, and I look forward to the talks. So thank you, William.
Thank you. Thank you so much, Theresa, for this wonderful welcome remark and introduction. And as you know, we cannot do this alone in the College of Engineering. So certainly, I think this is a collaborative effort, right, for the entire campus. And I'm also very glad that we are very honored to have Dean Pierre Wiesiers to join us today. So Pierre is the Executive Dean of the Letter Science, and Pierre will tell us a little bit from the other angle, how we actually see, right, AI and machine learning in the future of this campus. So welcome, Pierre.
Indeed, good morning, everyone, and it's great to see so many of you here in person. And before I get started, maybe I should really congratulate William and his colleagues for putting together such a wonderful program, which really shows the strength of what, and the character of what UCSB is all about. And that is a truly collaborative and highly interdisciplinary endeavor. So, as you know, artificial intelligence has become a critical research topic in many subjects across literally all areas of our campus: science, engineering, the social sciences, and the humanities. Just a few examples to demonstrate the broad reach of the field. Faculty in the English department, for instance, study now generative pre-trained transformer 3. I had to look up what that is, but now I know. That is to produce human-like text for creative writing. And then there is, in the social sciences, we have in the Department of Communication an example where the research is on AI and fake news, a highly topical theme. And then there's physics. I see Claudio in the audience, where AI and convolutional neural networks are used for experimental physics, and so on and so on. So there are multiple examples that cross many different departments and divisions. The Center for Responsible Machine Learning aims indeed to bring together AI researchers with experts from other disciplines to push modern AI tools into every area of science and engineering and the social sciences and humanities as well. And this has two goals. One is certainly to push the frontier, to push the research envelope, but also, very importantly, to teach our students, both graduate and undergraduate students. So for today, I think the goal is certainly to keep lowering the barriers that still might exist between departments and divisions and fields, and help faculty and students to understand each other's work in foundations and applications, and of the applications of AI and machine learning. The goal is to stimulate groundbreaking research ideas that push the interdisciplinary research boundaries and transform each discipline. So what we want to achieve here is to create a virtuous circle of AI and science, how AI can advance science, but also how science can help us design better AI algorithms, systems, and tools. So to do this, we need to bring together scientists who work on AI, foundation, and algorithms, as well as practitioners who have in-depth domain knowledge. So I wish you all a very successful summit, and learn from each other, and have a wonderful day.
Thank you. Thank you, Pierre and Theresa. Really wonderful remarks about, AI machine learning and also what we've done so far. So let me tell you a little bit about the center and also overview of today's event. But before that, I still want to briefly mention about the COVID-19 guidelines. The reason is because today's event, it is a big event. We're gonna have a few hundred people coming in and out. I want to make sure that you are aware of the existing policies and the latest policy updates by the UCSB COVID-19 task force. So this is for your information, and you probably have already got the same email about a month ago, okay? Center for Responsible Machine Learning was started in 2019, early spring 2019, and we are very interested in the interdisciplinary area of computer science, AI, and also fairness, bias, privacy, transparency, explainability, accountability in the context, right, of these AI algorithms and foundational models. So how do we understand, right, this ethical use of AI algorithms, legal and policy implications, even the energy efficiency angle, right? So we're at the IE building today. So there are a lot of, very interesting dimensions and axes that we have to think about when we use AI and machine learning technologies. So far, we've been actively working with the Mellon Champ Initiative on Mind and Machine Intelligence, the IEE, the Institute for Collaborative Biotechnology, and also the Data Science Initiative. So this is, again, also the with the Center for Information Technology and Society. So certainly there are a lot of interests, right, and also stakeholders for AI and machine learning on this campus. Want to briefly tell you a little bit about our engagement. So far, we have 60 faculty affiliates and 20 departments, and we have a lot of different events. So annually, we have this Responsible Machine Learning Summit, and this is the second in-person version. We also have distinguished lecture throughout the existing structure. So we have each quarter we have distinguished lectures. We have other events as well, we also have, this joint proposal writing opportunities between faculties, and we've been actively engaging the industry and also the students throughout different events in recent years. Okay, so let me review a little bit about the history, just quick 1 or 2 minute review about what we have done in the last few years, because everybody is so disconnected, right, in the last 2 years. And some of you I met in person for the first time because we're only connecting through Zoom in the last 2 years. So for the 2019, we actually had an in-person version in the Moshe Alumni House. That was the in-person version, and we were focusing on AI and fairness at the time. We had about 100 people attendance, and a lot of distinguished speakers from outside, from industry leaders and also the academic leaders. And then, unfortunately, COVID hit. We moved all of our events online, so we had our first online events in 2020 around the same time. And then we were basically talking about AI and COVID at the time. We had a huge audience, but also have people attending from across the country and international attendees as well. And we had about 400 registered and close to 300 people who attended online throughout the day. And have leaders from WHO, all these different universities to really discuss, right, the impact of AI and machine learning on COVID and how can we use AI and machine learning help deal with the impact, right, of the COVID. And then last year, we also had a virtual event, and last year's focus was AI and social good. We also have a similar number of registered participants, and we have a lot of distinguished speakers who's interested in AI and social science and social work. So this is, the existing event, and then I'm just so happy that we're able to gather everybody in person today. Now, finally, the year is 2022. Now we can do everything in person. So from the YouTube, you can also watch all of the existing talks from all of our lectures in the past. So let me tell you a little bit about why we are, gathering here today. So a few years ago, before the pandemic, Tim Sherwood, who was, I think, Associate Vice Chancellor at the time, we were sitting at a lunch, and he was suggesting me to maybe gather some, AI machine learning faculty on campus to discuss cluster hire, right, to discuss joint hire for different departments for faculty and for students. And then we thought it was a good idea. So this is where we are today. We still provide dinner today. We still provide lunch today, but it's going to be more than just a few faculty. So we actually have a 270 registered day. So you're going to see, hundreds of people coming in and out throughout the day. And we also have a breakout session with 3 topics that you can join. I'll give you more instruction when we get closer to that session in the afternoon. We have 2 overflow conference rooms at any point because, again, this is depends on the situation. And we have 16 speakers from 11 departments actually represented today for this summit. For the morning, so we'll have Miguel's keynote in just a second, and then we have the ML Foundation session this morning, because I really believe the theoretical foundations and the practical algorithms are both so important, right, for the AI and machine learning. So the morning sessions will be a little bit more theoretical. In the afternoon, you're going to see a whole variety of applications in different areas. And then we have the lunch break. The lunch will be catered outside around 11:30, so please join us for lunch. We have Manjuna's keynote in the afternoon, and then Yuxiang will be hosting that keynote. And we'll have an exciting ML for Science and Engineering session with wonderful lineup of speakers from different areas. And also, after the break, like I said, we have, ML for social science and humanities session. Originally, we're planning to have, good featuring of the, AI and arts, but unfortunately, due to some family reasons, one of our speakers were not able to join us today. So we're hoping to have, maybe AI for arts next time as a separate session. And then we'll have the breakout session around, I would say, around 4:10, and hopefully we close everything by 5 p.m. today, okay? The logistics, just let me tell you a little bit about logistics. Please silence your cell phone if you haven't done so. Please hold your questions towards the end of each session, because typically each session we have more than 3 to 4 speakers. So if you can hold your questions towards the end, we'll have the speakers line up at the front so we can have a panel that we can discuss with the speakers in depth. The lunch, like I said, will be provided outside. The breakout sessions, we have 3 different topics, but they are ordered organized in a way that is unstructured in nature. So we really want to stimulate more thoughts and ideas about collaboration. So each group will have 1 leader, and then towards the end, we'll summarize, right, what we find out at these different breakout sessions. Acknowledgement, I really want to thank a lot of people to make this happen. It's really a collaborative effort. I want to thank all of the speakers and you for joining us. And I want to thank my co-director, Yuxiang, for really helping us make this happen. I want to thank the organizing committee, Laura is the secret person who's running the CRML. And of course, with our colleagues in development, we really appreciate that. And also Jasmine for helping out today. And the session chairs, Kyle and the team and Manoush, we really appreciate your support. Of course, the DEF CON team has been really helpful for us. And finally, special thanks to the campus and college leadership and department leadership for making this happen. I also really want to thank the Mellon Champion Initiative on Mind and Machine Intelligence for the support. And finally, last but not least, I want to really thank AppFolio for being our sponsor for today's event, and also Amazon Alexa for being a sponsor for today's event. With all that, let's kick off today's program. So first of all, I would like to introduce Professor Miguel Axton, who is also my partner in crime in the Mind and Machine Intelligence Initiative. So Miguel has a very distinguished career, who's now this Mellon Champ Distinguished Professor in brain and psychology. So they have been doing a line of wonderful work in looking at human vision and machine vision, and also look at human AI collaboration. So with all that, let's welcome our first speaker, keynote speaker, Miguel.
I'm good with this one.
Okay.
Yeah. Now I can. Thanks, William. I do not have audio. Okay. There we go. Thanks, William. Very happy to be here in person and ramp up with our interactions across the campus. One of the among the many things, I've noticed my research has taken a little bit of a dip with COVID because I haven't seen my engineering and computer science colleagues as much. So I'm hoping to make up for that. So William told me, this should be sort of general. It should try to generate thought and questions, so we actually have good discussions in the coffees and the rest of the day, and it should be entertaining. So let me start. One of the sort of threads and themes of the Mellon Champ Initiative in Mind and Machine Intelligence is to really compare the differences and similarities, how humans and machines see, attend, learn, and reason. And the idea there is, like Pierre was stating, is to both shed some light on what is unique about humans and also try to inform sort of the next generation AI, try to understand where are the gaps and why might those be. So, in that vein, I've sort of brought I have a talk that will actually be looking at 3 different case scenarios where we're comparing humans and DNNs. The first 2 are having to do with visual perception, how machines and humans see. And the third one is a newer sort of line of work which has to do, which is a little bit different from what I typically do, which is really how machines and humans sort of make inferences about the knowledge of another person. I know some of you said visual search again, because you've probably, the first one you might heard me before talk about that. And so don't run out, because it's gonna be a little bit of that, but we're gonna have to revisit. So if you saw a previous talk on this, we're gonna revisit that, because since you last saw me talk about this, we've had to revisit the topic. Things have happened in machine learning, and we've had to sort of revise our opinion. So let's get started. I'm going to have a scoreboard, okay? So we're going to have a scoreboard, and game starts 0-0, humans, DNNs. We're going to start with visual search, and I'm going to start with a demo. I've shown this demo before. If you've seen it before, don't ruin it for me, okay? Just restrain yourself. Be like, God. So this is what's going to happen. So it's going to be a demo that sort of illustrates how your brain works and how you actually search for things. I'm going to briefly, so here we go. Demo is coming. So I'm going to briefly show you an image. And I want you to look for a toothbrush that's on the scene, and when you find it, raise your hand. And I'm not going to the images. I'm going to show the image, so do it quickly because I'm not going to leave the image for a long time. So just raise your hand when you find the toothbrush. Here we go. Okay, good. You guys are good. Yeah. Okay. So here's a question. Raise your hand if you found the red toothbrush. Okay, that was a trick question. I was just making sure you guys are not, there is no red toothbrush. Okay. Raise your hand if you found the white and green toothbrush. Oh, there's a lot of you. Okay. Now raise your hand if you found the bluish purple. 2 of you. 3, 4. Okay, there are a few. Yeah, Debbie, you know this. Okay, so most of you, you can see, found this toothbrush. Hold on right here. Let me see. I need to use my, yeah, you're ready. So look, I'm going to use, lasers tend to, okay, I'm going to put the lasers. So this is your the toothbrush most of you found. But I think most of you missed this one here. So what happened there? I mean, arguably you'd say this one is actually way more salient and visible than this one. So what happened there? So what is this revealing? Well, what this is revealing is what your brain does, it sort of rapidly analyzes this scene, and then it attends at spatial sizes or spatial scales that are typical for a toothbrush relative to the surrounding objects and scene. And you sort of ignore things that are not at the right size. So that's something particular about how humans search. You actually use, your brain uses information about the relationship of in sizes across objects, and also where objects might or might not appear. And when something in the image violates that, you miss it, okay? So obviously, this is a very, very compelling demo. It works quite well, as you could see, but I can't, we're in science, so we have to run experiments. So we had to bring naive subjects and show many of these images to demonstrate this effect. And of course, that is an actual real object. It's in my lab. It's a giant toothbrush. I don't know. I think Hollywood people, they use these things for props in Hollywood. So they're actually some giant objects you can buy. But obviously, there's the limited amount. So to do the experiment, we sort of had to compromise and actually do like the digital version, where I think you can see it here. There's like the toothbrush there at the right size, and here is the below it is the toothbrush at the large scale or giant toothbrush. I'm bringing my pointer back. Pointer is not working great. Okay, so what we did is we created many scenes like that, and the experiment would actually go. Okay, oops, sorry there. For a second, my screen froze. So this is how the experiment went. So you bring people into a lab, and then you have them look at this point. The pointer is not working great, so let's see if this one works here. Okay, can you see that? There, right there. So people look here, then there's a word that's briefly displayed, and it tells people what they're actually looking for. In this case, it's a toothbrush, but it could be many different objects. And then the scene comes up, and sometimes the object is at the right scale, and sometimes it's in this sort of giant spatial size relative to the background. And then they report whether they actually see it, they detect it or not. Half the times the object is there, half the times the object is not there. Okay, and they have to say, was it there or not? And then you're trying to see, is the basically reproduce what I actually showed you? Are people missing more often these sort of giant objects that are not at a typical scale. And indeed, what you find is, so this is on the y-axis, we have sort of the hit rate. And then here in gray is actually when it's at the normal size, the object is the normal size, and you can see that, you know, there's a huge effect where people miss these sort of giant objects. Now, when we first got this, you know, if you're in psych and brain sciences, you start with a behavioral study, and then immediately after that, if you get a strong effect like that, you want to understand where it happens in the brain. So we actually did a version of this experiment. We brought people into the imaging center, and using functional magnetic resonance imaging, we sort of identified brain areas. And in this case, there are two areas, this TOS, transverse occipital sulcus, and that is involved in object processing. That area particularly, when you start making the object large relative to the background, the response of that area will start diminishing. And the same thing for this area IPS, which is typically involved in attention. Now, there are tons of other areas and controls that do not show this. But these two areas seem to be very correlated to what we see in sort of behavior. So that's sort of an interesting thing. So we know that this is a very strong effect, and we know what are the brain areas that might be involved in this. Now let's bring 2017 CNNs, object detectors. So we have FastlyR CNN, YOLO, RFCN, and we run them through the same images and see whether this effect of size affects these convolutional neural networks. And what you find is that there is basically no significant, that you do not see this effect, that basically what this is saying is these object detectors, they just don't care whether they just detect the toothbrush. Doesn't matter what's the relationship to the scene. They're just looking at the features that define the object, and they just don't care. Okay, so this is a very strong difference in between how humans and these object detectors are finding objects. So, as a summary, humans 1, DNN 0. Now, you'd say, hold on. You're telling me humans missed the toothbrush, and that's a 1 for them? That scores as, that's counted. The DNN side were the ones that didn't miss the giant toothbrush. So why is this 1 for humans and 0 for DNNs? Shouldn't it be the opposite? Should it be 1, 0? I know, and that's what all my engineers tell me. You're thinking this all wrong, Miguel. So here's the idea. The idea is that this strategy that humans use is actually a useful strategy. It's an adaptive strategy to rapidly dismiss distractors that are not at the adequate size relative to the surround. This is particularly important for humans because you might or might not know, we see quite well what we're actually looking at, but in the visual periphery, we actually have sparse sampling, which is much more energy efficient, but we do not see things with good detail. No? Try reading or identifying a face in the periphery while you look, it's tough. Okay? So this becomes critical for biological organisms that have foveated visual systems like humans. And to some degree, it's also very important, or it could be very useful for computer vision. So let me give you a few examples, and there's many of these, but I just brought 4, of instances in where our CNNs are misclassifying or misdetecting an object, but if they actually used spatial relationships, they would not be fooled. So what do we have? To your left is a case where it detects a cell phone. And I think you don't need much convincing that, that would be a very large cell phone. It's like, maybe 1980s, I don't know, one of the first like this size cell phone. None of you would say that's a cell phone, okay? Even if you're like, so far so you couldn't see the details, you say that's just the wrong scale. And certainly that would be a hell of a big sports ball. So clearly you're using context and you're using size, that's it. And the same thing for the big, here's, toothbrush. Well, that's, let alone that there are other things that humans use. What are you doing with a toothbrush in the tool room? But, that could be the case. But the spatial sizes are all off. And sort of the CNNs are not using that. Okay? So that is why it's true. One of the byproducts of using this strategy is that humans miss giant toothbrushes. How many times does that happen? Not often. Okay, so yes, if you're dealing with a world where objects change in size, this would not be a good thing. But no, that doesn't happen often. You know, toothbrushes tend to appear in their small size. So so this is why this is the useful strategy that humans use and CNNs do not use. At the time when this happened, we started thinking, well, what's going on? Why is it that machines can't learn this relationship across objects? And you know, at the time I was reading a few things. One is this work that I highly recommend by Brandon Lake and Josh Tenenbaum, Building Machines That Learn and Think Like People. And then this other book came out in 2018, The Book of Why by Judea Pearl at UCLA. And they were making very, very compelling arguments about what is the difference between humans and machines, how machines are this sort of, you know, these statistical correlators, while the human mind has sort of hierarchical representations. It actually has knowledge structures and causal models of the world. And because of this, it gives them, you know, this allows you to be more robust, learn from small samples. I mean, very compelling arguments. So this could be the, you know, so the idea is that this could be the reason why CNNs cannot learn relationship between objects, but humans do. I mean, we obviously use. So humans' causal model of the world is what enables us to make assumptions about the relations between objects, draw analogies across experiences, and deal with new environments and problems. And at the time, and probably if you've heard this talk before from me, this is what I thought was going on. But things have progressed since then, okay? You know, we really started sort of thinking about, is this really the real thing? Or is there perhaps, one thing that we sort of thought about is, you know, talking to my grad students, is that, you know, these object detectors are very local in their computations. So part of these object detectors, they have these convolutions that do very local computations, and they're not really considering too much sort of relationships across the scene. So basically, what, you know, why can't the CNN at that time learn object relationships and scenes? Well, the first one is what these people are contending, that, you know, that basically object-size relationships require this sort of built-in knowledge structure representations and causal models that the mind has, but CNNs don't have, or machines don't. But the second one is, you know, not as glamorous, but perhaps there's something about these object detectors, some bottlenecks that they do not incorporate spatial relationships. Maybe there's something in the architecture that is limiting what they learn. And if you're an AI, you know that since 2017, things have progressed. There's sort of new architectures that have been developed. And many of these architectures coming from natural language processing. And why? Because in natural, and a lot of these new architectures sort of wanted to emphasize or the fact that they needed to create something that could actually relate spatial elements that were, you know, distributed. So in a sentence, this is critical. If you just do like analysis of like one word at a time, you're not going to get the sentence meaning. So you started having architectures that sort of would actually look at the relationship across elements in a sentence. And perhaps in its newest form is sort of the sort of transformer networks, which actually do this. And then came the visual version, sort of the applied version of transformers. And I'm not going to explain transformers to you because many of you know more about transformers than I do. So I'm a learner. But for those of you that are not familiar, the key point of transformers networks is that they actually break up the image into these little patches, and then there's sort of an encoding stage. And in that encoding stage, it's actually, you're looking at the relationship even across patches that are far away. So it can actually learn relationships of things that happen across the image, different than those object detectors that we tested. So this was a perfect example. When we figured this out, I went to my grad student in EC, Aditya, and I said, okay, let's try these transformer networks. Maybe they will learn or not sort of object size relationship. And we always have Manju not there to keep us straight. So what we did is we just went and we started testing. We created these simpler images where we just changed manually, and this is just one test bed I'm going to show you, where we look at the relationship inside. So you can see that I'm starting to increase the mouse size, and this is just one instance. We have different views, different positions, viewpoints, different arrangements, and what we're looking at is how does an object detector that's trying to find the mouse, does the probability of the detector change as a function of the size? So let me show you a result. This is for the old CNNs. This is one of the busier slides, so we'll see. So here is the probability of detection, the average probability across all those images. What I have in the x-axis is the mouse-laptop area ratio. So as you go here, as you go up in the x-axis, the mouse is getting bigger and bigger relative to the area of the laptop. Now, what is the histogram at the back? We analyzed ImageNet, sort of a data size, a common data set of images, and we looked at the typical object size mouse laptop areas that you find in natural scenes. And those vary, but you can see that here, right there, there's a peak where certainly that's the most typical thing you encounter. Now, if you actually run this is just confirming our stuff. If you run the old object detector, you see its probability, as you increase the size, its probability increases. So it does not, what we should remember, humans would actually start missing things when you actually make the mouse more bigger and bigger and giant. So this is just, and if you use another CNN, you get the same thing. This is just repeating what we saw. We see the failure of these CNNs to really represent object size relationships. So what happens with these transformer networks? Look, suddenly, this is a transformer network that actually learns spatial relationships, and now suddenly we start seeing that the peak probability for detecting the mouse is close to what is the typical relationship between the mouse and the laptop area. And when you start increasing the mouse size so it becomes relatively large, it starts decreasing its probability. Very much the same like humans. I know what you say. If you're thinking about this as, okay, if this is true, what happens if I actually remove the laptop? If I just remove the laptop from the images, and I'm still increasing the size of the mouse, but there is no laptop there as a reference. If I do that, you get this. So this is images, so the effect goes away. The probability drops, and it certainly doesn't peak. So this makes sense. When you have a the network only shows an effect of the size of the mouse when the laptop is present. When the laptop is absent, the effect of size is very, very different. So this is telling you that the transformer network is actually learning the relationships between objects' sizes, okay? Very much like humans. So what does this tell us? We need to go back to the scoreboard. So, and I have here back to the scoreboard, that's VAR. VAR, nobody knows? Okay, if you want to get one thing about this talk, the World Cup is coming up. Get informed about VAR, okay? You need to know what VAR is. VAR is when you review a goal to see if it's actually with video. It's a video review, so it's important World Cup stuff. Okay, so I'd say 1-1 instead of 1-0, because here things have progressed, and this sort of, these transformer networks, a new architecture of deep neural networks are actually now manifesting sort of the behavior that humans have. They are taking into consideration, they're sensitive to object relationships. Okay, and I have there, those that are old enough, I have this little thing as a reference, because it's in a small way sort of a Kasparov moment, oh yeah, chess, nobody ever is going to beat the champion of chess, no machine. And eventually those that are old enough remember that day in 1997. And this is the same thing in a small scale. We thought that these object relationships were something unique to humans that might not be learned at all by machines. But really, if we actually played with the architecture and we got these new networks, we actually can get there. And we can actually get sort of networks that have similar capabilities as humans. Okay, so that's the first one and the most arduous of all. We'll go to the second one. Second example. So what is the score, I guess? 1-1. We're at 1-1. The second example is a little bit, it's a little bit more, a little different, a little bit more abstract. When you look around and you do this every day, and somebody turns their head somewhere, or two people turn their head somewhere, you immediately turn your head and make eye movements towards where somebody is looking at. I mean, this is, This is something that is sort of, important part of actually trying to make inferences about where somebody's attending, what their intentions are, interactions, and so on. So what you're doing is your brain is somehow estimating gaze where somebody's looking at, and then you're inferring that and making an eye movement where you think that person is actually looking at. So what we're going to do now, and I'm going to show you the result, is we're going to compare a CNN that's trying to estimate gaze from a video, and we're going to compare it. Now this is going to be tricky. We're going to compare it to the actual eye movements. So let's just suppose William turns their head there. I move my eyes. And what I'm going to do, we're going to have people do that in a lab, follow people's gaze, and we're going to measure using an infrared video eye tracker how their eyes move, the observer. And we're going to compare the CNN estimate of where William or that person is looking at with the human observer's eyes, how they move, and try to see how they compare and how much information they have. So you might think, well, this is sort of a dumb question to ask. A sensible thing to do is if William moves their head, if I'm looking at William and William moves his head, I just wait until William finishes moving their head. And then once he finishes moving his head stops, then I just make an eye movement toward. That seems like a reasonable thing. Of course, your brain doesn't do that. Your brain starts moving way before William's head stops, okay? And I'll show you what's going on. See if this video works. Hopefully it does. Okay, so what do we have here? You see that little white dot? That's somebody looking at the video and where they're actually looking at. And you start looking at the gazer. We tell them, start looking at this person and then just, follow, see where they're looking at. That's the only instruction that we give. And this little orange arrow is our CNN prediction. It's basically a machine prediction, a CNN of where we think this gazer is looking at. So we're going to compare how the white dot and how this vector progress through time. Let's see. Okay, I'm going to try to control it. I don't fully see. Okay, let's see if I can actually. I might have to get out. Okay, there we go. Oh, sort of. I might have to get out of. Wanted to control it frame by frame, but we'll see. I'm going to do it like here. Okay. Is it? Oh, interesting. Okay, so it doesn't want to. If not in slide mode, it won't. Okay, so what, I'm going to play it, and it's going to play. I can't slow it down apparently, but what you're going to see is that the white dot is going to move while the vector is still pointing here. That means that when you start moving your eyes, the gazer is not looking at the head of the person. They're still about here. So at the time when your eyes start moving, the CNN does not have full information of where this person is going to be looking at. And I'm gonna show you a picture that actually. So look at, there you go, and then so the dot moved when the dot started moving towards there. The CNN was pointing this way. What does that mean? The CNN is mostly using the head direction to make its estimate. Where does the head point? Your brain uses that, but it also uses a lot of more information. It has perhaps Judea Pearl and is right. You actually have a representation of the rest of the scene. Sorry, yeah. I tend to move. I tend to walk. So what your brain does is you're using the head direction, but you also understand what's in the periphery, and you have an estimate what are likely goals. What are the likely goals? I mean, people look at people, and so that's one thing. That people don't tend to look at the sky often unless there's something, but most of the times. So what happens is when the head is actually moving, before the head stops, your brain is already committing to go somewhere to a likely goal. CNN is just using the head. It's not using any of this other information to make an inference about what is a likely goal. And yeah, apparently your brain doesn't wait for the head to stop. It just starts going. So what I'm showing here is actually many people So what you see in green is the eye movement, and what you see in orange is where the CNN predicts that this person is, the gazer is looking at the time where the person starts a saccade. Why do we have various lines? These are different people. I measured this in many people, and different people will start their eye movement at different times. If you see if you see the two people here, there are two vectors, two orange vectors that are actually going downwards. That corresponds to two people that probably started an eye movement very early on while the head was still looking down. So what this is telling you is that your brain is anticipating the CNN prediction, and it's something in the order of 200 to 300 milliseconds. And because it's using way more information. And you say, well, this is obvious because, you know, there's a person there. But even if there's no person there, you get a similar result. If I tell people to watch a video where this person is looking at and there is no person there, people still make an eye movement before the CNN prediction gets to that point. So again, your brain is anticipating basically the information that the CNN has, because it's not just using the head, it's using the whole context. Now, we have lots of movies and lots of measurements, and we can collapse that into one polar angle sort of display, where this is where the target that the people looked at was, and this shows the eye movements, and this is the CNN. And this is just showing you that, again, the CNN, at the time in which you actually the human starts the eye movement, has much less information about where the gaze goal is than your brain. Okay, so when we saw this, we said, okay, this confirms what we had before. CNNs are not learning about spatial relationships. Let's try transformers. Are transformers going to do the same? Is it going to bring it now to where humans are, and it's going to have the capabilities, because it has the capability to actually learn about relationships across the scene. And what happened is, we worked on this very, 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 very hard, and I'm disappointed that we have not got it to work. So this is our transformer result. You know, this is in a psych and brain science lab. So, you know, we might get, you know, and we might now get tips from Manjunat and William, and we see we can get it. But right now, our transformer networks are still not getting as much information as humans from these scenes to estimate gaze. So this, I think, is clear. The scoreboard is 2-1 for now. Okay? So that's the second one. Third example, I think it's the most fun. I think you'll have the most fun. It's not really my field. This started with a collaboration with people at UCI. Mark Stivers and Alex Bowers, and Nicole Hahn also is involved, who just recently graduated like a week and a half ago from UCSB. And this has to do, this is not going to be vision, this is going to be about the ability of humans and AI to make inferences about somebody else's knowledge. Okay, and that is an instance of theory of mind. What is theory of mind? Theory of mind is this sort of ability humans have to make inferences about other people's mental states, their intentions, their future actions. And under that umbrella is sort of a little bit more specialized, whether this person is knowledgeable or not. That is an instance of a sort of theory of mind. It's the bread and butter of what humans are, you know, starting with sort of babies. And of course, it's something that will become critical, sort of holy grail for AI, as AI, the next generation AI comes into play, and actually we wanted to interact with humans. So we're gonna really test humans and AI in their ability to infer somebody else's knowledge. I'm gonna give you an example. You go to a party, and you're just talking to people in a barbecue, and then this person comes, and they present themselves as a specialist in machine learning and finances. But you know, most of you are in machine learning, most of you are in engineering, CS, you know about machine learning. So within 10 minutes, you know, this person, oh, they know what they're doing. Oh, you know, they are out of their, you know, they're just talking. Okay, that's an easy one, easy example. Second example, you meet somebody that is an expert in medieval music. I know some of you have a secret hobby of medieval music, but I doubt most of you. That will be a little bit harder to judge. You know, you're like, yeah. Or you get like, you know, somebody that's crypto. You can run a lot of people are experts in crypto. Is this somebody who's knowledgeable? Are they really talking? Okay, that is the task, folks. And you have to judge oftentimes on things that you're not expert. Okay, so how did the experiment go? This is the experiment. you as the observer and the AI get these images. So and then you get, we asked two people, we call them informants, to describe the scenes. So let's see, the one on the left, clocks melting, horse melting. Expert? Doesn't really give me a well. And then below, a Salvador Dali painting with dripping clocks. Oh, that seems to be a little bit, give me a little bit more information. 5 red, what? Nude persons dancing in a circle. Picasso people dancing in harmony. Oh, that's a tough one. And so on. So now, what is your task? So you can get 3 of these images, you can get 12 of these images with the descriptions. You need to decide who is more knowledgeable, A or B. Okay? And then how do we know who's more knowledgeable? We get informant A and B to take quizzes afterwards with 30 questions on art. So we have a gold standard. We know who's more expert, and we can rate your ability to evaluate who's more excellent, and the AI. And of course, this is just art. You know, who's more of an expert? You could get reality TV, okay? So guys who fix cars on the right. Well, that doesn't seem much of an expert. Cast members for Pawn Stars. I have no idea what Pawn Stars is, but I go with that. So you get the idea. So, and there's 26 different categories, 100 people doing this, making these predictions. And we're gonna use a transformer model to actually also try to make these predictions. So what do you think is, who does better? Well, for now, and this is a transformer network trained in my lab, so I'm sure we could actually improve it. Humans actually have a little bit of an upper hand, but so 69% of the times humans are actually correct in predicting who's the expert. The transformer is actually at 63, so it's not trailing by a whole lot, and it's statistically significant. And here are the 26 categories. We found some interesting things. Apparently, the machines, so the y-axis is the model of the AI evaluation PC, chance is 50%, and in the x-axis is human. So apparently, the model, the AI, is better at Japanese cuisine and reality TV. I don't understand why, but that's interesting. And apparently, it's particularly bad at beauty and health, children's literature, and car parts. Those are significantly worse for the AI. We still don't know why. Okay, so we're gonna just scrap the surface of this topic because we're really just starting, and I'm going to give you a few hints on how machines and humans are actually do this in a different way. But I'm sure you'll have a lot of questions, so come talk to me afterwards. So the first thing that you might think is, how are machines and humans doing this? By the way, the transformer is not training this data at all. It's never seeing this data. It's not that we're leaving part of the data out. It's trained in a totally different data set generated with Wikipedia and other things. So it's never seen this data set. That's important too. So it doesn't have a fair advantage. So are words important? That's the first question we ask. So, and this is like, again, we're starting to do an analysis. So if let's suppose you have an informant A that says, G.I. Joe never missed an episode. Cobra Commander was awesome. I even had the action figures. Number of words, 16. And the other one has 13. So it's just counting the number of words. Is that a key? When there's a bigger difference in number of words, is that something machines and humans use? And here's the data. And it's actually, the correlation is not significant. So there's nothing there, at least for our data set, that tells us that this is actually something important. And I'm going to show you just a few. Are the number of proper nouns important? Right? If you count just proper nouns. So is that what sort of an important source of information to decide who's actually the most knowledgeable? And this also does not reach significance. That's not enough. Okay? What came really, really as significant, and this is a little bit tricky, is sort of the number of details. Now you say, how do we, so here's, I think you'll agree that this is actually, so one is, Guns N' Roses group photo, that's the left. And then Guns N' Roses, they were popular in the 80s. The lead single as Axl Rose. They had hits like November Rain. That's a lot of detail. So now you say, how did we actually quantify this? We actually had hand coders. We sort of instructed what a detail is, a sentence that provides a new thing. So we still haven't automated that, but we can count the number of details. And this indeed was actually something that both, when there was a larger difference between the two informants in number of details that made it the evaluation PC for both the model and the AI both improved dramatically. I know you're thinking, what about number of facts? Right? You just check if somebody's having, if they said here that's, I don't know, Rolling Stones, they're off, right? We wanted to test that, but apparently we did not find enough incorrect facts and descriptions. If people are a little bit unwilling to give incorrect facts, they prefer to be vague. A rock band, a rock band with bandana in their head, instead of saying, Rolling Stones or something else. So we know facts are important, but we don't know to what. It obviously has to do with how many wrong facts there are in the data. So what's the AI versus the verdict thing? I think it's fair to say that we're at halftime for this. So I still don't have all the full answers of which one is actually going to be higher on the scoreboard. I think there are things that humans are using that AI are not, but we're still at halftime. So so let me conclude. What I've told you about is I've really told you about comparisons between sort of AI and humans, and I've sort of tried to give you an idea of how, as the field moves, how my thinking has changed. First, I've shown you how new transformers that incorporate spatial relationships can learn object size relationships like humans, something that we thought before was something special about the mind, but maybe not so. When it comes to gaze estimation, I showed you that AI seems to fall short, at least AI in our hands. We just think we'll figure this out and within a few years with some help from our engineering and computer science friends. And I think the last one is, I showed you how these transformers show promising results in making inference about expertise and knowledge. Another thing that people thought is sort of a landmark of the human mind, but I think we're still, it's up to debate whether that is also unique to human, or we can actually get sort of machines that sort of narrow the gap. So with that, thank you very much.
Miguel, for the wonderful talk. So we have maybe time for one quick question.
I was thinking about the toothbrush, right? There is it's a big toothbrush, even a toothbrush at all. It has toothbrushiness, but is it really a toothbrush for all intents and purposes? And you have an even score now, but what if I see a video of someone picking up a toothbrush and it seems like a toothbrush is 1,000 pounds versus a light toothbrush? I mean, there is a lot of like toothbrushiness aspects that go beyond size. And
yeah, size is just right. It's right. So size is an instant of context, right? And that is, it's sort of like a little mini leap, but like you said, there's a lot of other things. I mean, I could actually just have somebody just rubbing with a piece of stick, and you probably say, that's a toothbrush, because you make an inference that's likely toothbrush. So clearly, humans use all these relationships. The question is, I think with the appropriate training and the appropriate architecture, I'm starting to believe that they could also learn these things too. It's just that some of the data that they are trained on and the architectures were not right, and the trainer are actually impoverished compared to what humans are actually trained on, which is, these, a moving world in which they act on, and, they see, so on, but yeah.
Okay, great. We're running out of time, so if you have additional questions, feel free to catch Miguel throughout the day or during lunch, and let's thank Miguel for the wonderful presentation. Next, I would like to introduce the session chair for next session, Professor Manoush Alizadeh, who is Associate Professor of ECE, and Manoush will help us monitor the AI ML Foundation session. Welcome, Manoush.
Thanks. Thank you, William. Thank you for the great keynote. I enjoyed it. Our first speaker is Sui Tang, Assistant Professor of Mathematics.
Okay, yeah. So shall we start? Oh, okay. Thanks for introduction, and thanks organizers for such a wonderful event. Today I will speak about a bridge interacting particle systems with data science via machine learning. Okay, so first of all, what are interacting particle systems? They are very common in our daily life, as shown in the following examples. And the particles can refer to the planets and the animals and the people's opinions. And they are grouped into, for example, different species and intact. And you can see in various examples and the individual interactions between particles can yield a wide variety of different like pattern formations. And these phenomena are called self-organization. So understanding the link between the individual interaction rule and the global scale pattern formation is one of the most important and fundamental problems in various disciplines. And while modeling the interacting particle systems by differential equations play an important role in this kind of task. However, this is typically very difficult problem to tackle, and it could be a Nobel Prize problem. So last year, 3 scientists are awarded for a Nobel Prize in physics for their groundbreaking contributions to the physical modeling of complex systems and explain the pattern formations. So in the past, like finding an effective modeling for complex systems are very, very difficult, and you rely heavily on the domain scientists' knowledge and creativity. So now in the era of data science, the machine learning algorithms actually have revolutionized our daily life by their very impressive power of extracting information from data. So we wonder, could we actually leverage the machine learning and to help us to do data-driven modeling in the complex systems? So unfortunately, this also could be very difficult in general. So I will explain the reason from the data perspective. Okay, so let us consider the statistical estimation and learning for ODEs. Suppose we observe a flock of birds, like saying they follow a first order ODEs as shown here. So here the governing equations can be represented as x dot equal to fxt. So this x actually represent the positions of our birds, and x dot are their velocities. And this f is a function defined on RD, describes their function relationship between the position and the velocities. And suppose that we can observe the same flock of birds every day at a certain time window, say 0 to capital T, and we can record their positions and velocities. And here this m denotes the day that we observe the birds. So in this way, actually, we can collect a set of positions and the velocities. And given the data, now the objective is trying to find an algorithm to construct f hat that is close to the ground truth f. And how difficult this problem could be. Actually, this is a well-studied problem in the supervised learnings called the non-parametric regression theory. So suppose like we have a function like f defined on the RD, and we have the IID noisy samples of the function. And you can see from the theory here, if we only know very mild information of the function, for example, we know it has certain smoothness, so this alpha is a smoothness constant, then the best attainable rate is n to the negative alpha over 2 alpha plus capital D. So what does this mean? This n is the number of sample size, and this rate is kind of min-max optimal in the sense that no matter what algorithm you use, there will always exist a function f whose estimator converge to the ground truth no faster than this rate. So you can see that this dimension capital D appearing in the denominator of here, this is called the curse of dimensionality. So to get an idea about this rate, so for example, we choose alpha equal to 1, so f is a Lipschitz function, and the capital T equal to 10. So achieve the accuracy 0.1, we need 10 to the 12 samples. Now to mention this capital D can be like 100, even 1,000. So this is going to be very computation intensive and infeasible. And especially in the dynamic system setting, we may have very complicated dependence in the data. So this also causes a huge difficulty. So in summary, so data-driven learning of this function f from scratch is very, very difficult in general and cursed by dimensionality. So what is the solution to tackle this kind of problem? So in this talk, actually, we'll consider a family of the ODE models for interacting particle systems with no dimensional interactions. So here, let me introduce the equation here. So we have like m particles, like saying x1 to xn. So they are like vectors in the Euclidean space RD, and they they belong to the K species, and they're interacting according to the following abstract model of ODEs. And here, so actually this mi here. So let me see I can use pointer here. Oh, if I okay, so this mi is the mass of the particle, and x at dot is acceleration. And this cosine I is the response variable of the agent I to the environment, and typically is simple, like it's a scalar variable. So you can see from here, the form of the governing equations actually is derived from the Newton's second law. So here, this capital F is the friction force, and the remaining part are the interaction force. And so this is a equation for the single particle, or have m particles of it. And so the whole dimension for the system is 2md plus capital N. So what's special about this kind of ODE models? Even though they are like lying in the high dimensional space, however, their interactions are actually low dimensional. So here you can see that these interactions, here we use phi, efficacy to denote different types of interactions, and they are dependent on so-called feature variables. So this Ri prime is a pairwise distance between a pair of particles, and these feature variables could be very low dimensional. So you can see here, like this is a very abstract model, but actually we collect the very widely used model from the physics and the social science and the biology and ecology. They are all specific instances of this abstract model, and here we summarize in the following table. So you can see here the black box means the presence of the atoms for those systems. And I would like to draw the attention to the last two columns of the table. So you can see here this quantity V is actually the intrinsic dimension of these interaction variables. So in most cases, it's 1. This means that the interaction only depends on pairwise distance. And so now the concern is that does the simple interaction really yield very complicated pattern formations? In other words, is this kind of like ODEs too simple to produce like enough like patterns we have in the real world? The answer is yes, actually. So here we show 4 different examples. You can see that all of the systems, they share the same form of governing equations, but by choosing certain interactions, they can display a wider range of different collective behaviors. And in the past, the difficulty lies in the selection of the right interaction kernels to produce the behavior. So this is a forward problem. So what we are interested in saying, like we now, given this data, can we devise some data-driven methods to learn these interaction kernels from the data? So you can see that here in the inch panel, the left-hand side is a simulation that we know the ground truth model. On the right-hand side is that we devise some data-driven methods to learn this model from data from a very small set of data. You can see in all cases, we get a very accurate prediction. So okay, so now how to formulate this data to model problem? So actually our starting point is very, very simple case. So suppose like now we have the M particles like in RD, and they evolve according to a very simple first order system like shown here. So you can see that this is still a system defined on Dn. However, the interactions are very simple, like dependent on pairwise distance. And we formulate the problem in a rigorous way by making connections with non-parametric regression in supervised learning. So assume that we actually only know a very mild information about this interaction phi, like saying we only know that they are kind of smooth function. And the training data here, we assume that it have some randomness. So we collect data from M independent trajectories. Now given the data, the only problem is that how we derive a accurate estimator from the finite data, like here this M typically is finite, and to have an understanding about the system, and also using this estimator to make future prediction and simulations on large time interval, and hopefully we can predict the pattern formation. So this is our like learning problem. Okay, so what is our learning approach? And our investigation starts very simple algorithm, and we call the least square gradient matching. So here is a visualization of training data. So to approximate the phi, actually we want to expand it using a very simple function. Here is an example of piecewise constant function. And the idea is that we want to find a simple function like such that it can reproduce the training data, the training velocity data. So here, as here. So to do this, we construct an empirical quadratic risk functional here. So this is kind of compute the L2 discrepancy between the true velocity data here and also the data generated by a candidate function psi. And we minimize this risk functional over very simple function space. And because here we know this function is 1D, so we can choose the function space as simple as piecewise polynomial. If you go to high dimensional space, of course, you can use neural networks. And also notice that here we do implicit regularization because we have finite data, so we can choose the function space of suitable complexity adaptive to the data size. And then we obtain this estimator. So how does this nonlinear approach work? So I will show it how it works on the 1D opinion dynamics, and we have seen that actually it works very well in the previous slides. And here is a very like a prototype system in social science is opinion dynamics. So it's a 10-dimensional dynamic system. So each opinion is represented by a scalar like x1 to x10, and we take an initial condition generated from some uniform distribution. And so we use the piecewise constant basis to approximate the ground truth, the kernel. And on the left-hand side, this is a visualization of our training data. So each blue line represents the evolution of one opinion, and we have 10 of them. So you can see we collect data from very tiny interval and define on 0 to 0.5. And you can see in each like trio, the opinions didn't form any pattern formation yet. So by throwing the data into our nonlinear approach, so this is the result we get. So this phi hat is our estimator. You can see by taking the data from 16 trajectories, we already get pretty accurate estimation. And of course, we increase the data and also increase the size of hypothesis function space, and we can get more and more accurate results. You can see some convergence going on here. Okay, then we can use the estimator phi hat, plug in back to the original dynamic system, and we can do prediction on the futures and also do simulations on the totally new data sets. You can see that even the estimator learned from the 16 trajectories can give us very accurate prediction and predict the clustering phenomenon of these opinions. Okay, so then if the algorithm works, the next step is that how to do rigorous approximation. So this is an important question addressed not to theory people, also to practitioners. And so in the context of rigorous approximation, so how do we characterize the relationship between the fitting database and the accuracy of the predicted results? And how do we give global accuracy guarantees? And more importantly, we want to solve this inverse problem. Like what fitting database do we need to predict a given property? So get back to our problem. And so here we have this capital X dot equal to F phi. So this is a high dimensional dynamic system with 1D latent radial interaction. So we can, mathematically, we can view this F as a linear operator. And in the given problem setting, because we know samples of X dot, so it is still a linear inverse problem. And also, this physics structure of this system actually make this form of F, make it a dynamic additive regression problem. So this have many connections with some additive regression model in statistics. And then the core questions to address is that the identifiability for an inverse problem. So when this operator is bounded and injective and has a bounded inverse, and also we are concerned about non-parametric learning. So we want to find out the effective sample size and the sample complexity. So these questions are very important to address as the function space will give us meaningful evaluation metric to measure the accuracy of the estimators. And the consistency result actually tell us the estimator learned from finite data is reliable. As we have more and more data, and the estimator will converge to the ground truth. And more importantly, we want to solve the optimal rate of convergence. Like given epsilon, like how many data do we need, and given the data, how we choose appropriate hypothesis space to approximate to minimize the prediction error on the future data sets. And So this has a lot of connection with the machine learning theory. And in the context of interacting particle system, when the data goes to infinite, and there are various limits to consider here. For example, here, the number of particles go to infinity, and the number of trajectories we have go to infinity, and the observation time goes to infinity. For different limits, and we have distinct interactions with the machine learning theory, and also the statistic property of the dynamic system. Okay, below I will give an example theory of this kind of convergence results. And of course, I skip many technical details and and it's rather informal. So here, for this kind of like abstract ODE model, so we prove the theorem here. So this mu(y) is the initial condition. So we actually conclude that a structured sum, like I denoted by phi hat EA, can converge in a suitable L2 space defined by a measure. So this measure is an intrinsic measure to the dynamic system, can converge at a near min-max optimal rate. And so here this rate S is a regularity, and the V is the intrinsic dimension of this interactions. And we view this M as a sample size. And what's like good benefits about this convergence? As long as this structure sum is very small, then the approximation error of the whole right-hand side function on the high dimension space is controlled by this error. So in other words, learning the whole right-hand side of function space is kind of data efficient because it only depends on the intrinsic dimension of the system. And here also, we would like to recall in many like well-accepted model here, so this intrinsic dimension is very, very small. So this actually supports our theory, like empirical findings, why this high-dimensional dynamic system can be learned from a small set of training data. Okay, finally, I want to present a real data application to support the practical applicabilities of these models. So this is like a real data sets. Actually, that contains 124 fishes swimming in a shallow tank. So we can view it as a 2D system. You can see that they actually display a meaning pattern. And what we want to do is fit the data into the model we proposed. So we use a very small amount of training data. So we only use 2 snapshots. So we want to use a model to reproduce the whole trajectory data sets. And here our model has some advantage because you can see that this data is translation invariant and rotation invariant. And our model, if it depends on pairwise distance, is also translation invariant and rotation invariant. So we actually know that many models with distinct form can reproduce this meaning pattern. So what we did is that we use a Bayesian machine learning methodology called Gaussian process to do a scalable model selection. So you can see this is a visualization of trajectories, and this is the results. And we compare with the sparse regression approach and the neural networks. You can see we can do a pretty accurate estimation of the trajectories. And more interestingly, how to compare the patterns, the meaning patterns. And so we use some like so-called group polarization parameters to compare the similarity of the meaning patterns. So you can see from these results, our method actually outperform other methods by preserving the essential physics in these data sets. Okay, so now let me summarize my talk. So in this talk, actually, we can see that the machine learning algorithm have great potential applications in interacting particle systems. And I have presented the work for the deterministic system. And now I want to comment that there are also emerging work of doing this for stochastic systems and also the PDEs. And also, this is a machine learning for interacting particle system. I also want to mention that there is some emerging work for interacting particle system for machine learning, because such kind of model has a gradient flow structure, and also it can produce very rich pattern formation. And also, they have well-studied qualitative theory to prove the asymptotic behavioral solutions. So they can be they find various applications in dealing with the sampling, the high-dimension sampling problem in machine learning, and understanding the optimization of neural networks and doing dimension reduction via t-SNE algorithm. So in the future, it's interesting to explore both directions. So that's all my talk, and thank you for your attention.
much. Let's remember our questions for the end of the session, as William mentioned. If you want to write them down, that would help. Our next speaker is Professor Ruming Hu from the Department of Statistics and Applied Probability. Do you want to present there or here? Okay. Oh, and also in mathematics. The program said that. Thank you so much.
Am I using this one or this one?
Whichever you prefer, if you want to.
Hello?
But also, I'll give you a 2-minute.
Oh, thank you. Thank you for the nice introduction, and also thank you for the invitation. I'm very happy to participating in this today's summit. So our session is called Machine Learning Foundation. It's a very big topic. And from my perspective, I'm going to talk about its connection with stochastic control problems and games. Okay, so let me start with 2 examples in my field. The first one, optimal investment. So imagine that you have some extra money. You want to invest in the financial markets, buying some stocks, derivatives options, or even bonds, and then how to diversify your portfolio or how to maximize your return. This is one of the most important problems that the Wall Street people concerns. Okay, it's also related to ourselves. Just to imagine like your retirement plan. Okay, so but I'm not going to talk about how to make investment today, but I'm going to explain why machine learning is important in those problems. Okay. So here are the key components for the modeling. Stock price. So we usually use stochastic differential equations for modeling stock prices. The most famous one is called the Black-Scholes model. So for SDEs, the stochastic differential equation, you can think about those as differential equations plus some noisy terms. Try to characterize the random fluctuations in the financial market. Agents, the second component. So those are like the investors who make decisions wisely how to optimally allocate their monies into different assets. Okay, and the problem can be formalized either by a mean variance problem. That means you want to maximize your returns and minimize your risk, or if you know exactly your utility function, how happy you are if you are receiving some money, then you can also formulate it as a expected utility problem of your terminal balance. Okay, and then depending on the problem that the scale of the problem that you're analyzing, we can either formulate the whole thing as a stochastic control problem in a random environment, if you are like working with your retirement plan, or by a stochastic differential games, if you are like one of the founding managers and your bonus will depend on the relative performance of comparing to your peers. So it's very common that for founding managers, your bonus really not only depends on the absolute value of your pool, but also on how much you outperform your peers. Okay, and if you are analyzing how to trade optimally, how to invest optimally with a price impact, which means the price are usually determined by everybody that are trading in the market as an equilibrium from everyone's decision in the market, then we use a midfield game. So midfield game is a game where you have infinitely many players and they are making decisions wisely in the same environment. Okay, cool. So then with all those factors, we can have many assets, we can have many agents. The problem is definitely a high-dimensional one. So that's why machine learning techniques come and play an important role here. Okay, the second example. So epidemic control. COVID, masks, or social distancing, or vaccinations. We have been hearing all those words many times in the past 2 years, right? And for a decision maker or social planner or region planners, it's important or very crucial for them to make wise decisions. How restrictive the policies are, or how much effort they are going to input for slow down the epidemic. Okay. And this picture have like 3 levels of models for epidemic control. So the first one is a very standard a compartment model in epidemiology. Let me see if this is working. Okay, maybe I'm going to use the mouse. So the panel A is a very standard model. So it described the population dynamics under a infectious disease. So how the population are susceptible population become exposed to the disease and then get infectious and then be recovered or dead afterwards. Okay, and on top of it, we can add controls to the models. So how much effort we are going to do? We are going to invest in developing vaccinations or distributing vaccinations, and how restrictive we are going to issue the lockdown policy, mask policies, and those will definitely slow down the pandemic, but will also harm the economy. So what's the trade-off here? So what is the optimal decision by the policymaker? Okay, and the panel C is a more realistic situation where multiple regions are making decisions simultaneously. Okay, so in the United States, we have like 58 states, and each state's governor will issue their own policies, and they are not necessarily the same. So for example, someone suggests that injecting bleach will be helpful, but of course, some states do not believe in that. Okay, and one state's policy will definitely, in fact, is neighboring situation. So there are travels between the states, and then they are sharing the medical resources. So all I want to say here is that for determining like optimal policies for mitigating a epidemic or epidemic, then it still involves many decision makers in this problem, and it's very high dimension. Okay, so for these two problems, we have seen that there are many factors or many components that are affecting our decisions. For example, in the first scenario, that's the number of the assets we are investing in. There's number of the agents that are playing the game. In the second example, there are the number of the regions or number of the compartments in the epidemic model. Okay. And we have been having machine learning for many years, so we all know that the challenge here, which is the curse of dimensionality, if we want to solve those problems numerically, for example. Okay. And in our community, in the community of applied mathematics and applied probability, there are mainly two approaches. The deterministic ones, there are two famous machine learning methods. One is the PIN, the physics-informed neural network, and the other one is called deep galaxy method. They are basically the same. They try to solve the partial differential equations, basically. And the other approach is probabilistic. So that involves Monte Carlo simulation. You have to draw some random variables from certain distribution. And the first one, it's a pioneer work proposed by Wei Nan E's group. This is called the deep BSD. And this is also the work that motivated me to work machine learning into stochastic control and the games. And my first work is also listed here. This is called deep fictitious play, where I combine a learning scheme from economics that's called fictitious play and deep learning together. And then we use it to solve games in high dimensions with many agents. I also want to mention that there's another very important algorithm, which is called deep backward dynamic programming. They share a similar spirit as the deep BSD. It's also very widely applied in our community, although I haven't used it personally. So the main idea of these two approaches are the following. So you use some neural nets, try to parameterize the quantity of your interest, and then you try to define a proper loss function such that when you minimize the loss function, this leads to the solution that you wanna identify. And how to minimize the loss function, how to identify those parameters for the networks by the gradient descent or some variant of those algorithms. Okay. And meanwhile, the theory part is also very important, and those are a sample of questions that people in our field has answered or are trying to answer. The first question, a very fundamental one is, are the neural network functions or are the maps, are the relations parameterized by neural network rich enough? So this is the answer to this question is usually called the universal approximation theory. And the first results date back to 1990 by Hornick. Okay. Other important questions are, for example, in theory, can the training loss that we define to be sufficiently small? And usually the answer is yes, if the size of the neural network are large enough, and then the solution of either our deterministic system or stochastic system are smooth enough. It has many derivatives, the solutions are smooth. Okay? And then in practice, can we really achieve those corresponding neural nets? So the answer is depends. Usually the problem, the maximization problem is highly non-convex, so there's no theoretical guarantee you can go to the global maximum or minimum. You will most likely you will be reaching a stationary point or a local minimum. Okay. And at the end, what does it mean if the training errors are small? Does it really mean we are finding the true solution? The answer is yes, usually under some appropriate conditions, like the smoothness of the true solution. Okay? And for different approaches, the deterministic ones or the stochastic ones, we rely on different type of analysis. And the first one is the PD analysis, and the second one is stochastic analysis. We have some like bounds on expectations or improbabilities. Okay, and my research has in machine learning we deal with both approaches. Okay, and those are the questions I usually use in my research. The first half corresponding to the deterministic approach, and we do dynamic programming. We can obtain some highly nonlinear and high-dimensional partial differential equations. So here G is just an abstract nonlinear operator which takes value of the first derivative of V and also the Hessian matrix, the second derivative matrix of the V. So V is usually some value functions that you are interested in. It could be like one dimension or high dimension. The most difficult part is usually the X here, the spatial variable is high dimension. So when you are taking the second derivative, you will have a high dimension large matrix that involves in the equation. And the second set of equations, we call them to be forward-backward stochastic differential equations, and this usually derived by the punctual eigenmaximum principle. I want to comment that even in the low-dimensional case, the system is not easy to be solved numerically, because you can see for one of the equations, for this X, is running forwardly, it has a initial condition, and for the second one, it's running backwardly, it has a terminal condition. So with these two contradicting directions, usually the numerical algorithms are hard to develop. Okay. So my research in machine learning can be categorized into like three directions. The first one is we are, with my colleagues and my students, we are interested in develop machine learning algorithms and theories for stochastic games, controls, and also mean-field games. For theory, I mean, I am trying to answer the question that was raised in the previous slides. So how to define those proper loss functions? Can they be small? And if they are small, are the solutions really close to the truth? Okay, and the first one, on the stochastic differential games is my single author paper. Is combined again the feature display to deep learning, and we are trying to figure out the Nash equilibrium for high dimensional games. So Nash equilibrium means a set of strategies from everyone in this game such that no one has the incentive to deviate. So it's like an equilibrium strategy. Okay. And when there are many players in a game and they are making decisions in a common environment, in the same environment, then we model this by mean-field games with some common noise. And there, with a student, we to obtain the equilibrium in mean-field games, we combine the rough path theory and feature display and also deep learning to make it work. So that's a infinite dimensional problem, actually. Okay. And then the second direction, we are working with apply things to real applications, and I want to highlight this is the article we wrote by invitation to the notice of the AMS. It's very reader-friendly, targeting on junior PhD students. Okay, so the third part is on the theory of deep learning. So in this direction, we are interested in one example here is we are interested in the convergence of the convergence speed of the empirical measures to a true distribution. And I think this is very important. For example, if you want to learn a distribution from observed data, you want to know how much data are necessary in order to recover close enough to the true distribution? And does it suffer the curse of dimensionality? So is the dimensionality of the data play a role in the convergence? So in our work, we design a class of probability metrics which give the convergence to be free of dimension. And we think this gives the explanation why the Wasserstein again performs great in the high dimensional problems. So we know that for the Wasserstein again, the discriminator is defined using the one Wasserstein distance, right? So they compare for two distributions, they compare the supremum of the difference when they are integrating with respect to some testing function in the one Lipschitz function class. But in practice, the implementations are using neural networks to approximate the one Lipschitz function. And mathematically, they are called the Barron functions or generalized Barron functions. So by their nature, we realize that this class is actually not rich enough to to feel the curse of dimensionality when they are measuring the the convergence of empirical convergence. Okay, so we think this is a very interesting explanation for the GAN. Okay, of course there are other directions. So for all the past I've talked about, it's mainly how to apply machine learning techniques and stochastic analysis to stochastic control and games problems. And other directions are also interesting in our field are, for example, how to learn and generate data using machine learning. So not only try to extract the governing equations from the observed data, but also how to develop generative models to incorporate with control theory that leads to the neural SDs or the neural CDs, the neural control differential equations. So that also combined with the rough path theory, basically. And the other connection is how to use the control and game theory to analyze the machine learning algorithms. For example, people use the stochastic differential equations to approximate the training of stochastic gradient descent. Okay, and people try to interpret the GANs using mean field games. So a generator, discriminator versus one agent and the mean field, the population distribution. Or if there are many neurons in the network and there are many iterations in the training, then we can also use the mean field theory, not the mean field game, but the mean field particle theory to analyze the output behavior of such a neural network. So those are also very interesting and ongoing work in our community, and I'm personally also very interested in those directions. Okay, so last I want to highlight some of the references that I have done in the past. So the first paper is an original work starting using deep learning into high-dimensional games. And the second one is, I just mentioned, we tackle this infinite-dimensional problem for mean field game with common noise, combining with signature, which is a concept in the rough path theory, and that's done with a student in the P-Stat department. The third one that I just mentioned is a reader-friendly article that how to combine game theory and machine learning, especially deep learning algorithm, to provide some reasonable baseline policy for epidemic controls. And the fourth one is in collaboration with our previous speaker, Sui Tang. We are analyzing the pins performance for primitive equations, which is widely used in fluid dynamics. Okay. And all my work on this area, machine learning in stochastic control and games, they are summarized in this a recent survey paper that I wrote with my colleague Matthew Lauria. And there are also many other references related in the related topic. So that's pretty much I want to say for today. Thanks for the attention and questions.
Thank you, Meng. Our next speaker is Professor Igor Mezik from the Department of Mechanical Engineering.
Can I put it on top?
Yes, yes, please.
And I'll give you 2 minutes.
All right. Hello, everyone. So it is really, let's see. There we go. It's really wonderful to see so much interesting research in machine learning and AI being done at UCSB. The first lecture by Professor Axton was inspiring. I'll actually connect to several elements. I'll talk about Koopman operator theory-based machine learning of dynamical systems. Time is essential here. Let me state that causality is about time. Yes? No? Okay, we can debate at the coffee break. It's an alternative point of view, but a point of view that actually goes after understanding the relations between observables, essentially. And I'll try to detail some of the aspects of this as we go and kind of connect it to the previously mentioned topic. So where does this come from? It's interesting. In 1931, Bernard Koopman and later on von Neumann got interested in this representation of classical mechanics using an operator theoretic approach that was first proposed in quantum mechanics. So it actually comes from our inability to measure things in quantum mechanics. The operator theory was essentially invented to deal with that, to provide a method for dealing with observables that we can observe rather than the ones that we were hoping to observe. So it comes from physics. It was dormant in ergodic theory for a while, and it was classically used to study what is called measure-preserving systems. I think for the mathematicians in the audience, this is going to be meaningful. For everybody else, probably not, but again. For dissipative systems in math literature, you can see this under the name of composition operator. And the elevator pitch here is that the spectral objects associated with a class of linear representations help unravel the state space geometry and enable model reduction and control in high-dimensional systems. That is poor elevator pitch, except outside of, inside a math department. But there are two issues here, or two highlighted things: model reduction and control, that hopefully resonated with everybody. So let's see. The current themes, and that's where it gets a little bit better and a little bit less abstract, is applications in learning and AI. So here are some promises. It enables learning with or without minimal supervision, so self-learning. Control and contextual adaptation are possible. And then learning from small number of samples. And if some of you are looking at the DARPA's third wave AI definitions, right there. I'm going to make some connections. I know a lot of people here and elsewhere are working on deep neural networks as a machine learning aspect of AI, and I'll make some connections to that. But let's state our objectives. So we'd like to, if we have a system, like humans have a system, there is the visual field around us and certain actions that we want to perform. We'd like to compose a model of that system. We'd like to understand what are the uncertainties of the model. We'd like to control it. We'd like to be able to reconstruct and validate from the data. We'd like to be able to predict system behavior, do causality analysis, and do what-if analysis. So these are the general aspects of what we want to learn. So a little bit of mathematics. The observables, and I'll tell you in a moment what they are in various contexts, are labeled as F. M is our general state space. This is a space where things are evolving. The Koopman operator is really just a composition operator for maybe I can do this and move a little bit. For deep learning, interestingly, going from one layer to another also is done by composition. So in deep learning, the time would be this direction. In dynamical systems, the time is the time. So the same composition operator plays an interesting role. So here, anybody recognizes this fellow? It's Kershaw, right? So you're close to LA, so I had to put this up. Probably I should have done a football picture. But let's think briefly about what a high-end pitcher needs to understand when they are actually performing the task. Really, there are two essential, well, several things. The position and the momentum, momenta, because there might be a rotational momentum because I think he's going to spin the ball right now. So really, everything else that's going on under that particular hierarchical level is computation. But the connection between the momenta and the position is essentially what is encoded and what enables him, in this case, to perform this function. So let's say we have an abstract point P over there that actually is the position and the momenta of the picture at time t. And then at some later time at P prime, we'd like to see a catch. That's fully abstract. I didn't associate any numbers with it. There are many numbers associated with it. Famously, Descartes was sitting in his bed and figured out that if you have a fly on the wall, you can describe it by X and Y, right? So we can associate numbers with abstract positions, and that's what Coupon operator theory does. It basically lifts everything up to some function space, and then that djk is a matrix. It's a linear matrix that connects the observables. Now, what can you do with this? This is the American Mathematical Society notices a paper that I published just, I think, a year ago, in which this concept of representation eigenproblem was proposed. And the idea is that this aspect of AI should really be about finding observables that need to be connected in order for the task to be performed. I hope this is clear. So out of many, many different things that a pitcher can observe, it is the positions and the momenta that they somehow need to learn through training are important and somehow connect them. Now, you can actually do that by neural networks. The mathematics is formally this. I'm not going to go into details because this is a 20-minute talk. It will take a little bit longer. But you can actually set up a cost function that says, this is my state at time t plus 1, j plus 1. This is my state at time j. Let me find the observables that are going to optimally predict what the next state is based on the previous state. That's the key idea. The rest of it is, as they say, math. You can get linear representations as well. You can get nonlinear representations. But that's kind of the general perspective. There are several interesting aspects of this approach. One of them is that it recognizes mathematically what are the coarse-grained aspects of the problem and what is the noise. Something that we've had problems with deep neural network in the context of overfitting, right? So there is a formula, this one is in particular mine, that splits the coherent parts. The G star there is actually an average over everything. These things here are things that are also the aspects of the problem that are coherently oscillating in time. Think of people coming in the building and just the building occupancy and the network. We're applying this, for example, in network security. I see Greg in the back. Think of people coming and the network volume just increasing because they're now sending emails, right? That's a coherent part. There is basically a square wave between 9 and 5. Not at UCSB, we are 0.24, so it doesn't work exactly that way. But in a general organization, that's how it works. And that would be encoded in this part. And the Coupon operator naturally knows about the noisy, chaotic part. One of the previous speakers was mentioning complex behavior in dynamical systems that can encode complex behavior. So that's that same representation. Again, right on the top, what we are seeing under element of M is actually the coherent part. And then the part that has an R in it on the right, I minus PM, that is kind of the noise. And so what you're looking at this is a particular oscillator network. What you're looking at from top to the bottom is at the top level, we retained 10 coherent parts and said the rest is noise. And orange is our prediction from that. Blue is the real data. And green is the bounds. And so you see that we don't do very well with 10. Interestingly, although this might seem fantastic, the orange and the blue are very close to each other. We are constantly outside of the confidence bounds. We are overfitting. The good model, because there is noise in the problem, the good model is the one in the middle, and you're seeing this curve kind of optimizing around 40 or 50, right? And dying when I'm taking too many parts as coherent, because I'm encoding noise. So that's one of the aspects of what we can do. For example, rejection of noise is an inherent feature of the approach. We can do control. We could do control instead, so what is a control system? So you have part of the system that is being, that is having its own natural dynamics, and then you have another part of the system that is connected, that is perhaps collecting data from the system it wants to control and pushing some commands through, right? Those commands are labeled as U. X is our original nominal system. The operator approach is very simple. Take X and U as observables, both on the state of the system and the control, and lift that whole thing and find the appropriate observables to observe. So if you're interested in reading a little bit more, there's a whole book on it. It's an edited book, Koopman Operator in Systems and Control, by Alex Moroa and myself and Yoshi Suzuki. But anyhow, even for very, very complex systems like the Lorentz attractor on the left, or I've mentioned some other applications, you actually get controllers that look very simple. Z plus is A, Z plus B, that looks very linear. But remember that I chose some possibly very nonlinear observables in order to get to that simple representation and do things that are very efficient computationally. Now, what is a nice thing is very efficient computationally. You can do control of a fluid flow on your laptop. One of the things that we didn't talk about, and yes, transformers are better than the rest in having correlations, but transformers, according to the last summit that we had here, spend 5 times more energy than regular DNNs. The pitcher, 20 watts, right? 20 watts. So there must be something like this, some aggregation of this sort, some finding of these observables that is encoded somehow in what humans do. And we should go after it in the context. We're sitting in the Institute for Energy Efficiency, so it should be encoded. It should be an aspect that we need to worry about in the context of responsible machine learning. All right. This comes slightly out of the left field, but it did make it to International Conference on Learning Representations. As I pointed out, the deep neural network itself is a dynamical system. So if you think about it, you start with some coefficients, and then you look at the cost, and you do stochastic gradient descent, and then you change the coefficients, yes? So that's a dynamical system. The coefficients are going to dynamically change over time. Every dynamical system has an operator associated with it as its model, and it's called the Koopman operator, the one that we're talking about. So you can actually try and see whether those coherent aspects of the dynamics have something to say about training of neural networks. Interestingly, they do. I'm not going to go into a long description of what these figures mean, but the only thing they should notice is that at the top there on MNISTnet and ResNet, you see 2 curves, right? In blue and red on top of each other. These are curves that describe magnitude pruning under what we call the Koopman magnitude pruning, which is really the pruning based on putting to 0 that G star in the previous equation that I said was the average. Precisely that. So there are 2 different pruning methods. In one, you just take the magnitudes, look at the ones that are very small, put them to 0, and that's it. If you notice, the 2 curves are on top of each other as I compress. Compression goes from 1 to 64. They're on top of each other. So the magnitude pruning, which is the most successful pruning method that we know of, is precisely the Koopman coherent mode pruning. To prove that a little bit more, here is the gradient pruning, which is the next thing that everybody uses. And that is exactly pruning based on the second coherent mode of the Koopman operator. So the point is that the most successful methods in pruning are actually Koopman operator based methods. All right? Okay, and now let's go into games. So this is a large group. You can see Air Force, you can see British Aerospace, you can see Professor Hispania, and so on and so forth. How many of you have played a StarCraft game? All right, many of you. Do you believe that an AI can do a StarCraft game as well as a human? Of course I'm going to show you that that happens, right? Otherwise I wouldn't be having the slides. So as you already know the game, then you know that it's Marines and Roaches and Hydraulics and so on. And the question that we asked is, can you actually balance the game? Because an unbalanced game in which the machine always wins is boring, and then the game in which the player always wins is boring too. So we were asked to see whether we can balance the game. We have learned the Koopman operator from it, and let's see whether my movie is going to work here. That would be sad, because I have a great movie for you at the end. Let's see. This one works. Okay. So anyhow, I'm not going to show you the movie, but they all die at the same time. So they're well balanced. This is a better slide. I mean, so what you're seeing on the horizontal is the Koopman model prediction, and the Koopman model prediction has a relatively small size compared with the whole dynamics of the game, right? All the parameters that you have to take into account. And then on the vertical is the actual, and if it was perfect, it would be all along the diagonal. You had a perfect prediction, and that's why everything worked, right? So the model, the intelligence, actually predicted perfectly. Now, of course, there is noise, there is stochasticity in the whole business, so you're going to be varying around. But as you can see, it does really, really well. I mean, a small Koopman operator-based AI does really, really well. And then I'm going to finish with this example. So this is with Professor Elliot Hoag's group. Soft arm is a cloth-based arm. It has a bunch of pneumatic actuators in there. And the idea is to train it for a short time and then have it follow a stick here, but I'll show you something even more fun in a second. And so, you know, having a constitutive PD model for this kind of thing is hard. I don't know if anybody has tried, but it's not an easy thing to do. So let me run this a little bit. There we go. Hopefully it works. Oh, no. It won't. Really? Let's see if I can do this. There we go. At least I'll show you this one, right? Still have a minute. Did you see it catching a ball? That's a poor representation of a pitcher. But, you know, it does reasonably well. Let's see whether it's gonna, there. I should tell you, so it caught the ball, right, and it had a very clumsy attempt at pitching into a bucket. But the point is, this thing was learning by, let me see if I can still run this for a second here. Could be kind of interesting. It doesn't work, but the way that the thing learned is actually we gave it, oh, there we go. We're giving it literally random inputs. Think of a baby looking at something hanging from the top and just, you know, trying to figure out what their body can do. So we're giving it relatively random inputs to start with. And then I'm afraid to touch this now, but so let's watch this. This actually is sped up. It lasts for about 5 minutes, literally 5 minutes learning of its own operator. So it's designing its own model of the world and itself, right? And now we're going to ask it to follow a stick. That was its first task. This is hello world. And it does reasonably well. If you watch it for a while, it gets a little spooky. If you have dogs. But it obviously learned the model of itself by only learning things like momenta and positions, if you think about it. And so, you know, as Chekhov would say, I introduced something at the beginning of the novel and then ended with that aspect of the novel in artificial intelligence. I'd call this AI, although it's not based on deep learning, but it's up to you to decide. All right, so that's it. Thank you.
Thank you, Igor. Our next speaker is Yushang Wang, the Center Co-Director for CRML.
Okay. All right, everybody. Thanks, Manoush, for the introduction. My name is Yushang Wang. Today, I'm going to tell you a little bit about reinforcement learning, which I'm kind of glad that the entire session is about control and dynamics and systems and interfacing with learning. So I'm going to tell you a bit about the learning perspective of this that's coming out of the machine learning community. Right, can I? Okay, so maybe I should turn this off. All right, like that. Okay. All right, so reinforcement learning is about is a control theoretic problem about an agent interacting with the world and trying to figure out how the world works, and at the same time learning how to do well in this environment by maximizing its, in some sense, cumulative benefits in the long run, right? So you need to take a strategic sequence of actions in order to get you to a state with a high reward, and then like you want to do that completely from scratch by trials and errors. Reinforcement learning is arguably the hottest topic in machine learning nowadays. So just look at the statistics from NeurIPS. So this is a leading conference in machine learning. It is even hotter than deep learning. Oh goodness, you wouldn't imagine this 5 years ago. And part of this is driven by this breakthrough in AI, for instance, in agents learning to solve games like Go better than humans, like beating the world champion in the game of Go, and using this to control robots and so on, learning everything from scratch, including the kind of little cloth robot that Igor showed us just now. But the thing is that most of these applications, even though it's not a very popular area, requires us to have access to some kind of a simulator, right? So it requires us to have unrestricted access to experiments for trials and errors. In real life applications of reinforcement learning, on the other hand, we seldomly have access to such an environment. Explorations by trying out different things is often illegal, unsafe, or sometimes illegal. For instance, if you are trying to train a self-driving car to do well, you have to really drive off the road and brake your car for many, many times before the agent using the standard reinforcement learning algorithm to figure out, right, this is really a bad idea. In practice, reinforcement learning always starts with some kind of offline data set. So this will be some existing systems or humans collecting data, making decisions, and then we log the outcome of those decisions, right? So we often already have this big data set. And the typical setting in practice that we're interested in applying reinforcement learning to is to kickstart the learning process with such an offline data set. And this task is called offline reinforcement learning, and that's going to be the topic of today's my talk. So there are two specific settings, one called offline policy evaluation, which is about, say, the engineer came up with a great new policy for the recommendation system, and he evaluated this on their data set, and the performance is a little bit better. Should we just ship this? Should we just use this for the recommendation in the future, and will it improve the performance? So the question is called offline policy evaluation. The thing is that we're not really deploying this new policy in the real life to test it, but instead we want to rerun the data set that's collected by a different policy and to gauge the performance of this new policy. So you can see that this is kind of a what-if question. It's a counterfactual question. And what if we have developed this new policy from a while ago? And there's a more challenging task for offline reinforcement learning called offline policy learning or policy optimization, in which we just want to use offline data to directly get to the optimal possible choice, optimal possible policies that interact with the world. Okay, and we call this optimal policy pi star, right? So this is obviously a much harder task. and it depends a lot on whether like our already deployed system is able to explore. So let me give you a few examples on why this matters in practice, and if you don't get anything, just understand the practical aspect of why offline reinforcement learning is important, and I've already achieved my goals in today's talk. So in the medical treatment setting, so we typically do not have access to freely assigning drugs to cancer patients, but instead we have doctors choosing different kind of treatment for existing patients. We can take electronic patient records, even like data from wearable devices to somehow make sense of the patient's interaction with a treatment and observe the outcomes, right? So it's more legal to do this, and it's definitely like we shouldn't be wasting our data and then try learning everything from experiments. So OP in this case will be about evaluating a new treatment policy, and offline learning is about learning better treatment directly from the data, without actually running experiments, right? It's kind of a dream that all the drug companies wants to achieve, right? So they no longer need to get the approval from the FDA and so on to test this on human beings. In the self-driving setting, the offline evaluation will be to evaluate self-driving algorithms. So you can't really run this algorithm in practice due to regulations. But of course, you can get humans to drive your autonomous vehicles around and then get the vehicles to collect all the sensor data, right? So that you can see the entire trajectories of state and human driving decision, next state, and then you can measure the safety metrics. And the question is that can we evaluate a particular algorithm using such data, and can we learn safer and more efficient self-driving cars? Okay, I hope these two examples illustrate that the promise of offline reinforcement learning and the idea of how we can learn this from offline data. And there are many other applications in ads, in material discovery, in computer networking, and so on. And we've been doing some of this more applied work in collaboration with my colleagues in material science department, and also in our networking faculty members in CS department. Before I get to the actual research, I wanted to give you a broader view of why reinforcement learning and the decision theoretic treatment to this learning is meaningful and useful, like even more broadly for general machine learning tasks. So take these two examples. For instance, a hospital tries to decide who to screen for infectious disease, and the test is kind of expensive, and the hospitals would like to be more cautious in who to apply the tax, so that we save on the budget, and they decide to use AI, right? So they train a classifier to decide who is more likely to test positive, and then use this to pre-select which patients to send for the test. Right, so they try this out, and on the holdout data set that's not used for training, the accuracy is pretty high. Right, so and way better than their current deployed system in achieving the same goal. Another example is a large tech company wants to improve their like email service, and they basically ask you to type the first part of a sentence, and they complete the second part of the sentence for you. Right, so this is a very useful feature. Like I don't like to type all my emails. What if like the email service can tell me what I should type? Right, it seems to be working great on all the data sets that they tested on. What could possibly go wrong? So these are like experienced engineers, and knowing what they're doing, they're evaluating their systems on test data sets that's not used for training. So following the best practices, but what could possibly go wrong? So I argue that every machine learning problem is arguably a control problem or a reinforcement learning problem for these reasons. So in the first example, if the test patients, if we decide who to test using the new rule, and the population of the people who we test is going to be different. But this classifier is trained on the previous distribution, not the new distribution. How should we trust the classifiers to still do well on this new distribution that is selected by the classifier itself? In the second case, if everybody just taking the suggested sentences that are suggested by the email service, then in the real runtime environment, the performance of the model is going to be really well, right? Because the model is doing the prediction, and then it got accepted. All these other alternative sentences that the user could have written will not be written, right? So is this model really fulfilling its own prophecy? right? So I argue that in all these applications, the ultimate goal of building a supervised learning model for prediction is not for the sake of prediction, but rather to make use of the prediction to interact with the world instead of learning to predict. The systems that we should be having in mind is really to learn to act and learn to intervene and learn to understand the impact of this learning system when it is deployed in practice. And figuring this out is going to be a critical task for responsibly applying machine learning in real-life applications. Okay, I hope these couple of examples convinced you that reinforcement learning and learning to intervene and learning to act is an important problem. And if we are trying to start doing this from the offline data set, and offline reinforcement learning is a very critical problem to address. Okay, so in the remainder of my talk, I'm going to tell you a little bit about my group's research on offline reinforcement learning. And if time permits, I'll also tell you about a new setting called reinforcement learning with low switching cost, which in some sense is somewhere in between offline and online reinforcement learning with various interesting applications. Okay, I'll start with this sentence. So offline RIO is a very challenging task. And to understand why it is challenging, so let me illustrate the fundamental difficulties of this offline learning problem from an example of my two little sons. And on the left, you are seeing my younger son who is 3 years old. His name's Oliver. On the right, you are seeing my older son, Joshua, who is now 6 years old. This is when he's 5. So Oliver, by being 3 years younger than Joshua, is always a little bit jealous of all the fancy things that Joshua does all day long, for which Oliver is too young to play. For instance, Joshua is now into video games and he's playing Super Mario, and Oliver has been watching him play but never really got his hands on the joystick. And the problem of offline reinforcement learning with the task is really, so can Oliver actually learn to play this game as well as any professional player by just observing and watching his brother playing Super Mario for say 100 and maybe 1,000 times? Okay, so you can imagine this might not be an easy task. It's pretty daunting, especially when Joshua is just 6 years old and he's nowhere near the performance of even an amateur player of these Super Mario games. Okay, so but concretely, what is so difficult? Let me parse this a little bit. Let's just imagine that Oliver watched Joshua playing, and now it's his chance to play. And if he decides to do exactly what his brother did, he's never going to be doing anything better than the lousy performance that his brother is obtaining, right? So if he's interested in doing a little bit better and improving over what Joshua is doing, he has to take different actions and choose different trajectories to move forward. But the moment he decides to play things differently, he'll be running into situations where, oh, this is a stage of the game that Joshua never really encountered before. At least the different policies that Oliver decides to take will induce different distributions in the kind of scenarios that you run into, right? So on top, I'm illustrating this an example of Markov decision process where a robot is starting at state 1, state S1, and take an action, and it gets you to state 2, and then you take another action. So this is an example of one trajectory, one data point as a data set of offline reinforcement learning data. But what is more important is all these paths that the agent could have taken but not really taken, right? So the fundamental challenge of offline reinforcement learning is to answer these what-if questions. So what if this alternative path was taken? How likely and what is the reward that the agents would have collected, right? So to address this question, we really need to solve the causal inference question, causal inference problem. The issue is that the problem is even more challenging than the standard causal inference problem, say patients receiving a treatment, and then we want to tell whether this treatment is effective. Instead of one treatment, the agent, we need to evaluate over a sequence of, a very long sequence of strategically chosen actions, right? We need to evaluate over a very long planning horizon. And in addition, there's a very large state space, right? And the distribution of the states that you visit is a function of how you play this game. It's a function of how you play this game, and depending on the policies you take, you induce very different distribution on this state space. So in this Super Mario game, every pixel could have taken a different value, right? So there is an astronomical large number of states if you're just representing it using the picture that you observe, right? Like this is how DeepMind solves the problem, right? So with by just having the computer looking at the pictures in these Atari games and choose those as the actual state. The next thing is that like Joshua is only like an amateur player and he's not really exploring all aspects of the state, right? So he might be trying a thing or two, but it's impossible for Joshua to end up visiting all possible states, right? Let alone like behaving the same as what the optimal player would have done, right? In addition to that, even if like Joshua is able to do well and visit various states and have good coverage, and the number of times, and in cases when there is uncertainty, right, the number of times that he ends up visiting different states can be very different, and which means that you have to somehow harness this uncertainty and make sure that when you optimize over your strategies, right, so this is a problem that's specific to reinforcement learning, you need to optimize over a large family of strategies rather than in causal inference, you have this one thing to evaluate. So in the past couple of years, we've been building solutions to these challenges in my lab. So we've been trying to come up with algorithms that tackle these challenges one by one, and we've been like coming up with good algorithm, and at the same time trying to understand the information theoretic complexity of solving these problems. How well can any algorithm do, and how well does the algorithm that we propose compete with any algorithm in the entire world, right? So we came up with a few solutions. So let me very quickly parse it for you. So the first solution is called marginalized importance sampling. So importance sampling is a standard technique that the econometricians use to reweight your observations so that you can do this counterfactual reasoning. So what happens in this case is that we have a very long planning horizon, and if we follow the textbook importance weighting procedure by weighting according to the trajectories, there will be a bunch of important weights that got multiplied together, which end up leading to exponential blow up on the variance. So this is called a curse of horizon. And what we propose is that we can actually directly estimate the induced state visitation probabilities for the target policy as well, and use this to reweight our observation. And this ends up giving us the information theoretically optimal bound for learning the optimal policy. With one catch, right? So Joshua needs to have a non-trivial probability of visiting all possible state action pairs. Okay, so how do we solve that? So we use what we call a functional approximation. And functional approximation allows us to transfer knowledge from one state to another state. So even if we never really see the state on the right-hand side with a green mushroom, but in one of the Joshua's games, and Joshua realized eating this red mushroom is good for the agent. So maybe Oliver will end up learning, like using a feature-based representation, that this green mushroom has some similarity to the red mushroom, and maybe it is good for me too. Okay, so that's on the high level how functional approximation works. And you can obviously use neural networks for functional approximation. And the last thing is, how do we handle those cases when the data coverage is really poor, right? And when the uncertainty is kind of an uneven distribution over the state distribution, right? So we try to solve this under the linear MDP model, and it turns out that this is what we got. Right, so this is what's known as an oracle inequality, which compares the performance of your algorithm with an oracle. right? So in this case, this V of pi hat is the value of my agent, the policy that I learned, so pi hat, by looking at the historical data, and I'm comparing this with a policy of an arbitrary comparator policy oracle, right? And the right-hand side is what we mean by a regret. So this is a performance difference. So as we can see on the right-hand side, like the lambda, the capital lambda inverse in the middle is in some sense a sample covariance matrix, and this phi is a state action features that are induced by running this oracle comparator policy. And as we can see that this is really the information theoretic limit that any algorithm can get with this matrix in the middle being the inverse Fisher information in some sense. And this like norm weighted by the inverse Fisher information measures the amount of distribution shift between pi and mu. So if Joshua is able to cover the behaviors of the optimal policy, we can choose this pi to be pi star, right? And this is give you offline learning bound. But if the coverage is not good, then my algorithm is able to compete with any other policies that leads to any kind of improvement to Joshua's performance. So the answer is yes. So even in the cases of poor data coverage, we can't hope to identify the optimal policy, but we can still do policy improvement. And we don't need to know like which pi that we're competing with, and effectively we're competing with any other pi that are out there with a regret that depends on the amount of discrepancy in the distribution shift. Okay, so I'm out of my time, so I'm gonna jump to the very end and skip this low switching cost setting. But the gist of this is that online RL, like, you don't need to make any assumptions. It can algorithmically enforce exploration. In offline RL, you have to make assumptions on good exploration in order to do anything meaningful. But it requires only one round of adaptivity. So whether there are anything in between, so we came up with a setting called reinforcement learning with low switching costs, in which the agent, in order to learn, you explore the world with k cycles. In each cycle, you collect data with the same policy, and then you get the data and decide the new policy to collect the data. So it turns out that this is an important problem for a lot of applications, and we recently established that the log t, where t is a number of steps that you have, log t number of policy switches is sufficiently is necessary for any algorithm with the nearly optimal regret for solving exploration to achieve square root of t regret. Right? So this is nearly a constant, which says that you can parallelize your experiments, and you can really distribute this new policy to all your Tesla cars, and they're gonna collect data for you, and you only need to do this a few times before you can obtain the optimal policy, and no assumption on exploration data at all. So this is a new setting that we are very excited about. I guess to summarize, RL is very important for real life applications, and it's essential to understand the impact and consequences of a deployed predictive model for the responsible application of machine learning. And we've developed some foundational algorithms and theoretical results on learning with offline data and reinforcement learning with low switching costs. Yeah, and this is still a very young field. I'm happy to talk more and chat with you guys offline about the things that might be of common interest. Thank you very much.
All right, thank you, Yushang. I guess, can I ask all the speakers to come back for the questions?
Test. There's another mic.
Igor? Oh, you want to? Okay, yeah, sure. So, questions for any of the speakers? We didn't write them down.
Miguel? Yes.
So all very, very interesting talks. Thanks a lot. I have a question to Igor. So you mentioned about the uncertainty. So when you put a loss function sort of implicitly talk about the distribution of the noise. So when you show this uncertainty, how do you compute it?
Yeah. So if you So this goes to, if you remember, the spectral decomposition formula that I wrote. So in the next slide, I had the part that I call the coherent part, and then the residual. So I put a cut between those two at a variety of different mode numbers. So you can keep just 10 elements for the coherent part and then call the rest the noise, and then compare with the data, yes? So as you do that, you get a variety of distributions. What I didn't mention due to time is on the left side of that slide, there were actually the distributions. If you follow them with your eye, you would see that as the number of modes goes up, the noise becomes more Gaussian. And that's a clue that something has regularized, and that now, you know, at the point when a noise becomes Gaussian, that's actually the point where you should stop, because otherwise you're taking, you're fitting a noise to your basically deterministic model. So hopefully that answers it.
So can I, yeah, very, thanks. Can I interpret like those very, very high frequency or something that you cannot capture?
Yes, you can interpret this. I mean, if you were in the signal processing world, you would call this maybe a sophisticated low-pass filter, but it really utilizes the noise in the representation so it doesn't throw it away. Maybe that's an important point. So it goes quite a bit beyond that, you know, low-pass filtering that we are used to. And it actually identifies the noise threshold from the process itself so that you don't overfit. Thanks for the question, yeah.
Thank you. Other questions?
This is for Professor Shanwang. Yeah. So you mentioned about the low-cost switching that once the offline policy has been trained, you can probably use the online training version and re-estimate the weights. But my question to you is, would this also be possible for use cases that change over time? And would there be an efficient way to learn new policies based on varying use cases with a minimal amount of data without needing to recompute most of the weights? Is there an inherent relationship between the state spaces that can be leveraged for this purpose?
Yeah, that's a very good question. Yeah, if you have a good model of the world, if you can fit the model of the world, and in some sense you have identified the underlying dynamics, and no matter what tasks that you substitute into the system in the future, you can do the planning with a learned dynamics, right? So some part of the algorithm sometimes do build a model, right? But there might be a difference in kind of the sample complexity, because in order to learn to do well in just one task, it is cheaper than identifying the model. Yeah.
That's all.
Other questions? Did I see a hand? Did you see a hand over there? Okay. I have some questions, I guess, for Sui. I was wondering, like, what physical or social applications would a non-parametric model be preferred over, let's say, searching among an array of parametric models?
Oh, you mean social applications?
Or physical.
Physical. Oh, okay. So I think the major thing we do the non-parametric setting is that we don't want to assume parametric form. Because, for example, in particle systems, like you use Leda-Jones potential or Morse potential, they actually yield the same kind of like Python formation, right? It really depends on a lot on the model's like expertise. So one to know non-parametric is that you give me how many data, we just know appropriate form that can actually give good prediction based on that data set. Yeah, I think I know that a lot of literature right now, they are using parametric, and non-parametric is just like, I mean, of course, with parametric, it's like using piecewise polynomial space like that, but still, like here, we really want to, you know.
I understand. Yeah, this is theory. I just wanted to say, like, how would there, like, you would have an elevator pitch.
I see. Yeah, now this kind of non-parametric method has been applied to astronomy, and also we are doing kind of application modeling fish meanings and ecology, yeah. Yeah, for social science, it's more challenging because data are very hard to obtain. Yeah, yeah. Yeah, thank you for your question.
Are there other questions?
Hi, so I have a question for Professor Igor. So I'm very interested in your last example, like there's a robot learning to to pick a ball or something like that. So I'm very interested in policy learning. So you mentioned that the robot will do some initial random collections in the initial phase. So my question is given that you have uncertainty models, and you may capture some epistemic uncertainty. So will it be a good idea for you to utilize the epistemic uncertainty to do the initial random exploration to this? And then the second question is what's the incentive for the robot to learn? Because in reinforcement learning, we have a return to maximize, but in the context of the Coupa operator, how do you achieve the learning? How can you maximize a return to learn policy?
It's working. Oh, okay, I succeeded. No, it's good. Let me describe the answer to the first question. So there is a cost function, to start with that is involved, and so it is. So when the robot learns, it actually is optimized a cost function. It happens that that cost function is associated with its ability to predict what the next state is going to be. So I hope that answers the first question. I think one aspect of your question is what kind of a distribution do you give it to start with? Yeah. And in this particular case, because it's a constrained space, just like for humans, you can actually do things at a relatively uniform distribution. Mm-hmm. It is also possible to have directed search. So if you are doing better in some directions and you're learning the model faster, then just go there. It learned in 5 minutes. It wasn't necessary for us to do it. I can envision that, this is a possible additional kind of meta-learning aspect that, given that we have distributions of noise, we can actually do. We didn't utilize it in that particular context. But yeah, nice question. Thanks.
Yes, thank you.
Okay, we have one more question for Igor here.
So yes, fascinating talk. I had a follow-up. Let's see if you can educate me. So I'm trying to place your approach. So clearly there is some built-in knowledge, because when you're, it's a little bit along, not symbolic AI, but it has built-in knowledge. When you actually have two terms where separating the signal and the noise, you're building into the model. That's not learned, right? That's a structure that you're imposing.
Yeah. Let me respond just to that, because not necessarily. So you can use expert knowledge if you want. So you can actually put down variables like, we know physics, so position and momenta, just learn that. But that representation eigenproblem that I mentioned, that's completely agnostic. And if you noticed, it actually uses neural network representations in them. That is completely agnostic. It's saying, why don't you learn me the observables that are really important? So for example, the size of the toothbrush would be an important observable, right? Why don't you learn that in order to figure out what's important to me? So you can run this in a completely agnostic manner. You can also incorporate SMEs, right? The subject matter expertise in it. But it's not restricted to SME. So it is a completely fundamental buildup from...
Okay, so but when you just said, you were answering that question, you said the part of the optimization or the separation used an assumption about Gaussian. That Gaussian, and that knowledge that, when you get to a Gaussian distribution, is that built in or is that learned?
Yeah, that can be absolutely learned.
Okay.
It doesn't, so let me actually go a little bit further. No need for a Gaussian. It turned out that this was actually a Gaussian noise. But if you ran this process with, the noise process was Gaussian. But if you ran this process with something else, instead of using a Gaussian classifier saying, oh, is this Gaussian or not, you could use Wasserstein. Somebody just mentioned it. You could use Wasserstein on any arbitrary distribution. The more important part is that the distribution becomes self-similar as you keep more and more modes. And I'm going to speculate now and go to your domain. Allow me for a second. I think maybe humans might be utilizing that they recognize that at some point they don't need to overfit anymore. There must be a cost function for that, right? And my speculation is that the self-similarity of the distribution might come into the picture, but it's not restricted to Gaussian.
So just as a final thought, so I get it clear in my head. So the self-similarity is built in, or is that learned too?
It's not.
It's learned.
Okay. In this particular case, the noise was Gaussian.
Okay.
And so what you got is that the noise, when you kept more and more modes, if you looked at the low number of modes, the noise was definitely not Gaussian. And if you increase the number of modes, it wasn't self-similar. It was going to something. It went to Gaussian, which is the appropriate thing at 40 modes. And then it started behaving in a self-similar way, right? And then actually you were losing accuracy. You were, despite the fact that this is where the visuals are cheating on us, right? It looked fantastic. The fit between the model and the data was great. But if you do a metric that says, well, how much time am I actually within the bounds of what the Gaussian is telling me? When you keep all of the modes, it was doing terribly. So it was actually making mistakes, relative mistakes that were really, really big. And that's kind of the non-trivial part of that particular analysis.
Thank you.
Sure.
Thank you. I want to ask a question from Professor Hu. So I only know like these classical models for how single agents do stochastic control problems for investment management. I was wondering, like, these days, how complex have these models gotten? Like, because machine learning can handle.
So thanks for the question. So in the industry, there are actually people or companies using machine learning, and that's called robo-advising. So there, you put the money in a bank account, and then the machine asks you some question, try to measure your risk preference. Say, with 100% you want $100, or 50% you have $0 or $1,000. So by having your answers, they measure if you are risk averse or risk taking, and then they are going to adjust their trading strategies for doing investment. And the benefit is that it has a low maintenance fee, actually. And with a comparable reward, sometimes comparable like return compared to like the human managers. Yeah, thank you.
Are there other questions? Is the food ready?
Food is almost ready.
Almost ready. Are there other questions? We can take more questions, or we can just, let them.
Okay, great. So I think we saw that. Let's thank all of the speakers again. Let's thank Manoush also. And the food is almost ready. You can head out to the patio. We have a catered lunch for the day, and we'll continue around 12:45.
Test. Okay. All right. Welcome back, everybody, to the CRML Summit. In the afternoon, our first speaker is Manjunas, who's going to give us a keynote speech on images. Manjunas is a distinguished professor of the electrical computer engineering at UCSB. And he has received many awards, but we're running a bit behind time. So I'll just let him to take the floor and tell you about his research and insight.
Thank you, Yusheng, and thanks, William, for inviting me and giving me this opportunity to present some of the work that we are doing here at UCSB. So the title is that okay? Is that no echo? There's some echo, right? Maybe take that. Okay, so are you guys okay with the echo? At least I'm hearing echo on my side. Anyway, so the topic, broadly speaking, is about computer vision, image analysis, and the machine learning techniques that are being applied within this context. And okay, thank you. So we all know that picture is worth, this is an old saying, picture is worth 1,000 words. And I'm using the word pictures in a very broad sense to include multimodal imaging data, for example, and also videos, time sequence data sets. And in the same context, patterns also in a very broad sense. I like this, I use this slide in my undergraduate computer vision class every time I teach about pattern recognition from images is a fairly challenging problem. And when we talk about patterns, you're essentially looking at, I had another slide which would be like the pixels and values from which you're making those interpretations, which is very, very difficult when you actually present that as a matrix of numbers. Even in those cases, right, in this case, how many of you have seen this picture before? Not too many. Do you recognize what's in the picture? Those of you who have not seen it? If I say that, I don't know, yeah, if I say that this is the face of the Dalmatian, you probably would immediately latch onto that, and then it will be very hard for you to not see that. And I'm sure Miguel is here somewhere in the audience, so he probably can give a 10-hour lecture on this topic. But one thing that was interesting, and I think my student is also here, when I showed this to him a couple of days back, and he has not seen this before, he said he sees a wolf in the picture, which I have not seen that interpretation, and Miguel can help me if we had. So let's see. First, let me see that first. So it's somewhere here, the face of the animal. And that's the first time I have heard about that. Right? So so we can see many different things in a single picture, even those that was not intended to be seen, I guess. Anyway, my talk will not be focusing on the human visual aspects of it, but rather look into applications of visual analysis in the context of many different science-driven problems. And the primary, we all know that the primary observation modality in most scientific disciplines are images or image sequences, right? You pick any of those, biology, materials, medical, etc. And these are complex in the sense that they're not structured data sets. So it's hard there's no prescription in terms of how you extract information from these. And they're dynamic in the sense of temporally or spatially varying. Typically, in most science observations, these are also multimodal, heterogeneous. And all of these things make computer vision applied to going beyond like typical cats and dogs detection and recognition problems, a lot more challenging and interesting. By the way, this is something that I took from a recent website. So there are over close to 2 trillion images that are there on the internet today. And about 90% of those pictures are all taken by smartphones these days. So even in the context of non-scientific applications, human to human or human-computer interactions, there's a plenty of data that's out there that's probably not well mined into. For example, we all take pictures and videos. Wonder how many times we actually go back and look at them a year or 5 years later, because it's not easy to manage, store, search through those data sets unless you kind of tag them with appropriate keywords. But then that gives us the plenty of opportunities here for interdisciplinary research, and that's kind of the main theme of my presentation here. Mostly I'll be introducing problems, not necessarily the solutions, and I see some of the faces here who could probably will be talking about it, and I'll mention those details later on. So in this context, in our lab, we have a variety of research collaborations spanning many, many different disciplines, from biomedical to remote sensing to materials. And so hopefully I'll pick some of those things and at least, if nothing else, introduce the problems to you, okay? And I'm sure I'll run out of time sooner or later. And so I would like to acknowledge all the students and researchers who have contributed to this. A large number of them have done all of the work that's I'm going to be presenting, including some high school students and undergraduate students. Okay, so let's start with the human brain as an example. So by the way, it will be discontinuous, my presentation, because I'll be switching from one topic to the other, so please bear with me on that note. So the first one that I would like to present here is on the brain connectome. NIH has spent over $100 million over the last 10, 15 years gathering large amounts of this data, but much of it is actually not been well explored. What we have here, and you kind of see this nice picture on the right-hand side, these are essentially what are known as the tractographs or the connections imaged at a very coarse resolution. You're looking at maybe a millimeter cube voxel volume here, and different regions of the brains that are connected, and the color coding here is essentially about the directionality of those connections. There's a large amount of prior research in terms of both on the imaging side of this, as well as how you can go about computing these tractographs. But what do you do with that? That's a problem that we are interested in looking into. And much of this work has been in collaboration with Professor Scott Grafton in the PBS department here on campus. So you can think of many different questions to kind of ask and see if you can get some answers, like if someone has depression, whether there are some connectivity changes that you can observe. Are there changes that you can observe as the brain ages? Or in certain disease or neurological disorder conditions. So these are the kinds of things that you could potentially ask. And much of the prior work within this context has focused on what's referred to as the connectivity matrix. Maybe the next slide would be kind of explains that a little bit better. So think of the whole brain volume somehow aligned for subjects, so kind of normalizing with respect to the spatial differences and sizes, and partitioned into, let's say, 100 or so different functional regions of interest. So one region might be focusing on visual processing, one region might be on the auditory, etc. And you have the tractographs that connect those different regions in the brain, right? So you can compute voxel to voxel connections coming from each one of these regions over here. And that would lead you to some kind of a network representation where the nodes in this graph are the ones that correspond to the functional regions, 100 or so that I mentioned before, and the connections could be how many neuronal fibers actually that you can compute that go from one region to the other region. And you can then come up with a connectivity matrix and base all of your analysis based on that connectivity matrix. But if you do that, what you lose in the process is how these things are actually connected to each other, the structure, the topology of this graph structure. And we kind of looked into this a little bit more, and Scott had done some prior work on this one. And the basic idea here is to come up with a sparse representation of this connectivity matrix, or rather the topological connections, but not necessarily having each and every fiber encoded, because that's computationally not only expensive, but also very difficult to make any inferences on. So we use what's known as a Reeb graph structure, which essentially has 4 parameters, so to say. So one is like where the connections begin and end. So that's the starting points and the ending points of each one of those trajectories. And there are these other 2 events, the merging and splitting, where the fibers come together or separate out. So you can have these parameters that control when they are grouped together and when they are separated, right? And based on that, you can create a sparser representation that better, in terms of the representation, is sparser, and also has more information than just a simple connectivity matrix. So in this case, you have this entire set of fibers here represented by these 6 nodes in the graph. Okay. And the question then is, how can you use this to do some analysis on whatever the problems that you are interested in? And here we are collaborating again with, well, actually before that. So this is something that we are currently working on, and we should have a paper ready shortly on this. So the data here comes from this ISM-RM data set, where again previously you just had the connections between the begin and end points, but now you can actually capture the topological representation in a better way. And according to at least our collaborators, this is doing a much better job than anything that's currently out there in terms of representing this information. But the problems that we are looking into are one example is the collaboration with Professor Jacob's lab here at UCSB, where they are studying the connection differences in women at varying stages of menopause from diffusion MRI. And one of the initial results that we have is that, I don't know whether the result itself is probably not that great in the sense that there are differences, but you can actually compute those differences between men and women in the pre-menopause status. The post ones are a lot more difficult. We don't have enough data at this point, so hopefully we'll have more results to report in the near future. The other problem that we are looking into is if there is an injury to the brain or a stroke, for example, what kind of disruptions, what kind of changes that would induce within the structure over there. So that's in collaboration again with Grafton and Professor Lucas Holz in Germany. Okay, so switching the topic here, still within the context of brain images, right? The other problem that we have been working on for about 3-4 years now is in collaboration with a neurosurgeon at UC Irvine Medical School, Jeff Chen, where we're trying to see if it is possible to detect and quantify this particular condition of the brain that is called normal pressure hydrocephalus. Essentially, what this means in terms of pictures here is that those, and by the way, there are about 700,000 plus people who have this condition. It mostly impacts elderly population, but there are also other age groups that might get impacted by this. So essentially, this is the result of the enlargement of the ventricles. So what you see in here, the previous one was about MRI scans, and this one is using CT scans. What you see are the enlargement of this ventricular region, the cerebrospinal fluid that gets distributed. And while the pressure is still the same, so that's why it's called the normal pressure. So the pressure hasn't changed, but the ventricular region has enlarged significantly. And it appears that, at least from what we understand, much of this is not well diagnosed early on. And this is one of the causes for dementia in elderly population, but and also it's reversible if it is detected early on, but again, they go undetected and untreated or treated differently because of the problems associated with correctly identifying this. So in this problem context, we focused on the segmentation problem. So given a CT scan, Actually, let me go to the next slide here. So in this case, what we are looking at is given a CT scan, come up with a segmentation methodology that identifies all of these different brain regions, gray matter, white matter, different regions that correspond to the CSF, and using the segmented volumes, do the prediction. And we did bring in here an interesting twist, which is to actually use the connectome information that was computed from the normal subjects from the NPH data set, the one that I mentioned before, to have average connection information that's factored into the segmentation methodology. And at the end of the day, you have the segmentation output and the prediction module that actually does quite well with respect to detecting the NPH condition. The current numbers we have is about 90 to 91% accuracy. The current state of the art is what's known as the Evans index, which is measuring what they refer to as the frontal horns here of the ventricular region. So this is the segment where the ventricles are the largest. So this is all very subjective. So the doctors would go, the specialists would go, and if they're quantitatively motivated, would look at these kinds of measurements and take the ratio of these frontal horns to the overall inner skull diameter. And if it's more than 30%, that's kind of speculated as the NPH condition. And compared to this Evans index, we can actually do a lot better in terms of the detection and identification of this. But more importantly, the segmentation itself is of interest in many other conditions, so that's one of the problems that we are currently exploring with the group at Irvine. By the way, feel free to ask questions since I'm going through different topics, so don't hesitate to interrupt me. All right, still within the context of brain imaging, but this is not really imaging the brain. This is another fun project that we got involved with, again, with Scott Grafton's group here, which is whether we can actually detect stress in humans by looking at and analyzing their face images or face videos in the IR domain. And again, a lot of people contributed towards generating this data, etc. Obviously, the advantages are that if you can do that with imaging, it's contactless, and hopefully you can do that. If you can do that in a robust manner, that's better than putting sensors on your body and doing all kinds of measurements. The setup here is interesting too. How do you induce stress in the first place? So essentially, the subjects were asked to put their feet in cold water, okay? And that's the condition that you're measuring here. And there are some other well-known methods that would quantify that and identify that as being a stress-induced condition. So I'm not going to get into the details of that, but basically this is how the stress is induced. And for whatever reason, and I think I should admit I don't know the reasons why they took the IR imagery or videos in the first place, because there was no intention of processing that as far as I know. But they did have the IR and the correlated visual imagery available. And what we did here was to come up with a deep neural network architecture that would measure what is known as this ISTI, initial systolic time interval. Honestly, I don't know exactly what it means or how it is measured, but that is coming from the signal that you are measuring from the sensors that are attached to the body, right? So the question we asked is that, can we actually measure that? And if we can measure that, from that can we predict the stress level associated with that? So that's essentially what we investigated. Here again, if you're interested in the details of it, maybe Satish is here somewhere. He can, so you can ask him. But it's essentially a deep network architecture with the input being the image sequences and perhaps focused on certain features of interest here. And then you're predicting the ISTI signal over here. And here are some qualitative comparisons in terms of the ground truth under no stress. And on the right-hand side an example of the comparison between the predicted and the ground truth under stress conditions. So seems to do reasonably well. And in terms of the actual numbers, we are about 80 to 85% in terms of detecting the stress compared to the ISTI, which gives you about 90%. So it's an interesting experiment, and I think there is a group of capstone students signed up this year to see if they can actually build an instrument that can do this stress detection. By the way, we only know the stress detection when somebody puts their feet in water. We don't know whether in other conditions what happens. I think they also were asked to do some problem solving. We have the experimental details elsewhere. Yes, Mother?
What's special about IR versus just visible?
The blood flow, which you can capture. I think that's the only thing I can think of at this point. Yeah, the visual information doesn't have it, unless you kind of have the visual expressions, right? That's the only way you can, but I don't know whether there is a commonality across subjects in terms of how they express or whether they're under stress or not. Whereas the blood flow, and then that's what actually the ISTI is measured by with sensors on your body, and I'm assuming that that's somewhat correlated here. Any other questions? How are we doing with time? I don't know till what time I have. I kind of lost track of.
You have 15 minutes.
Only 15 minutes, okay. Yeah.
Question about the Reeb graph.
Yes.
Is that essentially using like a knowledge graph architecture?
No, this Reeb graph is purely mechanical construction from the data. So it's essentially the spatial information that you have as the tractographs go from one point to the other. And you are essentially looking at when do you call these fibers to be grouped together versus not grouped together. That's all. Yeah. Okay. Moving on from the humans to up in the space. So this is a project that's in collaboration with Professor Dor Roberts in Geography Department and some of the students in my group. And also some of the researchers at JPL NASA who have helped us in terms of getting some of the data sets. So here we are looking at methane detection in hyperspectral imagery. So as we all know, this is one of those gases that are not good for the environment. Apparently it's about 80 to 100 times worse than carbon dioxide, even though it has a shorter lifespan. A third of this comes from dairy farms and livestock, and then a third comes from the oil and gas industry, and maybe some percentage from the landfill. So overall, it's not good news in terms of if you have a lot of these emissions, right? So the question here is, can we actually detect the hot spots by looking at this hyperspectral imagery, which is basically at least the way it's currently collected is that you have an aircraft flying and gathering information on a given region of interest. And at each one of those, so if you think of this as a data cube, you have an XY, which is basically the duration of the flight as the aircraft gathers those images. And at each pixel in the image, you are looking at about 432 bands of information, spectral bands separated by approximately 5 nanometers. So that's the image volume you're looking at. So it's pretty large in terms of processing that or feeding that into any standard neural network architectures. So, and then methane signature is somewhere around, I think, 2200 to 2500 nanometers. So but then it is combined with all of the other surrounding contextual information, so it is a hard problem. And we don't have too much of ground truth data also on this one. So working on this, we came up with, working together with Roberts Group, a match filter representation that processes this. Again, if you're interested in the details, please come and talk to me. I'm happy to discuss that with you. Essentially, you have some pre-filtering based on signal processing and then extracting the parameters of interest and then passing that through a classifier in order to do the prediction. And you are looking at here correlating the spectral and spatial information, kind of an end-to-end pipeline that does the detection. And the results are actually pretty interesting. So here on the left-hand side, and these are on a limited data set. So on the left-hand side, you see the ground truth information. So that's the people who have actually painfully annotated these signals. And on the right-hand side is the predicted plume mass that we are able to compute. And I think I'm going to just skip through the few slides. Essentially, left side is the ground truth, right side is the detections from our network. And the problem here, though, is that this average data is expensive, time-consuming, and not easily obtainable, right? Can we kind of scale this up to the world scale, entire world, where you have information from multi-band satellite images? So that's what Satish is looking into at this point, primarily looking at Sentinel satellite information here that have fairly frequent coverage pretty much all over the world, and see if we can take the knowledge gained from the analyzing the hyperspectral imagery, move that on to the multi-band Landsat or Sentinel kind of satellite imagery to do the prediction. So that's is a work in progress at this time, but the initial results are promising. So hopefully maybe in about 3 to 6 months we'll have more details on this available. Okay, going from top to bottom here. This one here is a collaboration between our group and there is this underwater imaging group called MAIR that do significant amount of underwater imaging. They have over 2,700 to 3,000 kilometers of the coastal line imaged off of the coast of California. In fact, the founder of this MAIR group was an ex-ECE graduate back from the 80s, I believe. But mostly now working on problems relating to underwater imaging related stuff. The problem that if this video plays, I might be able to say a few more things. So the way they are looking at it is fairly interesting, which is that when you, they're looking at the sea surface and basically counting a number of invertebrate species. So the only outcome or output that they have in their data set, which is tens of hours of video data, are the counts of the invertebrates present as the underwater, this UAV kind of goes through its whatever trajectory. So it's not like you have an object detector or bounding boxes nicely annotated so that you can work with that. And even that for them is an expensive, very labor-intensive process. And the way they count is that as the vehicle or the camera is moving, when the object hits the bottom of their screen, literally, they hit their count button. So essentially they say, okay, this particular species has 100 items here in this video of 5 minutes long. So that's the ground truth. So how do you work backwards from that information to actually annotating, detecting, and identifying regions of interest is what one of my students has been working on. And if you're interested to know more about it, he'll be defending his thesis in about a month's time. So please stop by. All right, okay, moving on to something very different. And I know that Sam will be talking about this at much greater length. And so this is coming from the materials problem domain. And this corresponds to, this concerns the microstructure pattern analysis, which is essentially the arrangement of the crystals and their orientation, and what can we do in terms of pattern recognition and the entire process here. And so this is in collaboration with Professors Theresa, Pollock, and Sam Daly, who is here in the audience today. And for the broader audience here, the basic problem here is that in the processing, how you create those materials does impact the structure at the nanoscale level of the materials you are trying to build, which in turn impacts their performance, right? So that's the PSP part here. So there is a relationship between the structure to the properties. Processing, of course, determines what the structure is. However, this whole process is fairly time-consuming and expensive in order to explore the space of possibility, space of materials that you can design. So what can we do to help? And just to give you an idea of the infrastructure, the equipment that's there here at UCSB, you have this tri-beam setup, which from this description here, it takes about 6 months to collect the sample, which is of this resolution here, costs tens of thousands of dollars, and not too many people have access to this, so et cetera, et cetera. It's a fairly laborious process. So what we are trying to do in this case is that, can we speed this up to some extent? One possibility is to speed up the XY resolution by interpolating, in some sense, not literally, but creating a super resolution based upon samples that you can get on the XY space. And that's something that we have currently have achieved. So that's the paper that's going to be appearing soon on that topic. But the goal here is to actually go in the third dimension. So the more expensive part is shaving off this material. So the way it is done is that you have a volume of data, a piece of material that you image, you shave the top layer off, you image again, and so on. You keep doing that. And that's the part that's pretty time consuming and obviously quite expensive. So can we do fewer samples and interpolate in some sense between both the spatial resolution and along the depth resolution? And unlike the traditional SR, the super resolution imaging that's done, what you're looking at, even though I'm showing this as a picture, these are not really pictures. What you have is that when the laser beam hits the material, it actually creates a diffraction pattern. And that at each location is something like a 64 by 64 image pattern, from which you're actually measuring the three-dimensional orientation of the crystal. And that is the one that's mapped onto this color coding scheme that you're seeing here. So what you're looking at is the orientation of the crystal as you go through that entire material. And so basically, you're not recreating the pixel values, but you're recreating the orientations in a physically consistent manner, because there are additional issues that are involved, and we explore different ways of bringing in the physics into the reconstruction process here. And the bottom line observation is that any of the standard existing good neural network architectures should give you reasonably good results, as long as you can take into account the rotational symmetry and the specific details of the crystals and their orientation within the context of your optimization problem. One other thing that I haven't mentioned here, I don't have a slide on this, is that we're also working on each one of these things. Here is think of that as a grain of your material, and we are developing methods to actually synthesize those grains using what are known as the adversarial network architectures. So can we now combine these to couple these two things together to actually create those synthetic materials where we can explore their properties in a more computational manner, rather than going through that entire experimental procedure that we discussed before. Okay, so in the interests of, well, actually, this is a cool problem too, and I should mention a few things about it. So far we have talked about problems where the images are actually captured and analyzed. In this case, what we looked at is how can we bring in signal processing to detect computer viruses. So think of this as taking those binary files, converting them into a signal, in this case an image. You can also do that with audio. That's what we have currently done. And creating a representation of your malware as an image signal. And then once you're in this space, you bring in your image processing pattern recognition tools to actually classify and group them together. The advantage of this is that with the traditional approaches, there are quite a few of them, including dynamic analysis. I'm looking at static analysis only here. You only know of things that you have seen before. So there's an exact match to, so when you have an antivirus software on your computer, most likely it is matching some kind of a signature associated with that that's unique. And you say, okay, this is classified as malware or not. By looking at this problem from a signal processing, image processing point of view, you can actually approximate this in the sense that I can look at what is close to this particular pattern. So I can actually do some kind of a similarity search in my signal space, whether that signal space is an image or an audio signal. And actually that turns out to be quite a powerful representation, and by the way, this was, we are working with researchers at Naval Research Lab in DC. This one actually got their prize award for the Science in Art exhibition. So essentially what you're looking at is malware here, shown as an image art. And the structure of the malware actually maps quite well to image signals. In fact, you can see sometimes people embed pictures within malware that also shows up in different ways. I don't think I have examples of that over here. And different classes or families of malware are grouped together within this context. So it's an interesting exploration, a different way of looking at malware analytics. And we have a website here, and part of this work was in collaboration with Professor Vinya's group in computer science department. And you can actually upload your data files and see how it gets classified. That's a fun thing to do. And here you can see the images that are embedded as part of the malware here. And this is being currently explored, and some of the technology is in the transition phases. And yeah.
Changing a few bits here and there should completely change the logic of whatever code you're running.
Right.
Where is the
So
implicit continuity coming from that allows you to do
right, that's a good question. So about what we have found, many of the malware that gets uploaded are variations of an existing piece. It's much easier to take someone else's virus and modify them, but so that these traditional signatures won't be able to detect, right? So that's, I think, what the numbers here are about 60% are about the repetitions of or variations of the existing malware. And that's how you can actually catch something that's a variation, but it's not yet out there detected and classified as such by your antivirus software. And with the image representation, you're already in the space where you have an approximation of the signal. So you can think of this as being filtered with, let's say, Gabor filters or whatnot, and then you have the filtered extractions of those things that are processed for your recognition classification purposes.
So I was wondering, of all the possible embeddings of the binary stuff into real vectors, why is an image?
We just started. There's a longer history. I can talk to you. Probably that will take another half an hour. But it came from steganography, by the way, which you were part of. So that was the history behind that. All right. Let's see. I think I'm probably running out of time here. So just to put things in perspective here, right? Till about 10 years or 15 years back, much of computer vision was kind of simplifying things obviously here, but you take the image or video and you do lots of initial signal processing. You extract edges, color information, texture, shape, whatnot. And then you have the pattern recognition engine, which could be either a machine learning kind of a thing or a more traditional approaches to that. And then you infer the signal, right? But what has changed in the last 10 years is that all of that internal structure is gone, right? People now just think of this as a black box. And you have a network, you hope that you can throw things at it, and you can get your thing out on the other side. So it's been successful, but you need to be a little bit more cautious in terms of completely disregarding what you do with the signal. And examples of this, I already have kind of mentioned this, right? One is the materials example, where you need to have a better understanding of the underlying imaging process in order to make that transformation. Or for the methane detection thing, we had matched filters coming from standard signal processing approaches, which are then, of course, fed into the classifiers. So I think it's important not to lose track of the initial processing steps, which could be crucial in terms of how the network performs overall. And also, again, you might have seen many of these things before. These networks are very easy to fool. It's actually almost very trivial to fool these networks. You can take I have an example here, where you can take a ship, which is classified as a ship by your great network, and then let's say I have another picture of a dog that's classified as a dog, and I can almost trivially make this dog, or rather make this ship be classified by the same network as as a dog with the same level of confidence. So it's not that difficult. And also, with this all the adversarial network perturbations, it's very easy to manipulate your images too. And it could have serious consequences, right? Whether it is deep fakes or more seriously with regard to manipulating satellite images to remove a building or insert a building of interest, that could create lots of other problems. Just recently, one other application of this, I don't know whether you noticed, it was in CNN yesterday or day before, Bruce Willis authorized his look-alike to be used for deep fakes. So you can have future Bruce Willis movies without him ever acting, right? So what is here is an example of we can actually, again, detect those manipulations, identify where the regions have been manipulated. And these things are getting better and better every day. Some of these manipulations would have taken an image processing expert working with Photoshop to create those things, would have taken maybe hours or days. But now with your iPhone, you can probably do that in seconds or minutes, right? So again, I have two examples here. I don't know whether you would be able to distinguish one is fake and one is not fake. How many of you think the right image is fake? Okay, and the left one? And who is right? So the left one is the filled in information. That's actually, this is a true image that has a lake here, and that's the data that's filled in. So again, it's not that difficult to do these manipulations. I would like to conclude this presentation with, so when we talk about image processing computer vision, I think we again lose track of the fact that whatever we do in the context of science, at least, it should be reproducible. But right now, there's nothing that's out there in terms of an infrastructure that enables that and facilitates that. We have been working on this, what we call the BISC infrastructure for a long time now. And again, this is in collaboration with Theresa, Rob Miller, and a few others outside of UCSB, Nirav Merchant and Amit Roy Chowdhury. In terms of building a software infrastructure where you can put your data, and once the data is in there, it's pristine, anything that you do to that is preserved, including all of the analysis that's performed on that. So many of the things that you saw before, including the NPH thing and the materials part, are now available as modules for anybody. So you don't have to really share the data by sending hard drives or emails or whatnot. Think of this as Google Docs, but for multimodal data. So once it is there, it's available. You can share it with anyone you want. In fact, we probably did this before Google Docs was available back in early 2005, 2006. So that's the system that we are building here. And it is, if you want to explore, feel free to contact any of us here, and we would enable that. But the most interesting part here is that unlike Google Docs, the traditional ones, you can actually bring your own processing modules to work with the data. And every computation that you do, the provenance of those computations is preserved. And I'm not going to get into these details here, but in closing, those of you who are into deep learning or excited about deep learning, yeah, it's great. It creates lots of opportunities, but kind of brings down the barrier to research in some sense. But there's no magic there either. So just pay attention to those things. I think that's a good message. And since this whole topic here is about sustainable and responsible AI, I thought I would just, these are not my pictures, this is not from our work. The one was from Facebook and the other one was from Berkeley and Google. So on the left-hand side, it kind of shows how the trajectory has changed over the last several years in terms of research in AI machine learning, broadly speaking. So I think that's the blue curve here, this one. So it's catching up with physics right now. And much of other areas in computer science and math have kind of lagged behind. But on the other hand, the downside in some sense is the computational cost associated with this. So again, these are all publicly available on archive, so you can explore this later. But if you look at the GPT-3, this is coming from the natural language processing, right? That's about 400 years of GPU time to get to that GPT-3 on a V100. That's scary, right? And look at the energy consumption. That's, I think, each one of these numbers corresponds to one round trip between New York and Europe, I think, but I'm not, it's just somewhere there, all the details you can find out, right? So it's expensive, and what can we do? And that's...
On that side, presumably your point is that more publications show some progress, more progress? Is that what
I don't know, it's just that there are more researchers publishing things. That's all it can say. So the real question is that, are they really relevant? That's, I don't know. Okay, all right, so I think I'll stop here, and if there are any questions, happy to take them.
We have time for a few questions. Go ahead.
So it seems like the availability of certain data that wasn't there before opens up. New data tends to open up new use cases, right? So
Absolutely.
like satellite imagery has become so affordable and all that. I was wondering, from where you stand, have you seen new types of data that are starting to grow really fast that eventually will be like, images today, and that we should start to think about applications of that?
I mean, from the science application, I think in medicine, in biology, materials, these data sets are huge. An image could be few tens of, and remote sensing too, the hyperspectral imagery volume, each one of them is in hundreds of gigabytes, right? So it's not still easily accessible to general public, right? So if you want to get even one data volume, we spend a lot of time trying to get access to the data. Connectome is another thing, which is data is there. It's been there for a while now, but not much has been done. Because of I mentioned about the barrier to accessing and processing the data. That's pretty steep. Each one of the problems that we kind of discuss, right, it requires one to actually jump into the domain to some extent, whether you are coming from the application side or from the computer science side of things. So the data is already there. It's just not visible to most of us. And I'm sure there are other modalities, instruments that are, I mean, if you just look at the health data, that your Apple Watches and all these things, that's a lot of data that's out there.
One more question. Okay, I can ask one question.
Sure.
So there's this recent breakthrough in the image world, computer vision world of generative models. Right. So the stable diffusion has been shown to generate really high quality images that has been perceived as AI taking over the creativity, right? So based on your experience and expertise, do you say that an AI being creative in generating stuff is easier or harder than using an algorithm to improve the quality of images to, say, in super resolution and so on? The goal is not to maybe generate creative stuff, but rather to better represent reality.
I guess there are two separate questions you're asking, right? One is what is the application space for these generative images in science applications? And the other one is on the creative side of things where AI can overtake I think I wouldn't say it's overtaking, it's just helping, right? Instead of using your pen and a brush and canvas, you are using your computer screen to some extent to do that. I'm not an expert on the artistic side of things, so I would not venture into that discussion. But certainly on the science side of things, definitely yes. I mean, the materials is a great example, and also using these generative tools to create more data for training, right? And that's people have already started doing that. So I think those are good users of such technology. But then, of course, there are this. And then Bruce Willis, I mentioned that. So.
Yeah, there's this ethical aspect of it. Like, how would you trust the generated images to actually represent the structure of the material? Or like, is this coming from other materials that you're training the model on? Or is it really representing the characteristics of?
Well, I don't know whether it's an ethical question there, but it's a valid question in the sense that whether what you're generating is physically realizable, right? Right now, the super resolution part, we have the ground truth. We actually take the original data and use that to downsample and see if we can create that. And that's the way to make sure that whatever you are doing has some confidence in it. Going to the completely generative models, that's still to be explored. And maybe I would let Sam and others comment on those things. But as long as you can validate in the first place, this actually reminds me of, I don't know, can I have one more minute? There was a paper that appeared in a very prominent journal very recently at the beginning of the year. They claimed on COVID, and my students are aware of this, they claimed that the recognition accuracy was 98% or so, 96 to 98%. We had similar data sets. So this is for, I think, lungs CT scans, not the X-ray images. We could not go beyond 80%. And we were wondering how, and so essentially bottom line is that they trained their model, and by the way, this was a journal publication. They trained their model, and of course the training data set has the label that said it's COVID or not COVID. And you see where it's going. When they tested it, they also had the data where they did not get rid of the label. So we actually went through this whole process, and then asked ourselves, so why didn't they get 100%? They didn't use the label. Obviously, the network didn't know that you should latch on to that only thing, right? So that's why they didn't get the 100%. Anyway, the paper has since been withdrawn.
Thank you, Manjunas. Let's give Manjunas another round of applause.
Thank you.
Let me introduce the next session chair, Professor Tim Sherwood, Professor of Computer Science, Interim Dean of the College of Creative Studies. And then Kim will host the next session on AI and machine learning for science engineering.
Wonderful. All right. Yeah, go ahead and get set up. All right. Welcome to our session on machine learning and science and engineering. As you've already had ample opportunity to see today, machine learning is this incredibly powerful lens for us to view the world. Sometimes, as we saw in our wonderful keynote, that can be tied to a physical lens, but it also is a metaphorical lens. It changes the way that we see things. It changes our capability to see things, and I think that has some deep ramifications for the future of science and engineering. Could not be more excited for the panel that was brought together here from the Summit Machine Learning. And so with that, let's welcome Leili from the Computer Science Department.
Thanks, Tim. So I'm Leili from Department of Computer Science. So today, I'm going to talk about deep generative models for drug discovery. So right after Yuxiang's question, whether we can use generative models. So I will talk about what is a generative model and how can we use that to discover new molecules that can possibly cure disease like COVID. Well, 2 years ago, there's COVID-19. Actually, I myself was impacted by COVID-19. I was supposed to join UCSB 2 years ago, but due to the pandemic, I couldn't, so I postponed 1 year. And of course, there are a lot of affected cases and a lot of deaths. So now here's the question. So we are entering 2020, and we have a lot of tools and a lot of computational power. Why still it takes so much time to develop a drug for a certain disease? Well, for the COVID case, it's already pretty impressive. Within just a year and a half, we have several effective treatment. But for many other diseases, we don't have that. And if you look at the whole pipeline of drug discovery and development, it's actually a very long pipeline. Usually it takes over 10 years and with more than $1 billion budget to develop from the very beginning, to identify target and to go to lab experiment and then lead to clinical trials. So each stage can take multiple years until it hit the market and get FDA approval. So, well, there isn't much we can do during clinical trials. There's something we can do, actually. AI can play a role here in clinical trials as well. But even before that, before the clinical trial, it also takes 3 to 6 years. So can we actually use computation and AI to accelerate that process? Well, even before AI, people are trying to use computation to do drug discovery inside the computer. So the main idea is, well, we already have some library, pretty large library. So it's a very large library with some candidate compound. So those are not particularly targeted for a particular disease, but those can be candidates. Where we can use some computation and molecular dynamic simulation to do some virtual screening. So only on those, without the lab experiment, we just select from those candidates and trying to filter out those highly promising ones, and then reduce those candidates to maybe a few hundred, and then do a lab experiment for those, and then go those most promising ones will go to a clinical trial. Well, to make it effective, well, you need a very large virtual library. So one effort we can do is building ever larger virtual library. But of course, there's a limitation. And you also need to predict the properties of those chemical compounds precisely. We're taking the COVID-19, for example. So these are two FDA-approved drugs for COVID. This one is remdesivir. So this probably most famous one. This one actually was from the library. It's originally for hepatitis C, so not really for COVID. And they repurposed that and repurposed that for COVID. And this one, actually this one has two compounds. So Paxlovid, just recently approved by FDA. It has two compounds. So this one is originally for HIV treatment. So that's from the library, and they tested on COVID. And that one was new, was discovered last year. And it's the way to discover this structure is by modifying prior inhibitors to other protein targets, and by tailoring to COVID, this specific protein here. So, and we can see from these examples, these two examples, there are two ways actually to discover new drug. One is trying to repurpose old chemicals from the library. The other is trying to modify existing structure tailored to the new target. So whether AI can play a role here. So a few years ago, 3 years ago, this is work from a startup company teamed with Wuxi Tech is another startup company. Two startup companies, they teamed up to use this reinforcement learning algorithm trying to generate new chemical structures tailored for this particular target called DDR1. So DDR1 is a very important protein kinases. It's responsible for many of the cancers in lung and in kidney. And within just 46 days, they discovered 4 promising chemical compound. They actually tested that in lab, and 2 actually lead to final test. I think they actually trying to produce 1 promising drug from there. So this is a first example, successful, not really successful. We haven't seen clinical trials yet, but already reducing the preclinical part from years to just tens of days, a few months. So it's pretty impressive. And well, can we generalize even further? Yes, there are a large family of models called deep generative model. And well, we use that a lot in AI for language generation, text generation, image generation, as I just mentioned. But we can also use the same family of algorithm, these deep generative models, to generate molecules. Well, I listed a few of them. There are some models mentioned by Miguel in the morning, like transformer, ASTM, and there are other models like reinforcement learning we already seen for the DDR1 case. And today I'm going to talk about one particular algorithm called MAS. Well, let's see how we are going to generate a molecule. So we can view molecule in different perspective. The first perspective is where we can treat this molecule as a graph, so we can actually represent it as a chemical formula. But instead of using this condensed version, we write it in this form. It's called a SMILES. So in this form, you can actually reconstruct the original graph structure from this SMILE representation. Well, if you view it, it's actually very similar to the normal objects we process in natural language processing. We have a sentence, we have verb. Here we have a sequence of discrete tokens, and each token is just an atom. All the heavy atoms are here, the hydrogen is out. And we can model the probability of this discrete sequence using this decomposition, and then using our normal deep learning models such as LSTM or even transformer models to model the joint probability of such sequence. And then once we train such model, we are able to generate possibly new sequences using the model. So that's one perspective, treating the molecule as a sequence. And another way is we can treat the molecule as generating from some latent space where it's high dimensional continuous space. We want to directly generate from there. And one particular way to do that is called a variation autoencoder. That's a usual method we use to generate image or generate sentences. We can use the same method to generate, to learn such latent space and generate SMILE sequences. Well, a third perspective is we can use this reinforcement learning based generation. Pretty much the same algorithms, the same type of algorithm Yuxiang mentioned in the morning. we set up the reward as whether this candidate molecule will bind to the particular target or not. Then gradually, by modifying existing molecule structure, we can generate better and better molecule sequences. And 2 years ago, a group of researchers at MIT actually, they used this reinforcement learning algorithm generated candidate sequences for these are 2 targets responsible for Alzheimer's disease. And this is the first example that they can actually use one algorithm target for two possible targets for a single disease. Well, all these algorithms are good, but what are the challenges? So the issue is we want to generate a highly effective molecule, but there are also commercial side about it. So there are, for certain diseases, there are already previously reported drug candidate or previously already patented drugs. Of course, you want to develop a new drug, the drug with a new structure that was not patented before. So novelty is really critical here. We want to find molecules that are not similar to existing ones, but still highly effective. Well, it's a very large search space if you consider all the possible molecules within, say, 50 heavy atoms. That's perhaps 10 to 30 to 60 search space. That's a very large space, even larger than the normal sentence space we have in natural language processing. And unfortunately, only very limited few of them have chemical properties tested in the lab. So majority of the molecule of the space are unexplored. And within that unexplored space, only a small fraction that are in our library, but they don't have any measured chemical property. So how can we find highly effective molecules from this possible space or even from unexplored space? And there are also other properties we want to consider, not only effective, but also safety, whether it's solutable, so that you can actually digest, whether it's selective or not. So multiple objectives are relevant. So our goal is to find diverse molecules that can satisfy those multiple objectives, including those efficacy, solubility, safety, toxicity, etc. And we want many of them, and we want normal molecules from there. And again, we don't have much label data. It's not like in image classification case where we have ImageNet here. We only have a very small set of chemicals that has measurement, but usually those measurements are not really tailored to particular disease target. So, okay, so one particular framework we proposed is this sampling-based approach using MCMC sampling, where we try to sample from target distribution of this pi x, which is a target distribution on all possible valid molecules. And we can decompose that target distribution into k different properties. So each one representing an ideal property we want. For example, it can be QED score. It's measuring whether a chemical likes a drug or not. And this SA score is a possibility to synthesize that compound or not. Of course, these are all approximate measures. So before the lab experiment, we can't guarantee that it can be effective drug or it can be synthesized. So our goal is to sample from this space once we have those desired properties. And to be able to sample from there, we have to build from some basic units. So the basic units are molecule fragments, which we mined from a library. So we start from this Campbell database. It contains 2.3 million compounds. And we break all those single bond and mine 1,000 most frequent fragments with no more than 10 heavy atoms. So those are a few examples. We see some common ones like water is there. And our framework is through sampling. So we will start with very simple molecule here with just 2 carbon. And start with this molecule, we propose modification to the molecule. We can either add one more fragment from our fragment library, or we remove some existing fragment by cutting the single bond. And then we compute whether we will accept this modified molecule or not using this acceptance ratio. So in addition, to make it more effective, we will learn such proposal during our sampling. We will use our own sampled molecules to get better and better molecules. So those are examples of the adding more fragment and deleting existing fragment. And to model the molecule, we use a neural network called message parsing neural network. It's a specific model that can represent graphs. Of course, it's not just the molecule itself. We have to consider the target. So we have to take the binding into consideration. So there's some target which is a protein. And this is the area we want our candidate molecule to bind to. So we will use an external software called Vine to calculate this docking score, which will tell us approximately how well this candidate molecule will bind to that particular protein. And we can also take the 3D structure into consideration in the same framework. 3D will determine the geometry and also geometry of the molecule and also geometry of the protein pocket. So some of the initial result we have, so we evaluate on these 2 target related to AD. And we use additional score QED and SA as we described before. And this one is the red bar is the score by our algorithm mass. And compared to some other, this purple one is a genetic algorithm. Rational IL we just introduced, it's a reinforcement learning. And JTVA is a VAE-based algorithm. So it's very effective, and it can explore very large chemical space as well. So if we consider, so here I plot those blue ones are molecules that's already in our database. We know they can, they have some show positive affinity to the target. And those gray ones are generated by all different algorithms. So this one is generated by Mars, and this one is by genetic algorithm, and this one is by reinforcement learning. So this plot actually shows the Mars can explore much larger space, and it's more distributed in the space. So here are some candidate molecule we found using the algorithm. I don't know much about chemistry, so maybe we need our chemistry colleagues to interpret whether they make sense or not. So the key takeaway from this talk is that there are great challenges in drug discovery. We need to satisfy multiple objectives. We want to find novel and diverse molecules, and there's lack of data. So this problem can be modeled as a molecule generation problem. So we have MAS, it's a MCMC-based sampling algorithm, and it's adaptive and can discover novel and diverse molecules. There are remaining challenges. How can we integrate more properties other than synthesizability and drug likeness? There are also larger molecules like peptide and even protein, so those are more challenging. So my team have been working on natural language processing and also AI for drug discovery. So some of our team members are here. If you have chance, you are welcome to talk to them. Ouyang Siqi and Wang Danqing and Zheng Qiaosong. Thank you.
This is this is Claudio.
All right. So just a reminder, we'll have a session at the end for some Q&A with our panelists. Let's welcome our next speaker, Claudio Campagnari from the Department of Physics.
Hi. So usually when I give a talk, I'm confident that I know as much about what I'm talking about as anybody in the audience. Here I'm giving a talk about machine learning, of which I know about this much, and medicine, of which I know zero. Okay. So this is going to be an adventure. What I'm going to talk about here about some of the machine learning stuff that I worked on in medicine is not what I do for a living. This is something that I do on a, it's like a weekend hobby project. And I work, there are two physicists on this team. It's myself and Javier Gil, who's a professor at San Diego, and he's one of my closest collaborators. And then everybody else here is basically a clinician. And if Avi and I know zero about machine learning, these people know -1 about machine learning. So anyway, now what you will see today, what you'll see is that what we do is very, 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 very simple, especially compared to what we've heard today. But the exciting and at the same time scary thing is that these people are thinking of starting to use what we've done in real life in their practice. So I'm a particle physicist, a high-energy physicist, high-energy physics, HEP, and we've sort of used some kinds of machine learning, primitive machine learning for 30 years, so we didn't call it machine learning. I work at CERN. We have this is a proton-proton collider. This is the detector. It's a huge thing. This is the size of, this is a person. These are technicians here working on the detector. And this is what one of the proton-proton collisions might look like. The collisions happen right here in the middle. And what you see here is a visualization of charged particles that are generated in the collisions. You don't see, there's twice as many neutral particles also generated that you don't even see here. So we call this an event, something happened. And this happens at the rate of 40 megahertz, 24/7 for 8 months per year. So there's talk about big data. Okay, so what we want to do in this experiment is to measure rates and properties of various physical processes. For example, how often does a proton-proton collision result in making two top quarks? Or are the properties of these two these events with 2 top quarks consistent with what we expect. Or we want to discover new processes. You know, the Higgs boson is now old news. It was discovered 10 years ago in these experiments, or some other crazy and rare thing. So what we do, essentially, we have a classification problem. We need to classify events as signal versus background. And so this is what we use the machine learning for. Recently, people have started also to use machine learning for improving measurement precision. But in this talk, I will only talk about classification. Now, the thing is that what we do is looking for needles in a haystack. These are various processes that we've measured. It doesn't matter what they are. But on this axis, you see the rate at which they happen. The total event rate is 40 megahertz. This is 10 millihertz. This is 10 per year. And what we are interested in is the stuff that happens over here. Okay? So we need to get this, find the cool stuff out of this mess of things that are not so interesting. And you know, as you can imagine, I mean, these are very complex quote-unquote events, and each event is characterized by many, many features. And so what we need to do is select the events. And there are many, many features, and this is just a cartoon where you can just maybe the nth variable, and this is the nth plus 1 variable that characterizes an event. There's a phase space of all of the events, which is huge, and what you're interested in here is somewhere over here, and of course, this is a multi-dimensional phase space. In the old days, we would select events just using what we could call square cuts. So you make a cut, this variable must be between here and here, this variable must be between here and here, and you pick out those events and then you go and study them. And you can see what happens here is that you lose efficiency because some of the stuff goes out of your selection. Now you can make your selection larger and get all of your signals, but then you get also a lot of background. So in a multivariate or machine learning approach, instead, we make a big selection, like I said, and then we use machine learning to try to tell the stuff that we're not interested from the stuff that we are interested. And so we select all of these events for further analysis. This is an example from my own research or a paper that we published recently. We were looking for one of those super rare things. So we have a boosted decision tree. Here's the plot of the boosted decision tree. To the left is less signal-like, and to the right is more signal-like. And there's a distribution. The dots are the data. And we have to try to understand the whole distribution. So we have various processes here with different colors for which we try to account for everything. And then in order to account for this tail here, we need to put also in the fit. The fit tells us that there has to be some signal here. So this is the signal that is extracted from the fit. So this is a typical application of these techniques in our experiments. I must say that for many, many years, I've not been a big fan of this stuff. I'm still a little queasy. And the reason is that the first time that I ever saw this was 30 years ago when we were all looking for the top quark. And one of our colleagues went to a conference, learned about neural nets, and came to our meeting and showed us a plot and said, "Hey guys, I found the top quark." And we had with a plot just like this, and we were, you know, those of us who had been beating our heads against the wall for the previous 2 years, trying to figure out how to do that, were amazed and scared at the same time, and everybody went out and tried to understand what the heck is this neural net. We never heard of it, But then what happened? That the guy came back 2 weeks later and retracted the whole thing. And so what had happened was that you have a neural net, and he threw the kitchen sink at the neural net, but as well as the kitchen sink, he also threw the garbage pail at the neural net. And so what came out was that there was some notorious pieces of the detector that were not understood, that had noise, and what the neural net concentrated on picked out the noise and said that the noise makes these events look more like top than something else. And so I've always been skeptical, because the challenge here is not so much the technology of how you make the machine learning, but do you really understand what's going on over here, okay? Oh, of course, of course.
The labels,
Of course, of course.
even learn rare events using a machine learning framework. It's never really been done before.
No, it has been done, but of course, I mean, this is just the last. Believe me, when we get on one of these analysis approved by the collaboration of 1,000 people, it comes with 250 pages of documentation to back up this plot. Okay, this is just the last plot, and literally, when I say 250 pages, I'm not kidding you. This is another one, another of our analysis. This is another boosted decision tree. You see that there's it's a lot of stuff. There's a lot of events over here. Our putative background goes over. Our putative signal would be over here. But what we do in this case is that we do not put the most significant, the most important feature into the boosted decision tree. Instead, we make a requirement on the boosted decision tree, and then we plot the feature, and the feature would be a peak, and we see a peak, and so that's good, and we make measurements. So that's one thing that we do. So when I talk about machine learning versus square cuts, the new way of doing things and the old way of doing things, the multivariate is more efficient. There's more information because you can throw more variables of it. It's more opaque, garbage in, garbage out. And naturally, each selected event has a weight, more signal-like versus less signal-like. With square cuts, it becomes more complicated, but it's more under control. We've been doing this for a long time now, and I think the bottom line is that these approaches are somewhere between a factor of 2 and 10% better than just the old-fashioned approach. It's not it's not game-changing in most cases. Okay, so now cardiology. So how the hell did I ended up getting involved in cardiology? It's all the fault of this guy, Avi Yagil, my collaborator. My collaborator came back from CERN with a cold, and he couldn't shake the cold. And then it turned out that something had attacked his heart. And he got progressively sicker and sicker and sicker until they put him in the hospital at UCSD to get a heart transplant. And so as he was waiting for a heart, his wife was at his side. And his wife is also a physicist. She's a professor at Irvine. And when you are apparently, I don't want to ever find out, when you are in a hospital waiting for a heart transplant, they measure the hell out of you every 6 hours or less. And so there was a lot of data, and physicists like data, and so his wife and him started plotting various things, and they discovered all sorts of correlations with the treatment that he was given. Hey, you've given me this drug, and then look what happened here. Stop it. And so the cardiologists were kind of impressed. So Avi got his got his new heart. He's in better shape than he's ever been before, so everything is good. But then then he made friends with this cardiologist, and so they said, well, can we do something together? And then Avi dragged me into this thing. And so just as a exercise, we decided, with the cardiologist, we decided to make a risk score for heart failure patients. So how bad, so somebody has a heart failure diagnosis, how bad is it? So again, we used the boosted decision tree. And this was based on the electronic health record of UCSD medicine. This is challenging, and I'll come back to that. In designing the algorithm, we thought that we should define the outcomes very crisply. I'll show you what I mean by that. Imputation, we learned this new word in medicine, imputation, which means that when do you guys know what imputation is? Yes, everybody knows? No, imputation is that if you need 10 variables and you have only 9 of them, you take the 10th variable from somewhere else and you put it in. Now, for a physicist, this is like blasphemy, okay? But in medicine, it's done all the time, and we decided not to do it, and we did all sorts of other studies, and you wouldn't believe the complaints that we get from the referees of the medical papers. Okay, it's a very small number of inputs, just 8. For ease of use, and also because there's not enough patient statistics to do anything sophisticated. And the other thing is that you want these 8 variables to be collected within a short amount of time. You don't want to use the blood pressure collected in May and the blood test in December, okay? So, and to define the samples, somebody that dies after 11 months and somebody that dies after 13 months, there's no difference, or the difference is very little. So to define the samples, we just decided these are patients that are very sick, they die within 3 days, and these are patients that are very healthier, and they survive at least 3 years or so. And the variables that are used are blood pressure, and then things that when you get your weekly physical and you get a blood test, you'll get. So they're very simple things. So if you look at the input variables for the low risk and the high risk, they don't look very different. They look a little bit different, but not that different. But of course, if you throw them in some machine learning boosted decision tree or neural net, you will get some separation. And the area under the curve is about 88%. Now we can get the same, whether we use a boosted decision tree or a simple neural net, even a Fisher discriminant from the 1930s would do just as well, okay? So we have that. Now, we made this plot, and which to me is obvious, but the cardiologist thought it was unbelievably great, and that made him believe in what we were doing. So what this is showing is the various variables, okay, and their correlation with the score. Low score means healthy, high score means bad, okay? And the yellow, if you go look at the yellow ranges, is if you go look on Google, what is the healthy range? Those are the healthy ranges. And of course, the machine figured out what the healthy ranges were. Okay, I mean, it's kind of obvious, but I think when the cardiologists saw this, they said, oh my God, maybe we can believe these guys. If you look at the mortality as a function of this score, it's obviously different. We validated it with data from other places, so from UC San Francisco and from a European group. This is the 1 minus the mortality, so the survival probability for 1 year. It looks the same. We did demographic studies, male versus female, white versus non-white, inpatients versus outpatients. It all looks good. And then we compared it with other scores and markers that we could get our hands on. And these are the curves. The black is us, and the other ones are these red curves. And turns out that we do better. So now you should ask yourself, why is it that we do better? And the reason is that the quote-unquote competition is extraordinarily simple. This is how this score is built, this IMRS score, which is actually one of the decent ones. It's extraordinarily simple. It uses 15 variables. Okay, we use 8, they use 15. But it just adds numbers like this. There are no correlations whatsoever in these scores, all right? So that's why we do better. So we published it. We made a calculator. The lawyers got involved. So so if you accept all of this mumbo jumbo, and you click on I accept, you get here where you can put your data. I don't want to put my data there. I don't want to know. Some things are better not known. And then when you put your data and you hit calculate, it calculates. And okay, these I put some random numbers in, but what it gives me minus 0.08, which is over here, which tells me that I have a survival probability of 80% in 1 year. So this is the scary part, because this was just a game, pretty much. Scary part is that now this is being integrated on an experimental basis in the UCSD and also in the Northwestern hospital systems. So machine learning, energy physics versus cardiology. In energy physics, we train with simulated data, mostly, and we can get as much statistics as we want. Easily, you can train with millions of events. which allows you to do sophisticated things. And also we have a crisp definition of outcomes. It's either a signal or a backer. In cardiology, we treat with real patient data. The statistics is limited. The number of data that the number of patients that you can get your hands on is small, so the algorithms are not very complicated. The range of outcomes is continuous. I mean, how do you distinguish between somebody that dies after 11 months versus 13 months? But the challenge is that getting reliable data from the electronic health records is very painful. You have to go to the bureaucracy, which is one problem. But then the data quality is terrible, and you have to really look at the data very, very carefully. We looked at the data, and then we went back to the people that extracted the data and said, how come you tell me that this person died in 2017 and I have blood tests from 2019? It's that kind of stuff. And then you have to be careful of bias samples and so on. In energy physics, the question is the garbage in, garbage out. At what level do you really trust the simulation of your experiment, both the underlying physics processes and the simulation of all the detector idiosyncrasies that you have? And so you have to use control samples. You have to be smart. You have to write 250-page analysis notes for the collaboration to poke at you. Since the publication, a group from Northwestern verified that it also works on their patients. And they tested it on the state-of-the-art score, which we couldn't test because it was too complicated. They found that our thing works just as well, and it's much easier to deal with, and so that's why they're putting it in the system. A group from Harvard decided to look at whether they can use this score to improve the efficiency of clinical trials. And then 2 Korean groups are interested in using it. They verified that it also works on Koreans, not just Americans and Europeans. And it also found that it works for conditions besides heart failure. So this is the comparison of the UCSD, Northwestern, and Korean, all about the same. And then with the Korean databases, by the way, Korean databases are so much better than American databases. There's no comparison, okay? It works for all of these other things, except for cancer. It doesn't work very well for cancer, but you don't expect it to work for cancer. That's a different story. So this was just a proof of principle for us. Our cardiology colleagues have several ideas for problems that we want to pursue. Getting our hands on good data sets has proven difficult. Even the data sets from clinical trials and some of our cardiologists collaborators are big shot PIs in some of these big clinical trials. These data sets are a mess. We do have some irons in the fire. The most interesting one is something that has an ominous name. It's sudden cardiac death. And briefly, the issue here is that there are guidelines to instill defibrillators in people that are not optimal. Many patients do not get it that need it, and many patients get it when they don't need it. And it's invasive, and kind of machine learning algorithms like the ones we just developed helps. And we have some preliminary results that looks like this looks very promising. Just one last slide. For machine learning in medicine, you have to, in my mind, I distinguish image processing from what we've done with numbers, essentially, with few numbers. And the image tools are quite advanced. We heard some about it today. For the other problems, there's a ton of low-hanging fruit. If newbies like Avi and myself that know this much about machine learning can develop things that are at or beyond the state of the art, it means that there's a lot that can be done. The tools that we use are not sophisticated. We do not need super expert understanding, just common sense is good. The software we use has been around for 20 years in energy physics. And the challenge is not the technology, but formulating the problems and then getting a hold of decent data sets. Thank you.
yours. Okay.
Because I changed it, sorry, I was traveling. I was traveling and my power went out last night. Yeah, it went out for like 3 hours. Okay.
Who needs power?
Who needs power? It's fine. I did check it, so it should work. Cool.
All right. Well, our next presentation here is Samantha Daly from the Department of Mechanical Engineering. Let's welcome.
All right, thank you. It's a pleasure to be here, and thank you for inviting me. I think these types of things are really important to get people talking across disciplines, and it's something that if we're all going to advance, that we really make an effort to do, and so I'm particularly delighted to be here. So we're going to talk a little bit about the work that we've been doing to integrate machine learning with mechanics, and in a broader sense, kind of the challenges and the opportunities that we as an engineering community are facing with the advancements in computational power, in machine learning algorithms, and in our ability to collect much larger amounts of experimental information than we used to be able to. This is work that I get to present, but this is really the work of my postdocs and my students. And so I just would like to briefly acknowledge my postdocs, Neil Brodnick and Jia Chen, and my graduate student, Kaylin Muir, who did the work that I'm going to present today. There's been a lot of discussion about how there have basically the frameworks for a lot of the machine learning that we're using in experimental mechanics and in engineering in general have been around for a while, but we used to kind of have to hard code kind of the classifiers. If you were identifying a stop sign, you'd have to hard code the edge detection algorithms, you'd have to hard code the letter detection algorithms, you have to like feed it in. And we kind of had, it didn't really take off for a while because you didn't have enough data. We couldn't collect enough data. We couldn't feed the algorithms enough data to train them. And so they were kind of stymied. They were at an impasse. And that has changed in the last 10 years. We are now able to collect enough data to make use of these beautiful frameworks that have been there waiting for us. And this has really enabled a leap forward, a paradigm shift that was just waiting to be activated so that we can start to enable the analysis of these complex scientific phenomena. There are a lot of shared challenges that we're looking at that extend into engineering as well, including feature extraction, things like, these are just a couple examples, reduced order modeling, experimental data analysis, dimensionality reduction, image recognition, controls, shape generation and optimization, intelligent design of experiments. And so I've put a couple, I'm a solid mechanician, but I've put a couple other examples on the right of fluid dynamics and thermal management. There's actually a really cool, they're doing kind of machine learning enabled chips where you go away from the von Neumann architecture, which you have a latency issue for those who are into chip design, where you are kind of storing your two processes. You have to constantly take your memory in your process and communicate between the two, and they're just kind of putting everything more like a brain onto one side. But there's some thermal management issues with that, so these new kind of ML-enabled chips. So there's a lot of places that these are being used. So today I'm going to focus on the use of machine learning to address the challenge of limited and costly experiments or computations, which is a widely faced problem in engineering, where we typically have very detail-rich and usually multimodal information at a very few select points. So we run an experiment, or we run a simulation. I'm an experimentalist, I'm going to talk mostly about that. And we get information from different modalities at that experiment, but it's taken at a very specific environment, loading condition, temperature. We're bending it or we're twisting it. We're doing something very specific, right, to a very specific material with a specific microstructure, a specific composite, right? So it's one very specific data point of that material tested under very specific conditions to give us the behavior. I'm going to talk briefly on 4 examples of recent research from our group in solid mechanics that highlight some of the uses of machine learning in engineering. So we're going to start with machine learning for high throughput experimentation. So we're now able to obtain a lot of experimental information, and this is one example of that from our labs. So this research was aimed at determining the relationships between twinning and microstructure. And what twinning is it's those blue lenticular shapes. So I've taken, this is magnesium. This is displacements on magnesium. We actually attached a bunch of nanoparticles to the material, and this is a 4 millimeter by 6 millimeter field of view. We track all the nanoparticles, and we can look at the displacements. Those little blue lenticular shapes are those twins. They're really important because they make magnesium more ductile. So if we want to superplastically form components for lightweighting, we need those twins. And so there's a lot of interest in how those twins relate to how you process the material. And so this is about 100+ million data points of displacement and thereby strain in one test. And this is a field of view of about 4 by 6 millimeters. Now the challenge here was we want to understand twinning, so we need a high enough spatial resolution to capture those twins, but we needed over tens to hundreds of thousands of grains in order to understand kind of the mechanism of twinning with relation to how we make the material. However, it would be absolutely intractable to identify twins even over the 1,500 grains shown in this one test, let alone across the many tests that it would take to look at different processing conditions, different loading conditions. It's just not feasible. So we've used machine learning to teach the computer how to do this for us. So here's the result of the machine learning analysis to segment and identify twin systems, or their absence, in each of the 1,500 grains in this test. And each grain is a different arrangement of atoms. So if you have a cubic atomic structure, maybe in one grain they're like this, and maybe in another grain they're like this, okay? And what we did is we achieved this by using just a k-means algorithm to cluster each individual grain, the strains in each individual grain. So we took a grain, and we used k-means to look at the strains in that grain and cluster like strains. And each grain is going to have a different number of clusters, because some grains are going to have twins in them, and some grains aren't. Some grains have other high strain regions, maybe cracking or something else going on. And for those of you familiar with k-means and clustering, we use things like the Davis-Boldig index and the silhouette value to kind of look at how many clusters to have. And then once we had segmented, which was fairly straightforward, the tricky part was identifying what was a twin. We can see it, right? I mean, it's the blue thing right there. But teaching the computer to do that was a little trickier. And so what we did was we used basically a voting scheme where we compared the strains, the experimentally measured strains, with the theoretically predicted surface strains of all the twins that were possible in that grain. We just applied Euclidean distance as a dissimilarity metric. And we considered the Schmidt factor of the grain, which is basically how likely is it to twin. We considered if it grew, it's just common sense, if you're loading the grain, the twin should grow. And we considered the shape. It's kind of like a lens shape. So we used a convolutional neural network to train the recognition of the shape of the grain. And not only the recognition of the shape, but we took the colors inside the twin, which are the strain inside of it, and we encoded the strain as a color, and then had computer vision recognize that color as also being part of the twin. And so we were able to actually identify specific variants of twins and backfill them. And what this does is it gives us really rich, very high throughput data sets that are sufficiently large to capture the stochastic nature of twinning at high enough spatial resolution that are fully segmented, fully annotated, ready to use. So these are fully mineable for a wide variety of new analyses on insights on the properties of magnesium in relation to their processing. And we are now working with modelers at the University of Michigan, and you can see the spatially resolved modeling on the left and our experiments on the right, in order to analyze what processing conditions can lead to more ductile magnesium alloys for lightweighting. In general, there is a significant push for all aspects of high throughput experimentation through using machine learning enabled experimental design and analysis. And so I talked a little bit about machine learning to segment and identify features of interest. But in terms of experimental design, Bayesian optimization is one powerful tool that's being widely adopted. And so Bayesian optimization is really popular because it can work directly with the black boxes of deep learning. It doesn't need to know what the objective function is, and it's really robust to noise. So it's popular. The problem is it's really computationally expensive, so it's a bit restricted to smaller design spaces. So to get around this, there's actually a push right now to using Bayesian optimization in dimensionality-reduced spaces. You can use an autoencoder, which is basically like a neural net that takes data and compresses it. Or you can use more traditional dimensionality reduction techniques like principal component analysis. The idea is that you dimensionally reduce the data, and then you do Bayesian optimization on that. Another push that's happening in experimental mechanics and mechanical engineering in general is closed loops between machine learning design tools and automated experimental platforms so that you can rapidly explore large design spaces. And this is really neat because these are actually self-reinforcing. So the machine learning algorithms actually improve the efficiency of the platforms to navigate complex design spaces. And then the information from the data collected on the platforms can be fed back into the machine learning algorithms to improve those. So this is really exciting. It's a positive, nice positive feedback loop with the potential for really improving rapid exploration of design spaces. The next topic I'm going to briefly discuss is using deep learning to create, change, and augment structure. So I'm going to specifically talk about generative adversarial networks, or GANs. GANs were introduced in 2014, and they've rapidly increased in capability. I put up their ability to generate a face as an example. And in 2014, I don't think anyone would have been fooled. And I remember when they came out, and you're like, oh, okay, that's cool, right? Like, you know, I'm not fooled. But you know, now that looks like a yearbook photo in 2019, right? So they've rapidly increased in their capability. So what generative modeling does, in short, is it uses deep learning methods to automatically discover and learn patterns in training data, so that the model can learn how to generate new examples that could plausibly be from the original data. And what GANs do is they're basically a two-player game, where you have a generator that we train to generate new models, and then you have a discriminator that tries to decide if the example is real or fake. And then you train these two together adversarially until the discriminator is fooled about half the time. So typically GANs operate using latent space, which was discussed in earlier talks. Latent space is basically, it's an embedding of a set of items inside a manifold where the items that represent each other more closely are typically positioned closer to each other in that latent space. It's like a dimensionality reduction, it's compression. So mapping to latent space is this dimensionality reduction, and it's being increasingly employed across applications. It's not just a GAN thing. So I'm going to discuss several applications of GANs. Faces are really the commonly known example, and I think it gets across how rapidly these have increased in their capabilities and how exciting their capabilities are. But I'm going to focus on GANs today just due to time limitations and the fact that we've used them pretty widely. So this is not my work. I wanted to also highlight some of the other things because I am just a solid mechanician, so I wanted to also highlight some other fields as well. So examples of GAN applications include anomaly detection and small object identification. The top right shows a really innovative use of GANs for anomaly detection, where a generative model was created of healthy training data, data that we knew was healthy, and the new data was fast mapped to the latent space. And then that new data that you don't know, the unknown data, that was fast mapped to the latent space, was compared to the healthy data in the latent space to see if the manifolds matched. And where the manifolds didn't match were possibly anomalies. So this type of approach can also be used for small object detection. Small objects have been really hard to resolve because they have a low resolution and they're typically noisy. So what GANs can do, and this is obviously broad applicability across many fields, is they can super resolve small objects, making them easier to detect, to make them basically sufficiently large that they can fool the discriminator. And if they can fool the discriminator, then you can detect them. You basically like zoom them up. Okay. So in our group, we've recently used deep learning in a collaboration with the Pollock and Junith groups at UCSB to create statistically realistic microstructures from very limited experimental data, and then Junith touched on that earlier, for high throughput simulations. So when you're looking at high throughput computations in solid mechanics, it requires a lot of realistic grain structures, and these are really, really expensive to obtain. So we have just we're really looking at a lack of data. So developing a way to create statistically realistic synthetic microstructures from experimental data is extremely useful. So here we've developed a GAN architecture to generate new grain morphologies based on distributions of training data. And so for those of you familiar with GANs, we developed a GAN with a Wasserstein or an earth mover metric to recognize the distributions of morphology features from actually functional objects. So we actually trained it on cars and planes and guitars and chairs, right? We didn't even look at grains to begin with. And then we applied that developed GAN to grain morphologies from a three-dimensional experimental data set of Ti64, which is up on that top right. And so our approach actually performed comparably to or better than state-of-the-art on benchmark annotated three-dimensional data sets. And then we also demonstrated this approach by validation against experimental real-world data using statistical shape comparison. So this is pretty exciting. I'm going to talk about another use for deep learning in GANs, specifically in physics-informed super resolution. Whew, I get excited about this and I forget about time. So coming back to the fundamental problem of how expensive and time-consuming experimental data collection can be, we also have to ask not only how can we generate data, but how can we improve the data that we do collect? So GANs are a great means for super resolution. So, leveraging high resolution experimental data and expensive data in a smaller domain to improve the resolution in a larger domain, or inferring a high resolution structure inside a low resolution area. This has been done in other fields. There's two really nice studies using super resolution to reconstruct high resolution turbulent flow data from extremely low resolution flow data. That's actually coming out of Kunihiko Taira's group. He's actually going to be visiting the mechanical engineering department next week if anybody is interested. He's giving a seminar. And then also an example in the thermal sciences, looking at using super resolution for an upsampling factor of 4 on thermal imaging. So in our group, we've used super resolution to augment data of limited spatial resolution using an electron backscatter diffraction data. And the big take-home message here is when we first started this, we looked at the computer vision field, and we looked at the architectures which were absolutely excellent for evaluating optical images. But the thing is that the experimental data in the physical sciences is very different, and it's often gathered using other modalities, and so the images that we get differ in appearance, and they differ in encoded information, like this data. And so to address this, we really had to incorporate, and we had to create a new physics-based loss for network training of this data. So in this case, we happened to use crystallographic considerations because that was what we had. That was the physics-based information we had. And so we found that quantitatively and qualitatively, using our physics-based loss, adapting that algorithm with the information we had, performed significantly better than using the common upsampling algorithms, the commonly used loss approaches, the traditional upsampling algorithms. So we're still at the point where it's hard to draw generalized conclusions, and honestly, those might not exist anyway. But it's becoming clear that the data structures that we create as experimentalists have fundamental differences from optical images, and that the physics-based learning has significant capability to outperform traditional machine learning algorithms in engineering applications. In the final example from our group, I'll discuss the use of machine learning to analyze spectral data. So many fields rely on spectral information to provide fast, inexpensive, and high volume data. They're really information rich, but they've typically been analyzed by scalar features like full width half max or max peak amplitude. So we can use machine learning to evaluate the information inside the entire spectra, and we can use it to evaluate large number of spectra. And so we used it to look at composites that are used in the aerospace industry. And what we do is we basically are listening to the sound. It's fibers inside a matrix. It's high temperature composites. And so we're interested in when the fibers break versus when the matrix cracks. And we're able to hear the sounds that they make, and we want to fingerprint what happens based on the acoustic spectra, based on the sound they make, which would be super useful for non-destructive evaluation and of great interest to the aerospace community. So what we did was we took this into the frequency domain, and then we broke this into bins and integrated it to get just an idea of the energy inside of each bin. And then we normalized it. Oops, sorry. We normalized it because a matrix crack should sound like a matrix crack, no matter how loud it is. And this basically created a fingerprint. We had basically a vector of all these little slices that were normalized. And then we put them into a multidimensional space. And we kind of clustered those fingerprints. And when we did that, we couldn't use k-means. We had to use spectral clustering because we had to consider the connectivity between them. But we were able to get a very domain knowledge agnostic identification of matrix cracking and fiber failure that was only from the acoustic spectra but completely followed the chronology that we would expect. We expect matrix cracking to happen first, then we expect fiber failure to happen at 80% tensile stress, and that's what we see. Also, if we flip out the sensor type and we flip out the sensor location, we would get the same partitions. So it was sensor type independent, it was sensor location independent, and it followed domain chronology, even though it was domain knowledge agnostic. So we're basically fingerprinting damage mechanisms from the acoustic spectra. So machine learning is being increasingly used because it's powerful. There's a lot of low-hanging fruit. We're not good as a community yet about benchmarking these. And current frameworks get wildly different answers. We took 4 frameworks out in the literature. And we tested them on one single data set, and they got wildly different answers. So independently, they were all like, this is right. And you could read the paper, and you're like, oh, yeah, that makes sense. So we were curious. So we took the 4 frameworks, and we put them on the same data set, and there was a 0.0 match between them. So this kind of highlights the need for benchmarking, and other branches of machine learning are fantastic about benchmarking. So we really need to have open source sets where we can benchmark these frameworks and we can build trust in these frameworks. Things like, for the acoustic emission example, we're building up benchmarking frameworks using pencil lead brakes. Very simple, very consistent, and you can relate them back to the angle that you were breaking the pencil lead at. So it doesn't have to be complicated, but it needs to be consistent. So that's it. ML applications were at an impasse. We needed technology to capture, storage, and process data. We got it. It's really exciting. We need to have extensible frameworks. We need to have physics-informed frameworks. We need to be careful because you can have patterns and they can look beautiful. It reminds me a little bit of finite element software, where like when it first came out and you go, oh, these colors. But it, right, it's exciting and people are super excited about it. But getting a pattern is not, it doesn't mean it's valid, right? Machine learning is incredibly powerful, but with great power comes great responsibility. So for machine learning to build the same trust as other computational approaches, in engineering, we need to have meaningful, in science, we need to have meaningful connection back to the underlying physics. We need to build physics into the architecture. We need to build physics into the learning processes. And we need benchmarking data sets to check ourselves. So that is it. Thank you.
I'm just trying to play your slides.
Oh, you have my slides. Okay, cool. Is there a pointer or a...
Cool.
Turn on your hand. Cool. Yeah, people always think I'm like spastic when they're trying to like point at the screen.
All right. Our next speaker is Stephen Wilson from Department of Materials. Let's give him a welcome.
Great. Yeah, thanks very much for the introduction, Tim. And thanks, William, for inviting me to come and talk. I've learned a lot. This morning, I learned that you guys are going to listen to this talk, and your brains are going to process the lack of detail that I put to you, and you're going to rapidly infer that I don't know anything about machine learning or artificial intelligence. So on Claudio's scale, I'm a -1 here. So Yeah. But I do hope to articulate a problem that we see in new materials development, and in particular in the domain of quantum materials, where there's really a mandate to try and accelerate materials production in terms of materials that can host quantum information. So, in terms of what I want to try and talk to you about today is, I just want to first, introduce, there's a center on campus called the Quantum Foundry with a mandate to try and develop new quantum materials for quantum information processes. And I want to try and articulate, what we're interested in. I'll give a brief introduction to what quantum information is, since we have such an eclectic audience. And then I'll just try and motivate what we think the roadblocks are, really, in this sort of desired acceleration in materials development to address the challenges. And then at the end, I'm going to introduce some beautiful work that Linda Petzold and Zhenjun, who's here, have been doing, trying to tackle some of the problems, which is sort of the paucity of data. Okay, so first off, we're all familiar with the traditional definition of a foundry, right? Coming from the original Latin, where we think about metal being poured out, and then sort of the modern age, for digital electronics, we think of semiconductor foundries. Actually, some of my colleagues think of this before they think of that, which is interesting. It really is telling of what field they work most in. And so we're down here, right? We're the quantum foundry, which is a cool sounding name. But the idea is we're not actually producing materials to ship off to, industry or anything like that. We're actually just trying some fundamental materials exploration, right? Trying to develop the next generation of materials for quantum information science. And this is a center that's funded by the National Science Foundation. Okay, so the premise of quantum information, just very briefly, for those of you who've never heard of it, is that, the idea that you can basically access different types of, more types of information if you can, instead of treating electrons, for instance, as particles, you treat them as waves. So if you think about low energies and small distances, the electron, you can define a wave with a well-defined wavelength. If I can make some sort of special point in time, or I can look relative to a different wave, I can also define a phase relative to these two, also intrinsic to the electron, right? And so if we treat these electrons as, or for instance, it could be photons or other particles as quantum objects, then we can use these probability waves that we can mix and entangle and encode a new type of information, which we call quantum information. And just to try and illustrate this, so I can think of two separate electrons. These are two separate waves. They can interact, so I can think of what's sort of called a product state of these two waves. And then I can entangle them, and I can think of some well-defined superposition of these product states, okay? So the way I think about this is I can think of my children, okay? So I can think of one of my children at any given point in time, at any point in space, right? That I can define their state as either being, well-behaved angels, or they're disrupting my life and being gremlins, right? And so this is some complex superposition of these two states. I have two such children, my daughter Mercedes and my son Chase. And I can think of them as a coupled system. They can interact with one another, and such they can organize themselves such that I can have an entangled state of my children such that I can guarantee that if one of them is behaving, the other is not, okay? So if I'm in a room with one of my children and I actually localize this wave function by observing it, I can see my daughter is behaving, and even though my son might be in a different room, I know I need to go check on them because he's not behaving, okay? So this is, one way in which we can, in the concept of quantum information, okay? And so this is the promise of using these types of information, is that these, for instance, in the field of quantum computing, if you can make bits that are now based on these sort of quantum concepts, you can realize large gains in, for instance, a number of different applications that I think people are searching for more. But just, for instance, factoring large numbers, cryptography is a well-defined example, efficiency optimization problems, but also, more naturally, you can think about simulation of quantum materials or quantum systems themselves. Furthermore, the applications of quantum information extend to sensing, for instance, the field of quantum sensing, which is really like an ultra-high precision field of metrology, right? Well, here's an example. Some of this is already being deployed. We're for Lockheed Martin, basically using these sort of highly coherent two-level systems using nitrogen vacancies and diamond to try and make a location determination just based off the Earth's magnetic field, absent GPS. Okay, so there's for quantum sensing, there's actually a lot of applications already being deployed. And so, the premise of the Foundry and a lot of the materials research in the domain of materials for quantum information is really based off, like historical perspective, right? So if you were to look at the 1948, you look at this giant machine, this IBM selective sequence electronic calculator, This is a huge thing that's really based off of a beautiful device, actually, electromechanical device of a vacuum tube, right? And so, you have this large physical array of all of these, but at the same time, you had these guys working on developing the transistor at Bell Labs. And really, this innovation in trying to develop the transistor was really based off of some material. Well, okay, obviously, the idea was unique, but it required the underpinning material, for instance, of ultra-high purity silicon, ultra-high purity germanium for semiconducting materials to be developed, okay? And this picture is also from Bell Labs. And so, the idea now is we look at the state of the art in quantum computing, for instance, and here's Google's quantum computer at Google Quantum. And this is a computer with 50 qubits, okay? It's a large device. And so the idea is that, for scalability, eventually, we're going to need some breakthrough in the elegance of materials to try and address the scaling problems of this, to try and scale the number of qubits. And the idea is, there's a number of different qubit platforms that have been proposed, and no one really agrees yet on what the well-defined future is going to be, okay? And the challenge is really that these quantum states that are generated via these number of different qubit options basically want to couple to the environment and decohere and lose their well-defined phase or wavelength information. And so, the challenge that we're trying to address is how can we engineer materials that protect this coherence of an entangled state, for instance, and then, once you do that, how can you reliably read, write, and store what we would like to think of as sort of fault-tolerant entangled states? Okay. All right, so here are the roadblocks as I see them for the materials development. And since I'm in the materials department, one of the major roadblocks and rate limiters is really the synthesis of new quantum materials that have been predicted. And the reason being is that I would say in the past 15 to 20 years, there's really been major breakthroughs and advances followed by a proliferation of theoretical predictions of new materials that can address some challenges that are being put forward in the quantum information space. And so this is good and this is bad, okay? I mean, the good part is it's great that we have theoretical frameworks that can allow us to try and say, okay, this material will work for this, okay? It's bad is that, these are often wrong and they need to be vetted, right? But the actual process of making a new material and vetting these predictions is very long, experimentally, okay? And so here's an example. This is a bold one, right? I found this one just on my Google Scholar feed the other day. High temperature superconductivity and some doped boron nitrogen clathrates, right? Okay, so it looks like they've discovered this, right? It looks like I'm going to open this paper and wow, I'm going to see some high TC. But no, this is a theoretical prediction, right? And so there's this proliferation of these papers. They actually often also use the word discovery. Predicting new materials with fantastic properties. And one would like to try and test some of them. But, so how do you do this, right? So if these materials don't exist, right? So someone has to figure out a way to make them, right? Or someone also should do some initial estimate whether or not it's physical to make them. Hopefully they've already done that. Okay, but in the synthesis process, here's the part that maybe you won't believe, is that actually making a new material in the solid state, and especially in the regime of like inorganic crystalline materials, it really is, even today, really relies predominantly on the scientist who's making it intuition, right? On where to start your synthesis process, right? And this often relies on previous successes for similar materials, okay? And the reason is that there's really a tremendous variability in synthesis approaches, techniques, and also timescales for making new materials in this domain, okay? And then there's this other challenge, especially in the realm of quantum materials, is that how do you know that the material made is good enough? Meaning, oftentimes what we're looking for, I'll use superconductivity as an example, can be a very delicate quantum state that's highly sensitive to disorder, and that disorder can sometimes be not easy to quantify in the material you make, right? So let's say you make the material, and then you characterize it. How do you know that you made the material good enough, right? So these are just challenges I'm articulating. All right, so here's an example. This is from one of my students' logbooks. I asked her to basically make a graph showing some workflow of how she made a material. So this is how she tried to make a material. It's a gallium niobium selenide, which is a material that's been looked at for hosting what's called a magnetic skyrmion phase, something that's potentially useful for low-power memory applications. But it's like an emergent magnetic state. It's basically what they call a topological magnetic defect. They can interact and self-organize, and they're somehow protected from annihilating one another. But you can see, it's the process, this is a fairly simple workflow, right, for materials, but you can see there are all sorts of details that aren't always captured, right? So she has some gallium, so some selenium, niobium, and they have starting reagents of different forms, and she's basically just cooking things, right? So she's putting them together, mixing them together, sealing them in a tube, grinding them, heating it up, it's grinding them together, sealing it in a tube, and then she's firing it under a very well-defined heating sequence to try and react and make the material, okay? And then she has to take it out, grind it up, and then she has to do X-ray diffraction, which is how we'll tell whether or not that's our first cut, right? Did we get the material we thought we were supposed to get? And do we make other materials along with it? And so this whole process takes something like, depending on how long she has to fire it in the furnace, it can take about several, let's say a week, start to finish, right, for one go. All right, and it's only at the end of that week that you know whether or not you made something or not. Okay, and then you take that input and you can go adjust based off of intuition or what you've kind of assessed you made, and try and close it on the material you want. That's just an example, okay? And here's just another example to highlight some complexity, right? So like, let's say there's this mixing process where she's grinding things in a mortar and a pestle, right? So she's putting things literally in something like this, right? And she's grinding them up and then putting it in a tube and reacting it, okay? Okay, so that works often, but we have other materials where sometimes when you do that and you do the same process, you don't get what you want. But if you'd mix them up in a ball mill, for instance, where you had much more, where you had this sort of subtle, what they call a sort of mechanical alloying already that's happening at room temperature before you fired it, then you get the phase you want. And then similarly, sometimes you have to melt and pre-react things to mix them. Sometimes you have to mix them in solution. So there are many different variables that can go into these different components of the process. So I'm just trying to highlight the complexity of why this is a difficult problem. And then the other bit is that the morphology of the material that we're actually studying matters as well. Okay, so depending on the science that we want, or, in some cases, sometimes making a powder of something is good enough. Sometimes you need to grow a large single crystal to try and assess the physics you need. So that's an additional challenge. How do I take this and turn it into something like this, right? These are all tiny individual crystals. I have to somehow melt and recrystallize them into one macroscopic crystal that I can then study. Sometimes the interface matters. I can have a system like this as graphene, right? If you twist them relative to one another, you can get wildly different quantum states that appear. And sometimes you don't need a single phase material. Sometimes for the physics you want, you need to make interfaces between dissimilar materials. So here's just a thin film heterostructure. And each of these are made via different tools, and each of them are targeted, each trying to make a quantum state with some type of protected coherence, okay? And each of these can all have different parameters and challenges to growing them individually, okay? So this is why it's somewhat of although it seems kind of simple, it's somewhat of a grand challenge because of the diversity of data types and techniques that we can get. All right, so how can data help? All right, that's why I'm here. Maybe you tell me. But one of the main things that we've identified in the Foundry is that community synthesis data of different materials is really scattered and not recorded well, and failures, importantly, are not reported, okay? So the example I showed you for my student Julia, who made this material, she tried maybe 10 times, and the one that worked was the one she reported. But she doesn't record or publish anywhere what came out of all the other attempts.
Why can't you publish the failure?
Because, well, there's just sociological. You get no credit for publishing failure, and it's a lot of work.
90% of my papers are failures. I think we have different cultures.
Yeah, there's not to say, if there was a system to incentivize someone publishing, just running a process and reporting what resulted from that process, then I think there would be people doing that. But there's no incentive right now to do that.
That seems like a fundamental problem in your field.
Yeah, I think one can make that argument, yeah. So, okay, let's see here. And so one of the things we wanted to try and see is, okay, first of all, to start with this sort of problem of having this sort of scattered data, to ask the question is, can data be curated? And can machine learning or AI I don't know the difference between machine learning and artificial intelligence, but so I'm sort of, lack of confidence, I put a slash there. Can one of these two techniques be leveraged to accelerate the time from the material idea conception, meaning a theorist or someone thinks that this material can do it, to growing the material and testing it, okay? And so the strategy for the Foundry currently is Linda Petzold and her team are trying to use natural language processing for looking through the literature and curating the synthesis metadata for 5 minutes. Okay, great. For successful synthesis of materials, okay? And so that's basically looking through a bunch of papers, basically just grabbing them in an automated way and grabbing out the synthesis procedure. And then the second is the Foundry is creating a data curation portal for the Foundry data, which, big picture-wise, we'd eventually like to open up to the community. All right, so Linda and Jianjun, for instance, what they've been doing is they've developed the machinery to grab a paper, and it can now, by training models, it can grab the paragraphs that involve the synthesis of the material, and then their natural language processing can then grab the steps for synthesizing the material, and they can diagram these sentences and get the actions and reagents and all of these things, operations, and then they can turn this synthesis procedure into like a graph, okay, a workflow. Okay, and then they can go through and they can do many papers, and they can basically create a database based off of this harvested data, right? And so they've had success in doing that, and they've created, okay, I'm using, this is Linda's words here, so created the only procedural text database in the material science domain that contains the sentence type, the entity mentions, and the relationships between them. Okay, so here's some comparison with other data sets. But the dream here is to create an ever larger database for direct reference eventually for machine learning techniques to try and help direct starting synthesis attempts for new materials. And so, in other words, a cookbook for quantum materials. Okay, and so I think our next step is to try and scale the data size there. And so what we're trying to do in parallel is that there's a web portal called the Quantum Data Hub where Foundry researchers, when they make a new material, for every sample they make, whether or not a success or failure, they input this type of workflow into a procedure editor, and we capture this in the Quantum Data Hub, okay? And so this is basically, it's a data curation portal that's capturing the synthesis metadata along with it, and then it stores the characterization data associated with each of these samples and outcomes under a unique sample identifier. And so this is being led by OK Altentis' team at San Diego. Okay, I got 2 more minutes. Okay. And so basically, you make a sample, you say how you made it, you can store any characterization data under that sample, okay? And then you can share it, and it also provides some provenance for any sample that you publish, okay? And you can also link the analysis in the hub as well. And so the dream, of course, is to then take all these action graphs that are eventually harvested by Linda's team and fold them into the same resources, for instance, from the literature with some sort of literature reference, as well as all of the new successes and failures from the Foundry, and maybe eventually from the community who wants to use it, and fold it into the Quantum Data Hub. And this hopefully can be some combined resource for eventually trying to use some type of machine learning techniques to help accelerate the synthesis of new materials. And so with that, I'll just leave you saying, I think that the materials domain, in particular the quantum materials domain, is a very target-rich environment for using these techniques. No one's really using these to try and guide experimenters currently. Because right now the current process of developing a new material is really slow. And there's this iterative feedback loop that's being expected by everyone, that you have a theorist predicts it, a computational person tells you, does some quantification, and then an experimentalist has to make it and measure it, okay? The make it part is like the rate limiter in this loop, in my opinion. And we're, of course, open to any ideas you guys may have. And yeah, I already went over my approach, and thanks very much for your attention.
Yao, can you hear us okay? So
yeah, I can hear you guys.
We can see you.
I think I'm opening my I've already opened my camera. Mhm. Maybe same system. Still cannot see me. Okay. But maybe
no.
it's fine.
or you can share your screen and let's see if we can
Okay,
see
sure,
your
sure.
screen.
Okay, sure. Let me see. Oh, but I'm still disabled to share here.
Let's see.
Host disabled attendee screen sharing.
Yep. So we'll have Laura to just give me 1 second.
Okay, sure. Oh, it seems like it's okay now.
Hey. We can see that.
You can hear me, right?
We can see you and hear you. You want to put it in full screen?
Okay, sure. Slideshow. Okay, everything is okay.
All right, we're good to go.
Okay, sure. Thank you.
All right, so welcome everyone. Our final talk is incoming assistant professor who is joining us early here with a remote talk from electrical and computer engineering. Thank you, Yachin. Go ahead.
Thank you for the introduction, and also thank you very much for the invitation of the talk. I'm super happy to introduce about my recent two works, Robustness of Variant Transformers. So I'm an incoming assistant professor, and I will join next January 2023. And currently, I'm still at Google. Okay, so first, what is the robustness in this talk that I want to introduce? So the first one is out of distribution generalization. So imagine that you train a classifier, and then all the available training data is a stop sign in sunny days. And then, but when you test your model in the real world, you might run into the scenario that the stop sign is covered by some snow. And then we found that the classifier will fail to work in these unexpected weather conditions. This is what we call as out of distribution generalization, because there is a distributional shift. The test distribution is not perfectly aligned with your training distribution. And ideally in real world, we hope our classifier can still work under these scenarios. And then another type of robustness that we are focusing on in this talk is adversarial robustness, which is that you will optimizely to generate some adversarial perturbation onto the original image. And this adversarial perturbation is generated specifically to attack your model, fooling your model to making an incorrect prediction. So as an example shown here, the generated adversarial example, the panda still looks similar as panda to humans, but the classifier will misclassify it as gibbon. So the adversarial robustness is kind of like the adversary, we can just manipulate the generated adversarial perturbation with regard to the gradient of the loss function, and then to specifically attack your model. And this is also very dangerous when we deploy our machine learning systems in real world. And then the next question, because, okay, we know robustness is important, but why do we have interest in variant transformers? The first and the most very direct answer is that the variant transformers has achieved great success in Veda. And some existing work have already shown that the variant transformers can have better robustness compared to the CNN, the most popular networks in variant tasks, under some scenarios at least. But what I would say is that, okay, so other than the pretty nice performance of variant transformers, what is pretty important is that the transformer architecture has been widely used in the language, in the text domain. And then the vision transformer has successfully been applied to some vision tasks. So it's kind of like plays a role of a bridger to connect different domains and give us like this kind of unified architecture provides us great opportunity to do some multimodality stuff or try to connecting all the research work in previously independently studied in both domains, but right now we can just have more connection with. Okay, and then the next question, because okay, how can we study the robustness of vision transformers? So in order to answer this question, I would like to first introduce some of the background of what is convolutional networks and how vision transformers work. So in standard convolutional networks, when we do the image classification task, we will just feed the whole image into the same model. And then the model will just process the image with some convolutional neural kernels, and then the output will be the classification of the image. So in contrast, the vision transformers, because it's originally proposed for processing the text tokens in a sentence. So then in order to process the classification task, we will divide the whole image into some non-overlapping small patches. And then we will feed a sequence of these image patches into the transformer model, and then to perform the classification task. So you can imagine each small image patch stands for a token in a sentence. So then the transformer model is just looks similar as the model used in the NLP large language models, but the input is just a sequence of image patches. So because of this like a very special patch-based architecture trait of vision transformers, so we studied the robustness of vision transformers along two lines. The first line is patch-based transformations, and the second one is patch-based attacks. So let's first just focus on the patch-based transformations. So here I show some images transformed by these patch-based transformations. And can you tell the true semantic classes of these transformed images out of 1,000 classes? I guess it's pretty challenging. And this kind of indicates that, okay, the features preserved in the small patches in the images, they're not indicative of the semantic classes to humans because humans cannot recognize them. And here are the clean original images. And the patch-based transformations that we perform here is patch-based shuffle. That is, we will randomly shuffle the patches within the image. And patch-based rotate, that is, we will independently rotate the small patches. The rotation degree can be pretty large, like 90 degree, 180, or like 270. And the patch-based infill, that is, we will remove the patches in the center of the image and infill edge with a boundary or background patches. And then the next question becomes, do vision transformers rely on the features preserved in these small patches? And the answer actually is yes, because when we test the vision transformers on these like patch-based transformed images, we found that the models will still classify these transformed images as original class with very high confidence. So this indicates a discrepancy between models and humans because humans cannot identify these images, but the models still just classify them as the original class. Should we worry about this discrepancy between models and the humans? So to answer this question, we train the vision transformers on the patch-based images. So in this way, the models can only see the features preserved in the small patches during training. And then we test these models on in-distribution ImageNet 1K and several robustness benchmarks without any transformation. They're just the standard, very standard images. And here is the result on in-distribution data. So the blue bar stands for the model trained on clean original images without any transformation. And the red bars stand for the models trained on each type of patch transformed images. And then if we compare the red bars with the blue bar, we can see that there is only a small in-distribution accuracy drop. This kind of suggests that the features preserved in the small patches, they're still useful, because if models just rely on them to make a prediction, the model can still give us a very high accurate in this distribution classification. And then we do the same thing, test the models on out of distribution robustness benchmarks. And we found that the models trained on the small patches, they suffer from a much larger accuracy drop on this out of distribution robustness benchmarks. So this indicates us, okay, the features preserved in the small patches, they're useful, but they're not robust, because if the model only sees these features during training, the model cannot give us reliable prediction on out of distribution benchmarks. Okay, with such kind of understanding, the next question becomes, how can we prevent the models from relying this kind of features, unrobust features? And if we do, can we just improve their robustness? So the core idea of our method is to use these patch-based transformed images as a negative data augmentation. So these patch-based transformed images, these negative examples, they capture those non-robust features which humans cannot recognize them at all. And then we want to teach the model to give us different feature representations between the original clean images and these negative augmented images. So this is complementary to the traditional, which we call it as positive data augmentation, like a crop, flip, or rotate. This positive data augmentation, they still preserve the original semantics. And then the standard way to do the positive data augmentation is to encourage the model to give us similar feature representations between clean and positive data augmentation. And this idea can be nicely achieved by maximizing the loss function shown here. So the first term is a cross-entropy loss, which is to perform the standard classification task. And then the second term is a contrastive loss, which is to infuse the robustness into the models. The general idea is that we want to encourage the clean image and the positive examples to share similar feature representations, but the clean image and the negative examples to share very different feature representations. And here are the just one of the results that we're showing here. We apply the negative data augmentation on top of the positive data augmentation. And we see that the negative data augmentation is truly complementary to positive data augmentation because they can still consistently improve models' robustness, especially on out of distribution robustness benchmarks. This is pretty exciting because people are used to generate some positive views to encourage and infuse robustness into models. But here, by understanding the robustness of the variant transformers against the patch-based transformations, it turns out to propose a new direction that is negative data augmentation to capture some non-robust features and then to encourage the model to become more robust. Okay, other than the patch-based transformations, another line of our work is focusing on the patch-based attacks. So what are patch-based attacks? So in this work, we mainly focus on two types. One is patch-based natural attack, and another one is patch-based adversarial attack. Let me remind you how variant transformers work. So given an image, we will just divide the image into non-overlapping small patches and fit it as a sequence into the transformer models. So if we randomly sample one small patch, for example, the showing in the red box, and then if we replace this original small patch with some natural corruption, for example, we can just replace it with a Gaussian noise. And then the generated image is patch-based natural attack. In contrast, if we replace the random sampled image patch with some adversarial perturbation, then the generated image is patch-based adversarial attack. So here is an example of both attacks. So visually, if we just Gaussian noise, it seems like these two types are very similar. But note that the adversarial attack are just specifically optimized with regard to, according to the gradient with regard to the loss function. So it is designed with intention to fool your classifier to make a wrong prediction. Okay, and then let's see how the models perform on these patch-based attacks. So in this table, we show the falling rate of the models. And then the lower falling rate indicates that the model is much more robust. And then we compare CA models and the VIT models. We ensure that all the settings are fair, so we can give a clear picture of how the model's performance is. So under naturally corrupted patches in the middle of the table, so we can see that the variant transformers is much more robust than CA models because they have lower falling rate. But more surprisingly, we found that under adversarial patches, which are specifically designed to fool the models, we find that variant transformers are actually less robust than CANs. So this different phenomenon, just is pretty interesting to us. And then we just want to develop a deeper understanding why the variant transformers sometimes more robust and sometimes less robust. And then to this end, we do some visualization of the attention mechanisms in variant transformers. So as the example shown here, the top image is a clean image, and the bottom image is a corresponding attention map. So we can see that the model can successfully attend to the object in the image to make a classification. So when we add some naturally corrupted patches onto the original images, so here we display different scenarios, like the corrupted patch is in the background of the object, or the patch is on the background, on the object, or we apply multiple patches onto the image. We see that the variant transformers actually effectively ignores these naturally corrupted patches. So you can see that on the attention map, the attention on the for these locations of these naturally corrupted patches are pretty dark. Dark means that the model doesn't attend to these positions to make a prediction. And then in contrast, when the adversarial patches are applied to the image at just the same place, and then we find that the attention map has a big change. The attention map has been fooled to focus on the adversarial patches. And then you can see that only the adversarial patches part are highlighted, are attended. That's why the variant transformers are just so vulnerable to adversarial patches, because it's easy for the adversarial just for the model to attend to these adversarial patches. Okay, so here our understanding reveals that it's the attention mechanism that effectively ignore naturally corrupted patches and easily fooled to focus on adversarial patches. And then the next question is, what's the key component in the attention mechanisms leading to such an adversarial vulnerability? And then here, actually the attention maps in the attention weights in variant transformers are computed, the last layer is a softmax function. So we will make sure that the attention weights on all the patches, the sum of the attention weights will be 1. And then we can see that if the input is a clean image, the distribution of the attention weights are much smooth and just focus on the object. However, if the input is just attacked by one adversarial patch, and then you can see that attention weights will be fooled to be skewed to the single adversarial patch. And that's why the model becomes much more vulnerable, because as long as the model attends to the adversarial patch, it's much easier for the model to make a mistake. So we should stop this kind of scenario to happen, because like if you generate one patch to attack the model and then stick it onto the image, and the model will just be fooled. And then because with such kind of understanding, we propose a method to smooth the attention weights via temperature scaling. So here you can treat Z as the input of the softmax function. And instead of use the standard softmax, we add a temperature T here to smooth the attention weights alpha. So in general, if we increase the temperature T, like the T is larger than 1, and then the attention weights will be more smooth. So if T is like, for example, infinity, and then the distribution of the attention weights is more like a uniform distribution. And here is the result. The x-axis is the temperature, and we can see that we gradually increase the temperature. The y-axis is the left y-axis is a clean accuracy, which is indicated by the blue line, and the right y-axis is the fooling rate. Lower represent the model becomes more robust, which indicated by the red lines. So we can see that as we increase the temperature, we don't suffer from a clean accuracy drop significantly, but we successfully improve the model's robustness against such adversarial patch attacks. Okay, so here is a summarization of this toolwork. For each of the direction, we start with some understanding of how variant transformer works. And inspired by these understandings, we propose the corresponding methods to improve models' robustness under out-of-distribution data or under adversarial data. And then the key point here is that the variant transformer is just as a starting point, plays a role to connect different domains. And in my future directions, as long as I arrive at UC Santa Barbara, one of the key themes that I want to continue working on is the robustness in multimodality models, how to encourage the interactions between different domains and further improve models' robustness. So if you have any interest in any topics shown here, feel free to contact me, and I'm very open for collaborations. Thank you.
Thank you. All right, so I'd like to invite all our speakers up to join us for some Q&A and a little discussion. Some microphones, maybe one for them, and then I'll take one to the audience if there's some audience questions. But I don't know, I guess I would just like to start with just a basic question. I mean, it's wonderful to see all these different perspectives from multiple different departments. And so maybe I would just like to start with just a quick reflection on some of the things you heard from the other speakers here, and interesting opportunities to build from there as an institution.
So, shall I what to mention? Actually, I really enjoyed all of your talk. So I worked on time series prediction as well before, so I didn't talk about that today, but your classification model on those time series, those are quite relevant. And material synthesize, I think those are also very interesting questions. So I mentioned molecule generation for drug purpose, but I believe the same type of generative model that can be applied to material as well. But in order to make that work, we perhaps need to separate into several stages. Like one stage is really we have the material, can we predict a property out of that? Maybe if you have data, we can try to use some classification regression model for that, or neural network for that. And then once we have that, we can use the similar deep generative model to generate maybe the crystal structure for the material. And the other part which I find very interesting is the synthesize, because that's the part I know some people are working on that for drug as well, but in particular for this material, it seems it's the procedure, so it may be similar to we have code generation in NLP in AI. So where in that case we want to find steps, procedure. There are certain operation space, finite operation space that we can vary. It might be a large search space, so we can try to limit it to use a machine learning algorithm to guide it to in the small space. Okay, so that's my reflection on the other.
That's great, thank you. Yeah, I don't know if anyone else wants to. We don't have to go everyone. By the way, I think we have about 10 minutes, we said, for someone's discussion, just so you're aware.
So what struck me was how incredibly cool your guys' stuff is. I felt like, especially coming after you, I felt a little like, whoa. But also just how similar the challenges and opportunities are in terms of everything's a feature vector, right? I mean, in terms of, my take on your comment about AI versus ML versus DL is, and I could have this wrong, and please correct me if I do, is that AI is kind of mimicking human behavior. ML is when you extract the feature vectors yourself. And DL is kind of when you are the feature, or you're putting in images, you're putting in information, and then those features are chosen for you. A little bit. But that the challenges and like the opportunities for ML, DL, which seems to be what we're really talking about today, to serve as a disruptive.
We're laughing at you. We don't know what DL stands for.
Oh, I'm sorry. Deep learning. Deep learning. Sorry. But I think the opportunities for, we had mentioned like low-hanging fruit, the opportunities for ML and DL for those to really like paradigm shift what we're doing is pretty exciting. And there's a lot of really common similarities for that. So I think we can learn from each other.
Yeah, I mean, through the talks throughout today, I was really impressed on sort of what these machine learning models can do. I think one of the things that struck me as I'm watching this is, like a lot of the like really sharp results are on like image data, right? Like really well-structured stuff. And like in the materials domain, I'm just thinking like the tremendous amount of resources that have to be committed to actually try and structure your data in such a sharp way, right? So that it can be machine learned from. So just trying to think about how to do that. That's an interesting challenge. But yeah, I mean, I've learned a lot. It was great. And I like your simplified model for predicting when people will die. That's
So, I mean, in my research, I use machine learning just as a tool, just as something that is given to me. It's a black box. I throw some stuff in, then something comes out, and then, but then I have to figure out whether it makes sense. Okay, that's my challenge. But what I was impressed at today, I had no idea that there was so much going on this campus, and so, now when I think about new problems, and I don't know that I have the tool ready. Maybe there are people here that I can talk to. So that's what I got out of this myself.
That's great. Yeah, if you're online, you want to add anything?
Oh yeah, I mean, can you guys hear us?
We can hear you.
Hear me?
Yep, absolutely.
Okay, sure. Yeah, I think it's super cool because like my background is mainly focused on like the machine learning, and I try to improve the robustness of machine learning in some very standard machine learning tasks. And then during these talks, I feel like, okay, there are just tons of opportunity for us to collaborate on like different areas. Yeah, some like the discovery of some materials, I think is pretty cool. Yeah, and then like I feel machine learning is definitely a great tool for us to expand it to different applications and different areas. Yeah. Mm-hmm.
That's great. So how about some questions from the audience? Anyone? I'll start.
Good afternoon. Thank you guys so much for presenting your research. My question was for you, Claudio. I know that it was kind of like a little aside, but you were saying that the Korean databases were much easier to work with when you were addressing healthcare issues. And I was just wondering why that was the case, and is there any best practices from the way they structure their data that we should replicate?
No, I think that first of all, they don't have as much bureaucracy exists in the United States. And also it's a more centralized system. So for example, one of the things that is done all the time I learned, but it's not done all the time in these medical studies, is that when you follow patients, you want to follow a patient through a year or 2 years, and then the patient disappears from your records. I don't know, maybe he moved to Las Vegas, or maybe he doesn't like your hospital anymore and goes to a different hospital. And it was kind of shocking to me that the assumptions that is made in all of this analysis of medical data is that this loss of patients, which they call censoring, is completely random, right? In Korea, they can figure out who's dead and who's not dead because it's all centralized in some social security system that they can easily access. So, for example.
Thank you. Yeah, so my question is for you, Professor Lei. So why do you think that your algorithm can have a higher diversity than the previous ones, like accept-reject sampling? And I also had a question more generally. As we see all of these great successes in ML, what do you think are going to be the biggest barriers to entry in the future? So if we want to apply all these great things, what do you think are the biggest problems in the future?
Okay, cool. Two questions. So, well, why it's more diverse? I guess if we directly generate, so that's generation is always this exploration and exploitation trade-off. So, the sampling is more exploration, and I guess the previous algorithm perhaps focus more on the exploitation part. There's always a trade-off. And regarding to your next question, I think the most important is finding the right problem to work on, and perhaps team up with right people, like folks here.
Hi, thanks. Very interesting talks. I just had a follow-on question from the last one. So you have an MCMC algorithm, and obviously it's quite a challenging design for the Markov transition kernel. And I wonder what the trade-off there was with the tempering rate or the annealing rate and your acceptance rate in your Markov transition kernel design, because you had to do a lot of learning to learn that transition probability. And I wonder how well that mixes in the Markov chain space.
Oh, that's a great question. So, yeah, it's really about the details of the convergence of the MCMC algorithm. What we did is we have a proposal which is learnable. So we have some parameters that can be learned from the data itself. And through the sampling process, we are generating some candidate molecule. Some of them might be better, some of them might be worse. So we use those as a kind of augmented data, self-training data to train the proposal itself. So in this way, we can have adaptive proposal, which will be getting better and better over time. We have some mixing plots, which I can show you later.
Hi, my question's for Dr. Daly about one of the comments or one of the things you had on your summary slide was that we needed to build physics back into architecture. And I'm in social science, but I feel like this is something that my advisor says to me too, like you have to have the theory. But it seems to me like they might, it might be different ways of approaching, inductive versus deductive. So I was wondering what your opinion is on that. What's the best practice? How do we do that?
Oh man, okay. That's a really good question. Sorry, little frog. And I like your point of saying it's more like theory and the information you have. So for us, that information is physics, right? But to be more generally stated, it's the information you have, right? You can put it into loss functions. I mean, we're learning how to do this by collaborations with machine learning and data scientists because it's not our field of study, right? You build it into the learning processes, into the architectures, and that depends on what approach you're taking. It's very depending on, and I mean, for example, we use GANs, and so we build it into the loss functions. But I would assume, I mean, if you're using, and we rely heavily on GANs right now, but I assume if you're using different approaches, you would build it in differently. But we have consistently seen that when you build in the information you have, you're basically narrowing your available space to your available manifolds to like what is realistically possible given your constraints. And so that just makes everything easier, right? And it makes you more accurate. It makes the machine learning more accurate. Yeah.
All right, let's thank our wonderful speakers.
Because we're running from late lunch, so we're gonna just take a relatively short break. We have coffee, cookies outside. So please take a 10-minute break, and we'll come back for our last session. Thank you very much. Awesome. Thank you so much, team. Thank you. Yeah, I think it's I really enjoyed the discussion. It has been wonderful. Yeah, thank you so much.
I'm Marcus.
Marcus, nice to
I'm
meet
actually
you.
working with Chandra, and Rich just happened to be here.
Oh, great.
I'll be back for sabbatical.
Excellent.
In spring. But what I wanted to ask you is, as the organizer, are the slides of the keynote?
Yes.
They're going to be making it available?
We already have them. They are already available. Go to YouTube and search Center for Responsible Machine Learning. You will see the recording.
I know.
Yes,
I already know.
yes.
Okay, so I didn't just realize you
Yes.
Oh, that's great.
So you can watch that tonight if you want to, just review anything.
Just the video or also
the video.
Their talk slides?
There are
the speakers going to make them available?
So we don't know. There were few speakers who haven't sent us slides, so we're gonna wait on those. But
you're going to make them the ones that you have. You're also going to
we can try to put that on our program page. But the video is the easiest because they tend to be a little bit.
Oh, thanks.
So let me introduce the session chair for next session. So our next session will be on AI and social science. And we're very honored to have Professor Kyle Lewis as the session chair. So Kyle was the former chair of the Technology Management Program and is a full professor, also recently got the endowed chair in the technology management. So Kyle will be giving us introduction for our next speaker.
Great, thank you. All right, thank you. Oh, yes, we can't lose that. As I was looking at the speakers for this session and the title of it, it was really entitled Machine Learning for, or being done by, people in humanities, arts, and social sciences. And it struck me that we really need to have the arrow go both ways, that it's machine learning that is being used by researchers in these areas, but there's also lots of research about what happens to humans who use these tools. So we're going to have two speakers, one of whom speaks about one and the other who speaks about another. So we'll start with Simon Todd, who is an assistant professor in the Department of Linguistics, and he's a computational psycholinguist, which is something I hadn't heard of. It sounds super cool. And who focuses on how the small-scale cognitive processes associated with in-the-moment listening has large-scale, long-term implications for linguistic knowledge and behavior. So really bringing the listener in is something that I hadn't seen before, and really bringing behavior in is something that I think that the people in this group are very keen on doing. So Simon, please take it away.
Thank you. I am very excited to be here today to tell you a little bit about my research. I want to acknowledge to begin with, though, that it's not just my research. What I'm going to tell you about today is part of a larger project that's been going on for a long time with a lot of people and is still going on, and you can see them here. I want to begin by answering this question of how is machine learning seen in linguistics? And it's really seen as a set of methods and tools that allow computers to represent and process language. But that has two distinct ways in which it's sort of cashed out within linguistics. One is to do with performing real-world tasks in response to language input, and another is to do with aiding in the scientific analysis of language structure and use. And within the field, these are known respectively as natural language processing on the left there and computational linguistics on the right. But these two things have in common that they give us a way of modeling and thinking about language that treats it as a probabilistic usage-based system, which is important for both. So what I want to focus on today is the synergies between these approaches. So, for example, how computational linguistics can help with natural language processing, because knowing how language works can allow us to process it better, and how natural language processing can help with computational linguistics, because knowing how machines process language can help us, can give us insights into how humans do it. So what I'm going to focus on today is something called morphological segmentation, which basically just means splitting words into parts. So for example, if I give you this word, deforestation, you might split it into these three parts, deforest and ation. And this is a really helpful thing for users of a language, because if you can split up a word, you can elucidate its meaning. So if you don't know what degemination means, nevertheless, you can look at it and say, well, it's got something in common with deforestation. It's you know, the process of removing something. And here it's, if you have recognized Gemin from Gemini, as in the twins. It's removing doubles. Splitting words into parts is also a helpful thing for us, or something we're sensitive to, because we notice when parts are missing or the wrong parts are used. So if I said unforestation, you would look at me strangely. And so if these things are good for users of a language, then they're presumably also things that we would want our machines that process language to pick up on as well. So the question I'm going to focus on today is, how can people and machines learn to do this task of morphological segmentation? Specifically, how can they learn to do it without explicitly being taught? So what I'm going to do is I'm going to run through two studies. First of all, looking at morphological segmentation in machines. How does it work? How can we improve it with insights from linguistics? And secondly, looking at morphological segmentation in humans. What predictions does machine learning make for humans, and do those predictions check out? And throughout the talk, I'm going to be focusing on Maori, which is the indigenous language of Aotearoa, New Zealand, my homeland. So let's start by looking at morphological segmentation in machines. So the task is to learn morphological segmentation without being taught. And now that means, in this context, we're doing unsupervised learning. And the system that I'm going to focus on here is something called Morphesser, which does unsupervised learning using minimum description length criteria. So the basic idea of this model is that it applies Bayes' rule to a generative model to find the smallest set of simplest pieces of words, which are called morphs, that generate a set of training data words with the highest probability. And as in any sort of Bayesian model, it's really important to get a sense of what the generative model looks like. That's what gives the flavor of the model. And the generative model here has a strong assumption of concatenation. So morphs, or parts of words, are constructed by concatenating atoms, things like syllables or characters, which are assumed to be just drawn from a bag randomly. And then words are formed by concatenating those morphs, again drawn from a bag randomly. Now there is a problem with this generative model, and that is that concatenation, this process of sticking things together, doesn't apply to a process in language known as reduplication, where part of the word is copied and repeated following a template. So here are some words from Maori, and what you can see is that there are parts of the word that show up multiple times. They're colored there, and they sometimes show up on the left, sometimes on the right, sometimes they're different sizes. But all in all, what we can say about these is that they are copies of what's already there. They're not separate pieces. And this is a problem if we take a Morphesser model, train it on all the Maori words in the dictionary, and test it on these kinds of words that have reduplication in them. The results of the segmentation performance are really poor. So there's a few different ways of measuring performance up there, but for all of them, it's low performance. And you might think, okay, maybe this is not a huge problem. Maybe this is just something about Maori, but no, it's a really big problem. If we look at the languages of the world, most of them, shown there in the red and pink dots, in fact, 85% of the languages that are documented in the World Atlas of Language Structures have some sort of reduplication in them. And those languages that do have them, like Maori, it can be quite common. So in Maori, a quarter of the words in the language have reduplication. So if we are not capturing that, we are doing really poorly for this language, and we're doing really poorly for a lot of languages. So our solution to this problem is to say, well, hey, let's just tell the model that reduplication exists. So build knowledge of reduplication into this model, which has two parts. First, extend the generative model so that reduplication can be generated. And secondly, defining templates for when reduplication might be considered in this sort of reverse engineering Bayesian reasoning that goes on in the segmentation process. And for both of these things, we use insights from linguistics. So for extending the generative model, here again are the reduplicated, some example reduplicated words. And we make an assumption following standard linguistic theory that all of these reduplicated pieces, the bits that are colored and bolded, correspond to the same thing underlyingly, which is called red for reduplicant. So it's not pucky pucky, few few, tor tor, it's red pucky, red few, red tor, right? Once we've made that assumption, then all we have to do to generate reduplication is say, well, this red thing is in the bag of morphs as well. And then, of course, we have this wrinkle of, well, we don't actually see them spelled out as red. They're spelled out as other things that copy other things. And so we say that red gets its form from copying through a template. So then we have to define the templates. And for this, again, we look at linguistic description and linguistic theory. And these different kinds of reduplication can be split into different categories as to what is being copied and what direction it's being copied in. And there are various complications, little nuances, but basically it's this generic size and direction thing. And the more we build into that with these specific nuances, the more we can leverage expert linguistic knowledge in our system, but it's not necessary because it's really just built on these generic templates. So does it help? Well, here are the results, looking again at just those reduplicated words that I showed you before, where the original model performs really poorly. When we add this thing in, we boost performance by quite a lot, right? So knowledge of reduplication improves segmentation of these simple reduplicated words. But of course, not all words are this simple. In fact, so a simple word might be something like toto, the same thing repeated twice, but that usually shows up inside other words, very complex words. So whakatoto here, for example. How does the model do for those words? Well, here I'm showing you the results for a number of different kinds of complex words. The details don't really matter. The point is that in the top row here, these are all ones that have reduplication, and we've got the original model on the left within each panel and the extended model on the right, and the extended one is better in every case. So knowledge of reduplication improves segmentation of these complex reduplicated words. And in the second row here, we've got complex words that don't have any reduplication because we wouldn't want to hurt performance on them. And indeed, looking at the results here, you can see there's not a lot of difference between the original and the extended models here. So this improvement comes without big sacrifices for other words. So just to zoom out from this a little bit with some interim conclusions, unsupervised learning of morphological segmentation can be accomplished with the Bayesian minimum description length approach, which basically encapsulates firstly, noticing recurrent statistical patterns in experience, and secondly, attempting to explain them with a generative model. And in this case, as in any other case of Bayesian modeling, the assumptions of the generative model are really crucial. If there are missing assumptions, they're going to give us really low performance. Linguistics can help by identifying important missing assumptions, in this case by emphasizing a diverse cross-linguistic focus, not just looking at English and other European languages that don't have reduplication, for example. And also by operationalizing new assumptions. So leveraging what linguists know about how language works to try to figure out how to adapt generative models to make them work for these other kinds of languages. So with this understanding of how morphological segmentation works in machines, I want to look at how it works in humans. So I want to take seriously the notion that this simple model could be a model of human learning. So what does that mean? What are the core insights that this model gives for human learning? Well, one, learning leverages statistical recurrences in experience. Two, learning can occur through passive exposure, so there was no supervised learning going on here, all unsupervised. And 3, learning morphological segmentation does not rely on meaning. Even though the parts are, we understand them to be meaningful, we can learn them without having any explicit information about meaning. So there's a major implication here, which is that people should be able to learn simply through being exposed or listening to a language for long enough, even if they don't speak it themselves. And this is called statistical learning, which is a really well-documented thing in psychology, and it's been investigated extensively in laboratory studies. But what happens in the real world when we step outside the lab? Can we find this statistical learning in everyday situations? Well, to answer that, we would first have to know what evidence of statistical learning would even look like. And so we can take inspiration here from the generative model that was seen in the machine learning approach, that exposure in this form of learning gives rise to a big bag of morphs that's stored in my head somewhere, right? So here I am, I'm surrounded by a language that I don't speak, and I build in my head a bag of morphs. Now, in linguistics, that bag of morphs is called a proto-lexicon, but it's the same thing. This proto-lexicon is important because it gives us implicit knowledge of 2 kinds. Firstly, lexical knowledge, knowledge of what is or is not a word of a particular language. And secondly, phonotactic knowledge, knowledge of how words get sequenced, how sounds get sequenced into words, which means both what are possible and impossible words in a language. So for English, blisk is a possible word, but bnisk is not. And what makes a possible word sort of sound good for a language. So again, in English, 20s sounds a lot better than 12ths, and the made-up word klest sounds a lot better than the made-up word shishosh. So knowledge of all of these things comes from a proto-lexicon if you don't know the language in question. So we're looking for evidence of that kind of knowledge in order to see if there's something from this model that can help us understand what humans do. So we ran some behavioral experiments with New Zealanders who are, surrounded by Māori, but don't speak it. So we show them real words and made-up words and ask them to rate how likely they think each thing is to be a real word. And we have it, we ask them for real words that are more or less common under the assumption, again, inspired from this model, that if they're learning by exposure, then words they hear a lot, they should be better able to recognize. So here, we've got on the vertical axis the ratings, so higher ratings, more confident that it's a real word. The real words in blue there, and the fake words in black, and you can see the real words are rated higher than the non-words. So these people can rate real words higher than non-words, especially when they're common, meaning that they have this sort of lexical knowledge. What about the other kind of knowledge, the phonotactic knowledge? We do a similar thing. We show them a bunch of made-up words and ask them to rate how good sounding they are. Here on the x-axis, I've got words that are objectively better sounding. As you go further along the axis, that means that they better follow the statistical patterns of the language. And on the y-axis, the human ratings. And what we can see is that there's a really strong relationship between them, right? So participants do rate better sounding non-words as more Māori-like, implying that they have this sort of phonotactic knowledge. But what we would like to know is, well, what does this tell us about the underlying representations of this knowledge? What about the proto-lexicon that this stuff is supposed to be coming from as inspired by the modeling work? So there are some unresolved questions like what's in the proto-lexicon or how big is it? And we answer these questions by simulating different situations, different proto-lexicons, and comparing them to ask what explains the experimental results best. So we make a couple of comparisons. Firstly, where does it come from? So on the one hand, it could be built from a dictionary, which means that every word in the language is equally likely to be included in there. On the other hand, it could be built from exposure, which means common words are more likely to be included. And this is this built from exposure is the one that the Morfesser model was assuming. And indeed, that explains the results better for the humans as well. And as for what's in it, again, a couple of options. There could be entire words in there, not broken down into pieces, or they could be the pieces of the words, the morphs. And again, this morphs was the assumption that was made in the model. And again, that's what explains the human results best. And if we look at how big this proto-lexicon would need to be, if it contains words, 4,000 to 5,000 words would explain the ratings that we see pretty well. If it's these pieces of words, 1,500 to 2,000 pieces is what's required. So this means that this morph-based proto-lexicon, the thing that's inspired by Morfesser, explains the human ratings better while being smaller than this alternative. And why does it explain it better, and why is it so much smaller? Well, the model has a suggestion for that too. It's something to do with language structure, because these things are being learned by statistical recurrences in what people are experiencing, and those statistical recurrences are governed by the structure of the language. For example, Maori has a lot of compounds, lots of words stuck together, like these examples. And so that facilitates this sort of learning process. In alternative languages like Spanish, which doesn't have so much of that, the prediction would be that this learning is harder. And indeed, when we look at humans who were exposed to Spanish but don't speak it, that does seem to be the case, and that's what we're looking into now. So just to zoom out to the view from computational linguistics here, unsupervised learning models from NLP can apply to humans by generating predictions for behavioral experiments. And as predicted, people do learn morphs by passive exposure, highlighting the power of statistical learning here. And they make another prediction, which we're looking into, as I mentioned, that learning varies with linguistic structure. So to put all this together, I want to come back to this idea of synergies between natural language processing and computational linguistics, and hopefully you have seen, you can appreciate that these synergies are real. And I think they're really important now because the future is synergistic. So in NLP, as I sort of suggested by what I talked about earlier, there's an increasing recognition of the importance of cross-linguistic coverage. That is not just looking at English or other languages that are have large data sets and things like that. But in addition to that, there's an increasing desire to explain what models are picking up on and why, and knowing how a model solves a linguistic task might help us address bias in that model. So these are all things where linguistics can help with NLP. And similarly, in linguistics or computational linguistics, as I described, modern models and data sets do facilitate numerous predictions that are really interesting from a linguistic standpoint. But in addition, computational methods are increasingly common across the field, and automation, particularly machine-learned automation, can greatly assist with data annotation. So there are lots of places in linguistics that can benefit from NLP as well. So my big conclusion from all of this is the future is synergistic, so let's work together. Thank you for listening.
Okay, our next speaker is Paul Leonardi. He is the current department chair in technology management. Thank you, Paul. He also holds an endowed chair from the Duca family, and he's an expert in organizational communications, whether communication is technology mediated or not. He is also done a lot of work with networks and organizing for innovation. So how does an organizational network look like when the organization is an innovator. So this is Paul's research, and inevitably when you have innovation or you have technology in organizations, you have people reacting to that. And part of what he'll be speaking about today is how do people react to these technologies that vary in their transparency and in their functionality and even in their reliability.
Great, thank you, Kyle. It's a pleasure to be here and present. I'm the very last presenter of the day, so I promise to make it snappy. In the Department of Technology Management, for those of you who are not too familiar with what we do, generally faculty in our department study the way that organizations, both formal and informal, shape how technologies are developed, and also how the use of technologies, new advanced technological capabilities, can shape the way we work and the way that we organize. And so the arrow kind of goes both ways in what most of us study in the department. I'm going to do a presentation that is quite different from most of the ones that you have seen today. Rather than focusing on any kind of development and rigorous methodological innovation around machine learning and AI, I'm going to focus on use of AI in the wild. So how organizations are making use, perhaps, of capabilities that are embedded, AI capabilities embedded in new technologies. And this is joint work with a former PhD student, Camille Endicott, who's now at UNC Charlotte, and sponsored by a couple grants from the National Science Foundation. Camille and I became interested in trying to understand AI deployment within organizations because they represent an interesting kind of problem when AI and machine learning algorithms are embedded in communication technologies. And one of those problems that is of interest to us is kind of a broader interest in the social sciences and economics, is a principal agent problem or a principal agent dilemma, right? So when you have a principal who delegates some authority to an agent to act on their behalf, there are all kinds of incentives for the agent to act in ways that don't necessarily benefit the principal. The activities of the agent can reflect poorly or in good ways on the principal. And there's a whole lot of theory in the organizational sciences about how you manage this principal-agent relationship effectively. In many ways, when you have a communication-based technology that is embedded, has embedded artificial intelligence, those kinds of technologies can act on behalf of the principal without much intervention by the principal. And what I mean by that is if you think about the kind of technology that I'm going to be talking about today, which is a calendaring scheduling tool with embedded artificial intelligence, these tools have an agent that will go out linguistically, talk to people, and try to schedule the principal's calendar for them. And so that agent is making choices on behalf of the principal about when the meetings should be scheduled, how to present a request for scheduling, how to respond to somebody when they ask for changes in time. And all this, though this may seem like banal and not super important, think about the key role that scheduling plays in all of our lives. And think about how you adjust your schedule very often on the fly to accommodate people of different status or different importance to you, how your communication with those individuals signals your deference to them or whether or not they're important to you. And people can get very offended, right, if they're scheduled at inopportune times or the way you responded to them doesn't signal any proper a deference to their position. And so scheduling, while it may seem sort of banal, can also be a fairly high stakes environment for many people in organizations. And so we thought tools that are using AI to try to do scheduling on behalf of the user, what we call AICTs or artificially intelligent communication technologies, are an interesting context in which to explore this kind of principal-agent dilemma. We've done some other papers out of this data set on this principal-agent problem, but what I want to focus on today is a bit of an emergent finding, something that we didn't necessarily go in and thinking about, but let me frame it up for you in this way. We're all familiar with the concept of humans in the loop when we think about machine learning algorithms in particular. And in my area of research, people that study AI diffusion within companies in particular, one of the key issues has been how do you deploy an AI tool that doesn't work as effectively as we think it should yet? And this is a very common issue, right? Because at some point we amass all of the training data that we can, but we have to put the tool into practice at some point. And in practice, we'll be generating more data that we can use to run our trainings. So because we're implementing these tools in work contexts in which people are depending on them, there's a lot of work that has to go on behind the scenes often in order to supplement for the fact that the AI and the machine learning algorithms are not doing as good of a job as they potentially should. So many companies, will hire employees on gig platforms like MTurk, for example, right, in order to manually classify things that their algorithms can't seem to classify. They will hire people in offshore locations like the Philippines to correct recommendations that a machine learning algorithm gave to somebody in the context of their work or is about to give. So while many of the things that we've discussed here today so far have been about how do we generate the right kinds of methodologies that would forestall these problems in the future, many companies are plowing ahead and implementing tools that don't have the right kinds of algorithms in place or are sophisticated enough yet to deal with many of the complexities that you've all been describing. And that's where our research comes in, is to try to understand at this early stage, how are people making sense of and engaging with those? These kinds of, these processes by which humans get involved in the development of the algorithm, or at least in making the algorithm work for users, is something that's getting to be fairly well documented. And I put a couple of citations to some key works in sort of management sociology and information systems realms that look at this. But as we all know, this is not the entirety, of course, of what happens in a machine learning process. And hesitate to put the slide up here because you are all the experts on this. But essentially, one of the key issues is in the training, analyzing, and retraining of models in the field, right? So we have we have technologies that are being implemented, like the scheduling tool that I'll talk about, that are implemented knowingly by the companies, knowing that they do not have their machine learning algorithms yet tuned very well. And because they've exhausted all of the training data that they could get their hands on, they have simulated as much data as they possibly could. But because they also have a business to run and need to start making a profit, they release these tools to users early. And they're hoping that in the process of using, they will be generating mass amounts of data that they can run their algorithms on to train while the technology is actually being used. And if you think this sounds weird, this is an extremely well-used strategy amongst many early stage companies in particular. And one of the developers that we worked with said the following about this AI tool. So Liz, who's the name of the AI agent that I'll be talking about in a minute, if Liz messes up, the customer will correct it. They'll say, no, that's not what I meant, or they'll just override the time that was scheduled. So then that feeds back into Liz. So then the human in the loop becomes the customer. And it's cool because then we don't have to pay a human. So there are some very important implications for the kind of labor and work that goes on within organizations or any kind of social setting into which AI tools are implemented if we're actually relying on the user to do work that's helping to train an algorithm that then benefits the company because now they have a more robust algorithm. And so when we think about responsible machine learning, I hope that this perhaps provides us a slightly different angle about what are some of the ethical dimensions about when we decide that we're going to release algorithms into the wild and when do we not. And there's a huge amount of unpaid labor that many companies are reaping by deploying tools early, getting the users to be the guinea pigs and producing the data that then feed back into the machine learning algorithms. And much of this is happening on other companies' dimes or is coming out of the time that independent contractors are using as well. So when we think about this human in the loop on the development side, what I've just described to you we could also characterize as humans in the loop on a usage side. So a second loop would be the usage loop here. And this usage loop consists of individuals that are trying to make up for things that the AI can't do effectively in the context of their work. And there are a number of studies that are beginning to be published that are showing, in the case of radiology, also in the case of business analytics, how users are starting to supplement some of the work that needs to be done in order to train an AI, when, of course, they have sort of no responsibility in that area, and they don't provide direct feedback to the companies that are producing these technologies. They're buying these technologies and using them as users. So this usage loop is the thing that we really want to study. And one of the key questions that arose as we started our research was, why in the world would people do this? So if you're trying to deploy a technology and you have some choice over whether or not you're going to use this tool, and you find out that it's not working the way that you want, in other words, you're a principal and your agent is not communicating the way that you wish that it would, why would you continue to use it over and over again and correct the things that it's doing wrong when you are providing labor that's going to benefit the company and you may never see that return in your own work? And of course, on the usage loop, these roles, the MTurkers or the consultants in the Philippines, are compensated financially for filling in for the AI, right, or being involved in manual training of the data. But these users are not. And so our question was, what might be at play that is encouraging them to continue doing this kind of work? And I'll kind of breeze through this really quickly, but there is a fair amount of research in the organizational and social sciences around identity as a key motivator for why people would engage in work that doesn't seem like it would be directly useful to whatever their line of action is or their particular role. And so if they are using a technology in a way that is somehow bolstering or helping them to construct a sense of self, that can often be a mechanism for continuing to use this kind of technology, even though it's not working for them currently. But most of our theories about why identity provides a strong motivation for people to engage in unpaid labor that doesn't really give them much benefit have to do with a very public nature of that kind of work. So you end up getting credits in your community of practice, you're recognized as an expert, you potentially can sort of demonstrate your knowledge or teach it to other people. But in this context, we have users that are sitting at their desktops or on their phone, and nobody knows that they're making these kinds of corrections, and nobody knows that they're engaging in all of this labor. So it defies a lot of the rationales that we currently have in our literatures and our understandings of why people would engage in this kind of work. So our sort of two major questions that are guiding this particular project is, what is the work actually that people might be doing to supplement AI in this usage loop? And secondarily, why are individuals motivated to provide this kind of labor? Okay, so in order to answer these questions, Camille and I designed a study that looked at two different calendar scheduling tools, both powered by AI and machine learning algorithms. We chose these two different tools, one built by a company that we call Time Wizards, based out of New York City, and the other based out of a company we call Smart Hours. And both of these companies used very similar kinds of machine learning algorithms in order to determine what they called optimal scheduling parameters and patterns. But the way that they manifested the use of the AI in the design of the tool was actually quite different. So Time Wizards used an anthropomorphic agent, and you could configure this agent as either Liz or Leo. And Liz or Leo would use natural language processing to extract from email text, primarily, people's requests to meet. And then the algorithm would go and identify what would be an optimal time to schedule this person in your calendar, and then make recommendations, would actually go out and talk to the person and try to negotiate the appropriate time for you. Smart Hours, by contrast, used a link-based scheduling tool. So the algorithm would do the same thing to try to determine the optimal place to schedule someone in your calendar, but rather than communicating that on your behalf, it would send you a link that then you could send to somebody, or you could configure it to automatically send the link to someone to click on to choose the selected time that the algorithm recommended. So we chose these tools to look at, to compare, because they made use of artificial intelligence in roughly the same way, right, behind the scenes, but in practice, in the implementation of the tool, the interfaces are quite distinct. Also, they had slightly different mental models for what optimal schedules should look like. And if you're interested, we can talk about this later, but a portion of our project was to try to understand how did the developers' mental models about how people wanted to schedule impact the initial parameters that they set for these algorithms to learn on. And what kind of conflicts did that have with the way people actually thought about scheduling their days and whether they would actually show up to meetings that were scheduled on their behalf or not. So we compared the use of these two different scheduling-based platforms by a number of users, most of whom were independent contractors, but many of whom worked, several of whom worked in large organizations, at two different time points. And we also talked to many of those users' communication partners. So if I was the principal and I'm the one that's deciding that I'm going to use one of these tools, I'm scheduling with a bunch of people all the time that are also interacting with this tool that's communicating on my behalf. And so we looked at data from those communication partners and from the principals as well. One fortuitous thing happened that we did not plan for, though, was that between our time 1 and our time 2 interviews and observations with these users, Time Wizards discontinued their anthropomorphic agent and switched to a very similar link-based system that Smart Hours was using. And so what that fortuitous change allowed us to look at was what kinds of effects did this anthropomorphic agent have on the way that people were sort of interpreting and making sense out of the tool, because we could compare what they did pre and post and also compare them to Smart Hours, who had a very constant link-based system the whole time. So I'll talk a little bit about that in a minute. I'm going to kind of just breeze through these findings, mostly because it's the end of the day. But the first thing that I would like to highlight is that the users that chose to sign up for these two different tools, and they had roughly the same price point, seemed to choose these two different technologies for different reasons. So people that were drawn to Time Wizards really thought that the use of an anthropomorphic agent in particular and being able to schedule with an AI was in line with their own self-conceptualization as technology enthusiasts. And so almost everybody that we talked to said, I'm super excited about using this new tool. I hope it helps me to schedule better, but I'm someone who really likes to use whatever new tool comes out, and my ability to use an AI agent is really exciting. And many of them who are consultants thought this could potentially help me win more business if people see that I'm really at the cutting edge of a lot of new technological trends. So to give you just sort of a snapshot of what some people were thinking, this is just sort of an anecdotal quote here. Remember, you could configure this tool to be Liz or Leo. And I won't discuss the gender implications that we uncovered about whether people chose it to be Liz or Leo. So this is the anthropomorphic agent, right? You could decide, does it take on sort of a gendered female or a gendered male persona? I used Liz a lot because of the cool factor. I scheduled a meeting with someone who said, I wasn't going to take the meeting, but your AI is really cool, so I have to give you some credit and take it. It makes a big difference in my effectiveness, but it also sends a message to the people that I'm trying to schedule with. Like if I'm trying to impress somebody with AI, Time Wizards can speak to that. And Bob is a very productive, highly paid organizational and management consultant, and thinks of himself as a avant-garde user of new technologies and believes that these kinds of tools using an AI is going to help him win more business, and could provide a number of anecdotes for how that actually might be helpful. Smart Hours users, by contrast, by and large, were attracted to the tool for a different reason. They conceptualized themselves not as technological gurus, but as master schedulers, people who were really, really good at figuring out how to arrange their time and schedules and meet with people and be very conversant with their audiences. And they were drawn to that tool because the promise of machine learning algorithms to help them work through their schedule meant that they could be even more efficient at what they did. And so they were not interested in having an AI agent personified, anthropomorphized as Liz or Leo out front talking to people, as long as they had the predictive capabilities of machine learning algorithms running behind the scenes. And so a user set of Smart Hours said, it makes me more accessible, but it also allows me to keep my boundaries. My clients think that I'm more organized and that I have my stuff that's cover for an expletive together. And this was largely the kind of sentiment about why these users were attracted to these different kinds of tools, even though they roughly provided the same kinds of capabilities. So I'm going to kind of breeze through this, but what we uncovered as we were taking a look at the different kinds of activities and the different kinds of ways that people use these tools was that regardless of whether our informants were using the Smart Hours tool or the Time Wizards tool, they had to engage in a lot of supplementary work to help these tools schedule. So neither of these tools did an amazing job of scheduling in ways that made people's lives a lot easier, even though that's precisely what they were paying for. And I outline here just 4 different kinds of work that we identified that people spent a lot of time doing. Operation work, so they had to help signal to the AI when their availabilities were. They had to fill out lots of questionnaires to get the tool up and running. They had to integrate it with their email platform. There were breakdowns that happened. So these are things they had to do to just get it operating correctly. They had to codify their schedules. And then the last 2, I think, perhaps are the most interesting in the context of a communication tool that's communicating as an agent on somebody's behalf. There were a lot of scheduling errors that were made that the principals had to go and correct, right? And so sometimes these tools would schedule a face-to-face meeting even though somebody was located in Boston and their person that was scheduling the meeting was located in Los Angeles. And so they had to go in and make those kinds of corrections. They also had to do a fair amount of relational work, like when somebody got upset because you scheduled me only for 20 minutes at the end of the day on a Friday. What are you talking about? That's really what you think of me? And so they had to send emails and make phone calls, right, to try to do some repair work because the AI was communicating on their behalf in ways that they didn't feel like really reflected how they wanted to present themselves to the people that they were communicating with. So on both platforms, users engaged in a lot of this work, and what this table tries to show is just kind of an average of the number of kind of instances of people mentioning engaging in these kinds of work across our interviews at these 2 different time periods. And what you'll see, what I want to really point you to is the comparison along the far left here, or sorry, the far right. That at Time Wizards, when the tool was configured as this anthropomorphic agent, users were spending much more time, right, engaged in these kinds of practices to help get the AI working properly. Right, they had to do a lot more repair work, they had to do a lot more relational work, they had to do a lot more operational work than the users of Smart Hours did, which you can see there as an average of 4.5 practices in time 1. After the Smart Hours, or sorry, Time Wizards changed from this agent anthropomorphic agent-based interface to the click and link-based interface that Smart Hours was using, you see a drop in the amount of time that users had to spend on that. But you can see, even more interestingly, that the means drop below what users at Smart Hours were doing. So one interpretation could be that, well, now they just don't have to do as much of this kind of work, right? Because there's this sort of easy click interface. But what our interviews and observations uncovered was that users on the whole were very upset that Smart Hours, Time Wizards made this change and dropped the anthropomorphic agents. And a big part of the reason was that, if you recall, one of their primary attractions to this tool was that they believed that having the AI front and center really helped them portray an image as a technological guru or an early adopter, could potentially help them to win their business. And because they were enabled to enact that identity, or at least present themselves as this kinds of technological avant-garde, they didn't mind putting in the extra work to help make the AI function such that it was sending data back to the developers who were learning and could constantly update the algorithms. But once they made that change, there was much less motivation for them to continue using this tool. And one of the folks at Time Wizards talks about this. We had a glitch and it ended up sending out 3 invites for the same meeting, and with an intro to the client, I think it has great potential for us. And for me, that was a bit embarrassing. For them, it was a bit like, whoa, what's this idiot doing? even though they had to do this kind of repair work, they still were willing to do it because the technology helped them to bolster the kind of self-presentation or identity that they wanted to communicate to their other users. And smart hours rarely reported these kinds of issues, largely because that AI was not front and center. And with the advent of things like scheduling links, it's made it even easier for me to be available to meet people who want to solicit help, but while being protective of my time because they're meeting me on my terms. So there's a couple of sort of key implications that I think are important for work and technology use in general, and speak really to a lot of the communities that our research talks to, which is trying to understand how are new technologies, like many of the algorithms that you are all developing that will at some point be implemented in many of these kinds of applications, right? How those are affecting the way that people work and the way that organizations operate. And I think I won't go through all these in depth here, but really trying to understand that there is a tremendous amount of motivation for people to engage in this kind of unpaid labor. And we've identified identity as a key motivator for why people might engage in this behavior. But to the extent that changes in the deployment of the tool may affect people's ability to feel like they're enacting their identity, might lead them to be discouraged in using this tool or give up use of these kinds of tools. And again, I raised this point in the middle, but I'll raise it again here. What kind of implications exist for us as developers of tools or as companies that are deploying these if we're relying really heavily on a user base that's not in our beta testing pool, right? But that we're deploying and asking to pay for these technologies, if we're requiring them to do a whole lot of the work to keep the tools running so that we can continue to make our algorithms work more effectively behind the scenes. So I think I'll end there. Thank you very much.
What are your questions for Paul or Simon?
Thank you. It's a really interesting talk. This question is towards Paul. So you mentioned this very interesting aspect of voluntary labor for annotating and improving the deployed software systems, machine learning-based system, by providing more data. I think there's an angle that's first of all, what you said makes a lot of sense. But there's another angle that happens when companies release their software for, say, alpha testing, right? So people who want to get their hands on the new version of the software they find to be really cool early, like they will be voluntarily doing the work. And there's also, for specific to machine learning, there is this personalization angle to this, and this is made very obvious from spam filtering, right? So if you annotate your emails with spams and non-spams, right? If you do that more than other people, then you're getting a better service out of it, right? So I think for the company, they're providing the tool, and that tool has a data component in it. But for the tool to be robustly leveraging the additional data that individual users provide to provide a better service, there's an incentive there for the users to actually provide this actual help for the system to keep improving. If it's also helping other people, right, maybe they should be paid, but on the other hand, they themselves are getting the benefit.
Yeah, it's a great question, and I'll answer it in two ways. So the first is that you're absolutely right that when people enter into alpha or beta testing regimes, right, they know that they're providing this kind of labor for companies. And I think of how often does Elon Musk send out a tweet like where somebody complains about, Tesla's autopilot system, and he's like, well, you're on the beta, stop complaining about it, right? Don't expect it to work well. You signed up for this. These users, though, aren't in those kinds of programs, right? So they're paying fairly high rates. Both of these are SaaS companies, right? But a fairly high monthly rates in order to have these tools, and their expectation is that they're working fairly seamlessly. And at the early stages in both of these companies, they were doing the human in the loop on the development side. So they weren't able to process calendaring requests fast enough and accurately enough, and so they had all kinds of coders in the Philippines that were going in and trying to correct some of the errors that the machine learning algorithm was making. So part of it may be, do we need to signal better about what phase the project is in, right? So I think that's kind of one way to think about it. The other thing that we noticed is that, so both of these companies really advertise that you're going to be getting personalized recommendations, right, that are optimized to you, which is exactly what you're suggesting, right, that you have to turn over a certain amount of data and potentially do a fair amount of work in order to get those personalized recommendations. What was interesting, though, is that behind the scenes, neither of the companies were actually doing that. So what they were both doing was they were trying to create macro models that would learn from, you know, several million data points about what optimal scheduling patterns were, and then use those to suggest generically how people might want to schedule better. And so one of the things that Camille and I sort of speculate is that if you have this sort of model, are you actually pushing people to be more homogeneous in the way that they act? If you're creating, you know, best practices essentially, right, from all of these data points, and then pushing those recommendations back to people as, you know, scheduling inferences essentially, rather than trying to fine tune it for everybody's individual scheduling practice. So this was definitely an instance where the rhetoric of what the companies were saying that they were going to do did not match the reality of what they were actually doing behind the scenes.
There's a bit of implicit like personalization that's perhaps happening. Anyway.
We have time for one or two short questions. Okay.
Hi, short question for Paul. Did you study how the other party of the negotiation process reacted to like one or the other tool, like whether clicking a link or being fooled into like talking to an actual human? Like, was there any difference?
Yeah, great question. We did, and I just didn't have time to present those data today. But we talked with about 70 or 80 different people who were the recipients of these scheduling events. And for the ones that use the anthropomorphic agent, I would say 90% or so thought they were interacting with an actual person. And they would you know, treat that agent as a person, and in some cases got really frustrated. And one of the things that we were interested in was, would their impressions that they built about the agent, you know, as like, this person is really annoying, would those transfer to the principal? And in many cases, I mean, I can't say this conclusively, but anecdotally, it seemed that they did, right? So if somebody got really frustrated at the agent, they also got really frustrated at the principal, thinking that the principal was instructing the agent to deprioritize this person in the scheduling, or to communicate really abruptly with them.
So I have a question I do want to ask Simon. I'm really curious about, I think this is a question for both of you. You know, when you're looking at, you know, this kind of analysis, or you can looking at more faster, or whether it's the scheduling tool, how do you account for this, you know, expert versus layman, or, you know, expert user versus general user in your study? Because I assume that, for example, I don't know Maori, right? So when you look at your Morphetha tool, you know, there's the learning curve, right? So I'll be very curious, you know, your experience of getting expert or non-expert users using such tool.
Yeah, so I think this is why we use Morphetha as a model of what people who don't speak the language think, right? Because that's exactly the kind of situation that you would be in if you're just exposed to this and you're trying to figure out the patterns on your own. If you use it as a model of actual morphological segmentation by people who speak the language, then for some languages it's very good. You know, Finnish, it's very good at. There's lots of compounding in Finnish, for example, but other languages it's not very good because it can't access those other pieces of information that people are bringing in as expert speakers of that language, things like meaning, or, you know, even just other kinds of data that they've seen, or various, in our case, knowledge of reduplication, right? So yeah, it comes down to what you, how you are using the model, how you are mapping the model onto, you know, what you're trying to study in people, in our case.
William is going to tell us what to do next.
Thank you. Let's thank the speakers. item for today is the breakout session, because we are already running a little behind, so we will run a relatively short breakout session. I think having this unstructured talks is still important, but we'll just keep it relatively short for the breakout session. So let me tell you what the 3 topics are. So basically, we have 3 topics to discuss. Each topic, you know, I carefully chose each topic, and I think they reflect really well with the things that we would like to discuss today. So let me show you what the 3 topics are, and then I'll tell you the location. So the format of the breakout session is that each group will basically elect a leader of that group, and then the leader will summarize the discussion. But we have 3 to 4 questions for each of the topic. And then basically, you know, for each group, we need to discuss this topic, and around 5:10, and then we'll come back and summarize our findings. So the first topic is the responsible and safe use of AI. For example, what are some ethical challenges of AI? How do we measure and quantify harm from these AI systems? And what are possible mitigation strategies, right, with some of the, you know, bias and concerns from AI systems? And how do we actually consider some underrepresented communities who are not involved in the AI R&D process? So for the topic 1, you will come to the front of this room, and then this is the first group, okay? The second group is making the most of AI data and foundation models. And as you know, foundation model has been really powerful recent years for AI applications. So what are some good practices, right, for your data collection for AI applications? How do we build more useful AI models, right, for these domain-specific applications we've seen today? And what are some opportunities, right, for these foundational models, for example, GPT-3 or DALL-E or BERT model being applied, right, in your in-domain applications? So if you are interested in topic 2, you will stay in this room, but you are going to be staying at the back of this room, okay? And finally, the last topic is interdisciplinary collaborations in AI, that this is also part of the reason why we're here today, to really think about, you know, these good practices, right, in cross-disciplinary collaboration, because, you know, part of that is research, part of that is technology, but also I think an important part is how do we start, right, this kind of cross-department collaboration. How do we facilitate student collaboration? Because many of our students will also join the breakout session, right? So how do we actually provide better education to you and better research opportunities to you as a student interested in AI and applications? And finally, I think, you know, this is also, you know, a topic for faculty and students. How do we attract, you know, more faculty to UCSB, right, in related areas? How do we facilitate cluster hire, right, in the area and in this critical area? You know, not just hiring faculty, but also hiring graduate students too, right? So if you're interested in the third topic, you would exit the room and you will go into the conference room next to this particular lecture hall. So we give you about 20 minutes, and then you can discuss, and we'll come back at 5:10 to summarize and close today's session. Thank you.
And you're not? For what reason?
topic 1 here, topic 2 at the back of the room. So this is topic 1, responsible use of AI, and that is the data, right, and also the foundational model. Can I ask you to do this for?
How do we map